मैडम नमस्कार।
लिंकाबू नमस्कार, गुड मॉर्निंग टू ऑल।
मैडम नमस्कार। नमस्कार
लिंकाबू
आज्ञा
कि समस्त फोन मारंतु जॉइन करंतु केते लोक नांती 9:15 हेलानी।
आज्ञा आज्ञा जणोच
आम लोक तो जॉइन करंतु।
आज्ञा आज्ञा हां जणोच।
हेलो गुड मॉर्निंग डॉक्टर सुंदरम।
Good morning, ma'am.
Good morning.
Yeah.
I'm telling Dr. Lenka to call our people at least to join fast. So make it.
My team is also joining in our committee room, ma'am.
Okay.
About 15-20 people are joining there.
Okay.
I'll just keep myself muted so that as soon as the function starts, I'll join.
Yeah. लिंकाबू फोन मारंतु कोंतु से पिला जे अछि पाखरे।
मैडम मु करछि नायक सर के करछि आज्ञा हां।
म्यूट करी कोंतु।
Sir, very good morning, sir. Datta sir.
Good morning.
Good morning.
Can you hear me?
Yes, sir. Yes.
Sir, good morning, sir. Pranam, sir.
Good morning, Dr. Sundaram.
How are you, sir?
Yes, sir. दत्ता सर प्रणाम।
Good morning. Good morning.
Namaste, sir.
Good morning, sir. Pathak, sir.
Sir, good morning.
Good morning, President.
Madam.
Good morning.
पाठक सर नमस्कार।
Yeah. बड़ा उनका हो रहा है।
गुड मॉर्निंग डॉक्टर सुंदरम।
Good morning, sir.
Morning.
Good morning, everyone.
Sir, good morning. Good morning, sir, Professor Datta.
Good morning. Good morning.
Good morning, Dr. Sundaram.
Good morning.
Morning.
Dr.
Morning.
डॉक्टर प्रणाम। प्रणाम डॉक्टर।
Namaskar, 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 namaskar.
सर प्रणाम सर, नमस्कार।
Namaskar, Lanka Babu.
हाँ सर मैं थोड़ा फोन कर रहा हूँ सब। अच्छा हाँ सर।
परिडा जी नमस्कार सर।
Sir, good morning, sir. Pajita, sir.
Arina sir.
शायद आप muted, sir.
Muted है। Sir, आप unmute कर दीजिए। Sir, unmute कीजिए।
प्लीज ऑन।
Parida, हाँ। Sir, good morning, sir.
Good
Parida,
morning,
sir.
sir. Good morning.
Sir,
Good morning, Dr. Parida. How are you?
He is always well.
Yeah.
He has to.
That's right. I think along with rice, he has also accumulated some genes of stress tolerance from mangroves or prosopis or some other plants.
He has to tolerate now COVID-19 also.
Yeah. And I think, sir, ILS is doing really good job for testing and those kinds of things during COVID situation. I always see his, postings in Facebook and some other social media. Also in some newspapers, yes.
So as a token of appreciation, they now like to see that how resistant he is.
Yeah.
And he proved that yes,
That's right.
he can handle it. He can handle it.
Dr. Reddy, good morning.
yeah. Reddy, sir, namaskar.
सर नमस्कार। सर अनम्यूट करो अनम्यूट।
हाँ, sir.
Good morning,
Sir.
Datta sahab.
सर नमस्कार।
Good morning,
morning,
Dr.
Pathak sahab.
Reddy. Good morning. Good. This is the beauty of online virtual mode, that you can meet anybody and everybody anywhere, anytime.
हाँ हाँ करूचंती हम देखिली धीरे धीरे बढ़िले टिके फोन मारंतु
I think, madam, we can start now.
Yes, sir. We can start, sir.
Yeah.
okay sir yeah
So,
okay sir Dr. Kuttu Dr. Kuttu sorry sir maybe some problem with Dr. Kuttu.
नहीं कुतुब जान कर गया कर रहा है.
Okay
Yes, sir.
हाँ आ गया.
yeah
Yes, you can start.
Okay. Good morning. 1 second, please. A very good morning to everyone. I am Kutubuddin Mullah from National Rice Research Institute, Cuttack, and we are very happy to receive such a large virtual gathering for the ARRW Golden Jubilee Symposium 2021. Thank you so much to all of you for joining us for this 2-day symposium on Gen Next technologies for enhancing productivity, profitability, and resilience of rice farming. Respected chief guest, Professor Swapan Datta, founder Vice Chancellor, Vishwa Bangla Vishwavidyalaya, West Bengal, and former Deputy Director General Crop Science, ICAR. Today's guest of honor, Dr. Ajay Parida, Director, Institute of Life Science, Bhubaneswar. Dr. Himanshu Pathak, President, Association of Rice Research Workers, Cuttack, and Director, National Institute of Abiotic Stress Management, Baramati. Dr. Padmini Shwai, Director, National Rice Research Institute, Cuttack. Dr. R.M. Sundaram, Director, Indian Institute of Rice Research, Hyderabad, and Dr. M.J. Beg, Secretary, ARRW. All the distinguished delegates, ladies and gentlemen. An expanding global population and changing diets are increasing the demand for food. Production is struggling to keep up as crop yields become stagnant in many parts of the world. Ocean health declines and natural resources like soil, water, and biodiversity are becoming dangerously thin. The challenge is intensified as agriculture is extremely vulnerable to climate change. The negative impacts of climate change are no longer only discussed in scientific fora. They are already being felt by commons. We have great hope also as mankind is experiencing a technology boom in all fields. We got genome editing as a new breeding tool. Agribots and drones are helping us in precision crop production. Artificial intelligence, machine learning, facilitating us analyze big data and derive new perspective. You know, flooded rice paddy fields account for around 12% of global anthropogenic methane emissions. And we are in need of disruptive next generation technologies that could facilitate us to find the right equilibrium between food security through rice farming and also to limit global warming. Keeping in mind those facts and to celebrate its 50 years of glorious journey, ARRW is organizing this Golden Jubilee Symposium in collaboration with Indian Council of Agricultural Research, New Delhi, National Rice Research Institute, Cuttack, and Indian Institute of Rice Research, Hyderabad. Association of Rice Research Workers is one of the oldest societies under the Society Act of India. It was established way back in 1961. Well, ladies and gentlemen, over the next 2 days, this symposium will provide you plenty of opportunities to discuss and brainstorm next generation methods, tools, and technologies, and also to share knowledge, ideas, and insights. And so, to kickstart this wonderful deliberation, I would like to request Mr. Santosh Shetty to play the ICR song, please.
जय जय कृषि परिषद भारत की सुखद प्रतीक हरित भारत की कृषि धन पशुधन मानव जीवन दुग्ध मत्स्य फल यंत्र सुवर्धन वैज्ञानिक विधि नव तकनीके पारिस्थितिकी का संरक्षण शस्य श्यामला छवि भारत की जय जय कृषि परिषद भारत की हिम प्रदेश से सागर तट तक मरुधरती से पूर्वोत्तर तक हर पथ पर है मित्र कृषक की शिक्षा शोध प्रसार सकल तक आशा स्वावलंबित भारत की जय जय कृषि परिषद भारत की जय जय कृषि परिषद भारत की
Okay, thank you, Mr. Santosh. So we are happy that we have with us Dr. Padmini Shwai in this inaugural session. And you know, Dr. Padmini Shwai is the director of National Rice Research Institute, Cuttack, and she is well known for her work with rice drought tolerance. Sorry. She has over 30 years of experience working with physiology and biochemistry of rice drought response. So without further delay, I would like to request Dr. Padmini Shwai, Director in RRI, for welcoming our chief guest, guest of honor, and other dignitaries and delegates in this symposium. Madam, please.
Thank you, Dr. Kutu. A very good morning to all. Most honorable today's chief guest, Professor Swapan Kumar Datta, former DTG Crop Science ICR, and presently the first Vice Chancellor of Viswa Bangla Vishwavidyalaya, Bolpur, Sriniketan, West Bengal. Today's guest of honor, Padma Shri Dr. Ajay Parida, Director, Institute of Life Science, Bhubaneswar, Chairman of this ARRW Golden Jubilee National Symposium 2021, and President ARRW Dr. Himanshu Pathak, presently Director ICAR National Institute of Abiotic Stress Management, Baramati, Dr. M.J. Beg, Organizing Secretary of this symposium and Secretary ARRW, dignitaries, delegates, and participants across the country, scientists, students, ladies and gentlemen. It is indeed a great pleasure for me to welcome you all to this ARRW Diamond Jubilee National Symposium 2021 on Gen Next Technologies for Enhancing Productivity, Profitability, and Resilience of Rice Farming. I am thankful to Professor Datta for accepting our invitation, gracing the occasion, today's occasion, particularly as a chief guest. I am thankful very much to you, sir, and I wholeheartedly welcome you to this symposium. I am thankful to Dr. Ajay Parida, also accepting our invitation to grace this occasion as guest of honor, Director ILS of Bhubaneswar. I am extremely happy to welcome you, sir, to this function. I also welcome Dr. Himanshu Pathak, Director NIACM and President ARRW, for his wholehearted support in organizing this program. I also welcome Dr. M.J. Beg, Secretary ARRW, Organizing Secretary, and organize a whole program on his expert. So I welcome you all once again and to this inaugural function, and I also expect that this will be a very successful program, 2 days program. I welcome you all again. Thank you. Dr. Kutub, you can carry forward.
Thank you, ma'am. I must say that we are also lucky to have with us Dr. Himanshu Pathak. Dr. Pathak is the Director, ICAR National Institute of Abiotic Stress Management, Baramati, Maharashtra. He obtained MSc and PhD in Soil Science and Agricultural Chemistry from Indian Agricultural Research Institute, New Delhi. Previously, he served as the director of this institute, ICAR National Rice Research Institute, Cuttack, and also as a principal scientist and professor at IARI, New Delhi. And he was the co-facilitator of Rice Wheat Consortium, New Delhi, and a visiting scientist of Institute of Meteorology and Climate Research, Germany, and University of Essex, United Kingdom. His research includes soil science, climate change, and abiotic stress management. He has published about 200 research papers with H index of 66, item index of 188, and more than 17,000 of citations. He was the lead author of the IPCC 5th Assessment Report and refinement to the IPCC guidelines for national greenhouse gas inventories. He is a fellow of Indian National Science Academy, National Academy of Science India, National Academy of Agricultural Sciences, and also Humboldt Foundation and Rafi Ahmed Kidwai Awardee of ICAR. Dr. Pathak has been included in the Reuters top 1,000 global climate scientists by the study of Stanford University, USA, recently published. So it's my real pleasure. I'd now like to request Dr. Himanshu Pathak, President ARRW and Director NIACM Baramati, to say a few words to introduce the symposium to the audience.
Thank you very much, Kutub. Good morning once again to each and every one of you. Very honorable chief guest of the day, guest of honor, all my distinguished colleagues at NRRI and IIRR and many other institutes in India and across were working on rice. Kutub has very brilliantly introduced the symposium today. I shall just add a few words to what he already said. Friends, all of you know that rice, the golden cereal, is the world's most important food crop. We are growing this crop for more than 7,000 years. The crop is feeding 4 billion people. It's source of livelihood for many more billions. And this is the crop which is key to global food and nutrition security. And for Asians, particularly for Indians, rice is our life, rice is our livelihood, it is our culture, and also it is our heritage. Asian farmers and also most of Asians are born, live, and die with rice. And this is the importance of rice. If you see the rice scenario in our country in just last year, 2021, we have produced 121 million tons of milled rice, that is equivalent to 182 million tons of paddy. It is feeding 0.8 billion people, 65% of population, harvested from 43 million hectares. So 22% of total cropland of our country is grown with rice. It is providing livelihood to 150 million rural poor. 40% of rural poor are getting livelihood from rice. The crop also receives 30% of total irrigation water, 37%, around 40% of total fertilizer, and also it emits a substantial amount of methane, which is a very important greenhouse gas. In many of these parameters, rice is #1 crop in our country and also globally. Fortunately, there are many positive developments in Indian rice sector. The productivity of rice is increasing, and this year we had record production of rice. Rice production has become more climate resilient. Some of the data shows that the risk and uncertainties have reduced. In COVID situation also, the sector performed very well, probably the best among all other sectors of our economy. Greenhouse gas emission intensity is reducing. This is another good observation. And nitrogen use efficiency in rice is improving. Not very big way, but in some way it is improving. But nevertheless, there are many challenges with rice farming. Challenges of market, all of you know, monsoon, climate change, mechanization, management, mainstreaming, and many others. All these 5 M's are the major challenges. But if you have to summarize it, low income in rice farming is one of the probably most important challenge which our country and many other developing countries are facing. Depletion of groundwater, particularly in northwestern part of our country. Contribution to climate change, as I mentioned about methane emission. Burning of rice residues, again, not only now limited to northwestern part of our country, it is extending to almost the whole country. And uncertainty in sustainability of rice production. So all of these are the major challenges. With these challenges, we have promises to keep. We have to achieve sustainable development goals. And for a country like ours and many other countries in Asia and also globally, sustainable rice production is the key to achieving the sustainable development goals. And that's why many times I say that sustainable development goals is equal to rice development goals. If we cannot improve the rice sector, if we cannot make rice farming sustainable, probably we will not be in a position to achieve sustainable development goals. Along with this, my friends, all of you know that to combat global climate change, India has committed 5 major commitments. We call them Panchamrit in the very recent concluded COP, Conference of Parties 26 meeting. And they are the most important of all these commitments are that the country will attain net zero emission and carbon neutrality by 2070. There are 4 other commitments which we need to achieve by 2030, including reducing emission intensity by 45%, drawing 50% of energy from renewable sources, raising non-fossil fuel-based energy capacity to 500 gigawatt, and cutting carbon emission by 1 billion tons. So these are our commitments. So to achieve sustainable development goals and also to fulfill the commitments which we have made, certainly we now need to shift to next generation. Before I go into the specific objectives of the symposium, let us all remember the quote of Albert Einstein when he said, "We cannot solve our problems with the same thinking we used when we created them." So if you have to solve the emerging problems, probably your thinking, your knowledge, your technologies, your science also needs to be different. And there comes high-tech or next-generation technologies for evergreen rice farming. We shall discuss each and every of all these high-tech technologies in today and tomorrow's deliberation. But what we need to remember is that whatever we do in rice sector or agriculture sector as a whole, it must be backed by sound science. It must be backed by new generation of technologies, next gen what we are talking. Whether we talk of high-yielding stress-tolerant crops, automation and mechanization, efficient need-based input use, integration of all other sectors of agriculture to develop integrated high-tech rice farming. So keeping all of this in view, we decided to have 2 days deliberation on Gen Next technologies. Before I proceed, let me very briefly define what we want to talk over here. When we talk of Gen Next or next generation technology, these are the ones which has been developed using the latest tools and techniques. And these technologies are more powerful and have been demonstrated for considerable advantages over the existing ones. And probably these Gen Next technologies will replace the existing ones. So this is what we want to talk. The specific objectives of this symposium are to deliberate on Gen Next technologies to address the challenges in rice sector, particularly to produce more and better food to boost income, to reduce the vulnerability to abiotic and biotic stresses in rice, to enhance the efficiency of agri inputs to reduce cost and also environmental pollution, including climate change, to identify the key areas of research, development, and delivery for sustainable rice farming, to sensitize young researchers and students on Gen Next technologies, and finally to develop an action plan for promoting Gen Next technologies for sustainable rice farming. So these are our specific objectives, and we are going to discuss all of this in 4 themes. First one, Gen Next technologies for rice improvement, where we shall discuss about genomics and precision breeding tools for stress tolerance and higher resource use efficiency, also designer and nutritional rice. Second theme is precision technologies for rice production, where we shall discuss about precision agriculture, mechanization and customization in rice farming, and also how to mitigate greenhouse gas emission and making rice sector more adaptable to changing climate. Thirdly, we shall discuss about Gen Next technology for pest management, where we shall deliberate upon decision support system, forewarning techniques and models, sensors, drones, bioresonant and Gen Next pest management techniques. And finally, we shall deliberate upon livelihood security, equity, and profitability, particularly agribusiness and entrepreneurship development, big data management, e-agriculture, Internet of Things, robotics, and many other latest technologies. In the whole symposium, we have got several of the activities. Besides inauguration, we shall have plenary lectures, panel discussion, evening lectures, lead lectures, lightning talks, and of course, valedictory session. And also we shall have our ARRW General Body meeting and also ARRW award ceremony. I shall request each and every one of you to kindly join in all of these sessions. On my right side, you can see our speakers, probably almost all the who's who of not only Indian rice sector, but also global rice sector. Global rice sector are going to speak, going to deliberate upon all the themes and issues which I just mentioned. So with this, I invite each and every one of you once again to this very important symposium, and I wish this symposium a grand success. Thank you very much once again, and over to Kutub.
Thank you, sir, for giving us a wonderful overview of the symposium. It could not have been better. So, today we are lucky to have Dr. Ajay Parida as our guest of honor. And I would request Dr. Himanshu Pathak to introduce him to the audience and request him for his remarks.
Thank you very much, Kutub. Friends, let me tell you, it is indeed a pleasure and also an opportunity to introduce a very old friend. No, it is not that he is old. Our friendship is old, actually. Dr. Ajay Parida, all of you know, is really a very renowned plant biologist. Currently, he's the director of Institute of Life Sciences at Bhubaneswar. Prior to this, he served as the executive director of Professor M.A. Swaminathan Research Foundation in Chennai. He has got a very long association with Cuttack. He did his graduation from Ravenshaw College, Cuttack, way back in 1982, Master of Science from Utkal University, and then PhD from Delhi University. He had postdoctoral experience in many institutes and universities abroad, including University College of Wales in UK, University of Naples, International Rice Research Institute, Philippines, and so on. He was awarded Padma Shri, the coveted Padma Award of our country, also MGK Menon Lecture Award from National Academy of Sciences, Samantha Chandrasekhar Award, Government of Odisha, Recognition Award in Crop Improvement from National Academy of Agricultural Sciences, Tata Innovation Fellowship from Department of Biotechnology, Government of India, and many more. The list is really, really long. He's a fellow of National Academy of Science, Allahabad, and also National Academy of Agricultural Sciences, New Delhi. His research includes mostly developing climate-resilient crop varieties with abiotic stress tolerance, particularly salinity, as well as drought. He identified salt and drought-tolerant genes using mangroves for salinity stress and Prosopis juliflora for dehydration stress. His research has really contributed to the basic understanding of the genetic architecture and species relationship in mangroves, cereals, legumes, and many other cultivated crop species. He has supervised around 25 students for their PhD program, published more than 100 peer-reviewed publications, and currently he's very actively involved in application of science and technology for rural development, and is really working with grassroots organizations. Last to add, as I am always in touch with his social media, I can see that his institute, under his leadership, ILS is doing very great job in also testing and developing new tools and kits for managing COVID in this country. Dr. Parida, it is indeed a great honor for me and all of us who have joined today to invite you as a guest of honor. And now I request you for your remarks. Over to Dr. Parida, please.
Thank you, Dr. Pathak, for the very elaborate introduction. I think which I'm sure that many of the participants of the seminar and the speakers, we have been interacting for a long time. I think it's so. Let me first thank you, the chairman of the organizing committee, as also. Let me first thank you, the chairman. It's not audible. Is it audible now?
Yes, Dr. Parida, audible.
I think Dr. Datta is saying
yeah.
Not able to hear. But anyway. So let me thank you personally as the chair of the organizing committee, as also Dr. Padmini, the director of ARRW, Dr. Baig, as well as Dr. Mola, for this invitation to join the
Sir, we apologize for interrupting you. Sir, your audio is not clearly audible to us. So if you would you mind if I ask you to come closer to the mic or maybe any other means?
Is it okay now?
I think you can increase the volume, sir.
So could you please check if your computer system's volume is full?
So let me log out and then log in again if it can improve.
Hello.
Is it audible now?
Yes, Dr. Parida, it could be little more, but I think I can clearly hear you. Kutub, is it okay from your end?
We are not able to hear, sir.
So, sir, I would recommend if you have a handy headphone with you, if you could please use that.
Sir, we are not listening also, sir, with the low sound, sir.
No, I put the full sound in the system.
I think he can use earphone.
Yeah.
So, Manas, let me see this. Internal microphone. Is it now more audible or no?
Sir, it's similar.
You just let me see. I'm just calling the. Is it better, Kutabuddin? No, it's the same.
Yes.
Okay.
Now, okay, sir.
Now is it better?
Yes, sir. Yes, sir.
Okay.
Now it is okay.
Right. So I'm sorry for this initial glitch in the technical issues, and that happens when you talk about new technologies. Many times we do really face the problem in taking the technology to the people. But now let me thank Dr. Pathak personally as the chair of the organizing committee, Dr. Beg and Dr. Molla, Dr. Padmini, Dr. Sundaram, for your nice invitation. And when friends like all of you request to participate in a conference or participate in an event, I have had hardly any option to say no to all of you. And I had great pleasure in accepting this. And thank you for considering me. Dr. Datta is there, and so many other dignitaries are there. But I have one difficulty because we're all going to talk to people who have worked on rice and about rice and what has been done on rice and what has to be done on rice. So I think so that's a real challenge because all of us know that what is the problem of rice, because rice, as Dr. Pathak has beautifully explained how it has contributed to food, agriculture, culture, history, heritage, and all these things. So that reminds me in 2004 when the international UN system declared 2004 as the International Year of Rice. And during that period, there was many conferences, many discussions. And that time also it all resolved around the same thing, that rice is our food, rice is our health, rice is the culture, rice is our livelihood. But how to improve the rice productions and make people, the rice farmers particularly, more happy and prosperous in the coming days. So there was a lot of discussion went around that time, and what Dr. Pathak in his slide presented what are the priority areas, whether it is on stress tolerant genotypes, producing more crops from unit area. So all these things was discussed, and it was for over last 20 years it is being discussed. But the question still remains is that why we are talking about improving the rice farming system. So there are something that our research methodology or the research outputs has mostly translated into actionable points where the farmers have started getting benefit. But I think we're still long way away for translating the technologies from the laboratory to the field. I think that is a greater concern which each one of us has been realizing. But at the same time, as Dr. Pathak mentioned, that we also have a lot of challenges whether it is the temperature increase or change in the rainfall pattern or rise in the sea level or increased incidence of weather hazards which is happening in the country. Like for example, in Orissa, for example, the on-seasonal the cyclone which came very recently, that has, I think, affected something about rice productions or rice harvest in something about 120 blocks of the of 8 districts of Odisha. So this unprecedented health weather hazards are also increasing day by day. But the question what has happened is that everybody is concerned about where will the world meet the requirement of the rice production. Because what is slowly happening is the land is moving out of rice. The labor is also moving out of rice because of the mechanization and commercialization. And also there is a huge competition for water for producing whatever the quality of rice. And it is generally believed that if Asia does not produce sufficient rice, the world will go food insecure. And if Asia's production in rice has to improve, so most of the productivity of rice of Asia should come from India. So India has a major role to play if you need to make Asia or the rice-based farming system as mainstay of achieving what you call the food security in the global level. But if you really look at the past, from 1960s or 65 onwards, our annual rate of yield increase in rice has been reported something about 50 to 51 or 52 kgs per hectare. So that is annual growth rate of rice which we have achieved through use of various technologies, whether it is hybrids or whether it is irrigation efficiency, fertilizer application, post-harvest management, and so many are, using a lot of technological inputs, we have been able to achieve what you call the annual rate of yield increase of about 52 kg per hectare per year. But the question is that going to be sustainable? Are we going to maintain those leads, or there are challenges which are going to face? So as Dr. Pathak said that this entire target of this particular conference or the Diamond Jubilee Seminar, which we're talking about how to use next generation technologies and for improving the rice productivity, the rice productivity, prosperity, as well as the resilience of the rice-based farming system. So I'm very confident that it's a very timely initiative, and now with so many brains all around from both India and from abroad, I'm sure at the end of the 2 days conference will come out with very carefully developed strategies or recommendations for how to get it done. But at the same time, even if you really take the next generation technology, whether it is genomics or proteomics or transcriptomics, a lot of work has been done. But it's not that I have been involved in the task force or the expert committee of the rice or the crop improvement in DBT. For example, in rice itself, there are about 8 network coordinated projects, starting with abiotic stress, starting with the salt, drought, marker-assisted breeding or biofortification, which is being supported, and the number of research institutes which are involved in all these 10 to 12 network programs is not less than 60 to 70. 70 institutions are involved. And believe me, these 60 to 70 institutions are based in the country in terms of their expertise, in terms of their experience, and in terms of their track record. But the major question what remains is that, unfortunately, in Indian context, we are all time bound, whether it is a 5-year plan or it is a 3-year project or 2.5-year project, when the money is not also received on time. And then you are expected to deliver everything in time. And what happens is that even if, say, for example, to do a selection of, say, drought tolerant rice, I know Dr. Pathak, if you see that in your CRR itself will have thousands of germplasm of potential drought tolerance. And if somebody has to use the marker-assisted breeding, whatever fast you may go, it is not possible in doing in 3 years' time. But after 3 years, when you start with all enthusiasm in a particular research project, then your project comes to an end. You do not know where to go about it. So I think since most of the participants here today are the policymakers per se, I would suggest to them, instead of doing this into a very small time frame research, I think if you want to use the next generation technology for improving the rice system, I think a concerted effort has to be done with some long-term investment, because imagine investment is a key for achieving success. I mean, I don't know that Dr. A.K. Singh is there or not, but I think he must be there in the program. But look at the single basmati business. The research and development effort, the research and development expenditure on the whole basmati would not have been more than 1,000 crores. I mean, look at the small groups who have been doing it. But what it has given to the country is that something like what Dr. A.K. Singh has been telling, it is something about 53,000 crores of income per year. I mean, that is what is the trade value of basmati. So investment is the key, but rightful investment is also the major factor. I don't want to go into the details of how genomics will help you or how proteomics, that everybody knows it. But I think we need to choose what are the type of technologies we need to do it. My last request to all the eminent panelists here is, how do you ensure the utilization of advanced technology in rice improvement? For example, biotechnology or genetically modified. I mean, rice is such a system with so much of diversity. It's actually a real good experimental system. At least if not all rice varieties can be transformed, at least few of them can be transformed. Some are with high amount of iron, high amount of zinc, or it can be modified using genetic modification technology. And if you go around in Indian laboratories per se, there are so many laboratories who are working with genetic modification technologies for improving rice. But unfortunately, due to a lack of consensus on use of the technologies or use of this advanced biotechnological tools and technologies, we have not been able to see or utilize the full benefit of these things. Now, after the genetic modification technology, it came the genome editing. Everybody said that since genome editing is much simpler, so it will not have any regulatory effect. I know because I sit in the IRAC committees where we support a lot of funding on the rice improvement. I know there are a few technologies using genetic genome editing technologies. The products are fully out and the rice yield is almost 2.5 times more than the compared control things. But I'm not sure whether we are going to see the light of the day for this utilization of these technologies. So I think this Diamond Jubilee Symposium, since it is focusing on the next generation technologies, should come out with a strong recommendation, not only recommendations, but a way forward how you employ advanced molecular breeding technologies for improving the rice productivity and thereby increasing the income, and everything comes onto that, whether you're doubling the farmer's income comes in, or Poshan Abhiyan, or all Atmanirbhar Bharat, all those type of things is key when you have your use of advanced technology. I just gave you an example of the advanced technology application in genomics, but there are advanced technology applications in the use of the water resources or making the byproducts of the thing. Like, for example, when I was working with Swaminathan Research Foundation, in Myanmar, we established a rice biopark, where we have started developing a park where every part, other part than the grain, can be utilized for the value addition of the resources, whether it is energy or whether it is byproducts and all this. So that can also contribute to the livelihood enhancement of this. So it is not important now that we go on doing different things, but I think it is our results should be that we do the things differently so that at the end of the day, we bring in prosperity to the farming communities of our country. And that ultimately brings out a level of satisfaction to the rice workers. And there is nothing more you can do when you have assembled the galaxy of experts in rice. So I think the moment they open their mouth, rice will come out automatically from their mouth, both research and development. So I congratulate all of you. Thank you again. And I'm sure the 2 days consultation or the discussions will go a long way in contributing to enhancing farmers' income through improved rice productivity and production. Thank you very much. Thank you for your invitation.
Thank you very much, sir, for your insightful remarks. And I'm no had to comment on your remarks. So it is well taken by the audience. And as part of the inaugural session, we now request the chief guest and the guest of honor and other dignitaries to virtually release 2 of our publications in these occasions. So I would request Mr. Santosh Shetty to please share the screen. The first one would be abstract book of the symposium, which contains more than 200 abstracts from 4 different scientific themes. And the second one would be the souvenir of the symposium, which contains goodwill message from the Vice President of India and other distinguished personnel from Government of India and Indian Council of Agricultural Research. Thank you. Thank you for releasing these 2 publications. Now the time has come to listen to the inaugural address from the chief guest, Professor Swapan Kumar Datta. Although Professor Swapan Kumar Datta needs no introduction to rice scientist, as a customary, I would like to request Dr. Himanshu Pathak to introduce him to the audience and also request him for his inaugural address.
Thank you, Kutub. Thank you very much. Of course, you are very right. Professor Datta doesn't need any introduction, but I still do it all the time, not for you or not for me, but for our younger colleagues, our students, who may not be aware of all the achievements and the contributions of Professor Datta. Professor Datta is a mentor for many of us. He is a well-known biologist with vast experience in plant biotechnology, agricultural science, nationally as well as globally. As we already mentioned, that he is the founder, vice chancellor of Vishwa Bangla Vishwavidyalaya, located in Bolpur, Santiniketan. And previously, he was the vice chancellor of Vishwabharati Vishwavidyalaya, Santiniketan. And also, he led the crop improvement research in Council, Indian Council of Agriculture Research, as DDG crop for 6 years. Of course, he has received several awards, including prestigious Deputy Distinguished Biotechnology Research Professor, Raspberry Ghosh Chair Professor of University of Calcutta, DAD Fellowship, Visiting Faculty at UC Davis, Senior Scientist at ETH Zurich, Switzerland, Global Rice Crop Leader at International Rice Research Institute, Philippines, and of course, there are many more. He is a fellow of all the renowned academies of science in India and also abroad. He is a fellow of India National Science Academy, INSA, National Academy of Agricultural Sciences, NAS, Indian Academy of Sciences, and again, NASI, National Academy of Sciences in India. He is also a fellow of Third World Academy of Sciences and several others. He has supervised more than 40 PhD students, and his research could really develop genetically improved rice. We talk about golden indica rice, high iron rice, bacterial blight, as well as sheath blight resistant rice, and many others. He has published more than 150 research papers, which appeared in very renowned journals like Nature Science, Nature Genetics, Nature Biotechnology, and many others. He's having an H index of 58, I-10 index of 145, with around 15,000 citations in international literature. He has been named as one among the top 25 Indian scientists from all fields of science, including agriculture, And he was also recognized as top 2% of global scientists in his field, the study which was conducted by Stanford University, USA. Of course, I can go on talking about Professor Datta, but certainly we are all waiting to listen to him. Sir, it is indeed a great honor, a privilege, and also an opportunity to have you as chief guest. Of course, you are not our guest at any point of time. We many times take you as granted. We know that whenever we need you, we can have you. So thank you very much for kindly joining us. And with this, I request you to please make your inaugural address. Thank you very much, sir, once again. Over to Professor Datta, please.
Thank you, and good afternoon to, good morning to Dr. Himanshu Pathak, the President of ARRW, as well as Director NISM, for giving such a illustrated introduction. Thinking now forced me to think that I now became an old man, no longer just working in the bench or in the laboratory, that where all these contributions are made, along with my great number of students across the world. So first of all, congratulations to the President again, Dr. Pathak, and his entire team. And the names are being mentioned in the beginning, for organizing and particularly celebrating the Diamond Jubilee National Symposium on Gen Next techniques for enhancing productivity, particularly resilience of rice farming. And of course, I'm grateful to the organizers for inviting me, for giving this inaugural address today. It's a great pleasure and honor also for me, for such honor that you have given to me and trusted me. And in the morning, I heard Dr. Pathak as well as Dr. Parida, wonderful talk and wonderful introduction also, Dr. Kutub, and that made me feel that Diamond Jubilee celebration is in the right tune and spirit and objective. And also, I'd like to thank Dr. Patini Schwein, the director of NRI, as well as all other scientists, rice scientists from India, as well as abroad who are attending this morning session, as well as will be attending next 2 days symposium on rice. Interestingly, I find the symposium provided a very nice platform for future-ready rice with the next generation technologies, that including some key speakers, Dr. A.K. Singh, Dr. Rajiv Persney, Dr. Himanshu Pathak, Dr. Suresh, Dr. Abhishek Banan, Dr. Prashun Mukherjee, and etc. And of course, follow up the breeding, precision breeding and breeding technologies that include Dr. Ajay Kohli, Dr. Z, and Dr. Holger Gupta. And Holger Gupta actually led when I joined FMI and ETAs, so I knew him also very well. And of course, my classmate and batchmate, Dr. Pramod Agarwal. So some of you may not know, but it is interesting to see that Pramod Agarwal is also a part of this symposium. And some other issues that have been or would be highlighted that includes pest management, and particularly ecology, or chemical ecology and nanotechnology, and of course, genome editing, and finally, livelihood, security, equity, and profitability. The symposium also have two interesting events, that is lightning lectures and also evening lectures. So I think the organizer, I would salute to the organizer. They made this program in such a manner so you never get bored. As Ajay was telling that we are talking to the rice scientists, rice workers, rice consumers, everybody rice. So it can be boring, or it could be nothing new to be added. But I believe that, before I say that, one of my PhD students once told me, he is now a CSIR scientist. She told me, sir, you have done so much on rice and people have done so much. Is there still left something to do rice? Is there any work left that could be done in rice? So I told her, which is more than 20 years back, I told her that it's not today what you do on rice. Even next century, even beyond that, we'll be continuously working on rice and will be continuously needed to work on rice. And rice is such a crop that the present work as well as future technology that would be added or that would be included for rice for work and rice improvement would never end. So a crop of 4 billion people for its use will continue. So, and that's probably this lightning and evening lectures. I'm sure that even some of the people who are not directly involved in rice work, but they work tremendously on other aspects of technological work on different crops. But that way they will bring some new dimension that could be thought or could be used in rice improvement. So once again, this is a great impact or compact program that has been organized, this particular symposium. I'm very delighted to see this entire program, which is very good, very good. Now, first I'd like to start a little bit on one of my favorite areas of my research, that is disease pest management. Now, as we know that host and pathogens evolutionary are co-workers. They're co-workers. They live on each other. And you may kill one, say a pathogen, whether it's a sheet blight or it's a bacterial blight or anything. You name, there are hundreds of diseases in rice. So you name anyone, but that would be only for a short time. So they would come back and would be more virulent and will attack the host in a different manner. So what do you do then? So I remember long back, in fact, I need to say one thing, that in fact, 1976, I published my first rice paper on sheet rot disease of rice. That is something 45 years back. So my experience with rice, and particularly disease, is a long history. Now, long back, say around 2002 or something like that, one of our transgenic rice for sheet blight resistance was evaluated in the US. So my colleague Muthu Krishnan was very excited, called me. So great success has been done because transgenic plants showing resistance to sheet blight. So I said, I was excited listening to him because I was expecting something will happen because the PR protein gene has been incorporated and we developed homozygous rice. And now the material we sent to US, that material might do well and might do that particular thing. And PR protein and all other things have been evaluated already. But then I asked, please show me the field picture. And I'd like to see how they are shows in the field. Then he showed me some pictures and also some video. And then I said that if I'm not very wrong, but control plant also showed some resistance. And control plant didn't show much disease as I expected in sheet blight. And then again, he showed that picture more closely, and then I found that my apprehension was right. That means the control plants also did not show much disease. The result is this cannot be concluded that sheet blight resistance has been worked out, has been developed by genetic engineering, incorporating PR gene. So now why I'm saying this, because after that we have published dozens of research papers on sheet blight, not one with pyramiding more PR genes, as well as PR genes with XA21 and BT genes together. So there are many number of PR genes we pyramided in rice and see the results. My today's conclusion would be on working on disease that this disease you cannot remove forever. The disease will be there, and it's a management strategy need to be developed that incorporating the defense-related genes, including PR proteins, small peptides, etc. That also we have done, and we need to see that disease, okay, not moving much on vertically, so that your harvest of yield can be made, but not hampering or not causing much yield loss. But you cannot get rid of the disease totally. Earlier, we always used to try to get 100% of disease resistant, but it is not possible. But rather, we leave some of the part for the pathogen and take the harvest as much as possible. Now, we recently published a paper, also a review on this aspect in Plant Biotech Journal. The lead author is Dr. Kutub, and I would suggest for some of you might be interested on sheet blight details, you can read that review. It's a very well written review that published in Plant Biotech Journal. So other things what we found while working on it, when we incorporate XA21 gene in rice, and most of the elite cultivars do have XA4, so that means XA4 combined with XA21. It showed enough resistance, but now we know that there are many other genes, XA23 and several more have been incorporated, have been referred, have been cloned, and many researchers working on this field. Now, in this particular context, I must say one thing that Dr. Ning Huang of International Rice Research Institute made an enormous contribution on this, on XA or bacterial blight, and particularly marker-resisted selection breeding, which is followed in India across the different part of India. And it showed a tremendous good results now pyramiding not only bacterial blight, disease, and many other disease-related genes together. Now, with regard to insect pest, definitely may not be, scenario would be different. Here you can, or one can get 100% protection, 95% plus will be good enough, so that that resistance may work very well. Now, interestingly, that we have developed the BT rice and homozygous BT rice that published in Nature Biotech long back in 2000 and 2002 follow-up paper. In China, probably, and it is from the Greenpeace report, that China is consuming this rice, and they have done all regulatory work out. And I think in India, I will talk a little bit on policy matters later part. In India, we're still struggling with the policy, how to move ahead with this sort of transgenic work. But nevertheless, again, like cotton in rice, also pyramiding different genes and driven by the tissue-specific promoters would make a big impact, and which has already been shown in different countries, particularly in China. And also we have seen that in India also it works very well. Now, the second aspect that I would talk a little bit on the precision plant breeding, the next generation of rice breeding that is being focused in this symposium. No matter how much technology we develop, how much technology, new technology comes, conventional breeding would remain the key component of rice breeding. We can never replace conventional or traditional breeding. If we are not good enough in traditional breeding or conventional breeding, no matter how new technologies are emerged or utilized, it would not be befitting. So we have to be very, very sure. We have to combine with our conventional breeding technology along with new technologies together. It cannot go one at a time or alone. Now, we know that at one point, mutation breeding came and gone, but still there are some remnants, useful remnants are there. Transgenic breeding is definitely will play a very key role and is still there very much. And genome editing, that the new technology that has come, and I'm sure that in next 10 years, genome editing would play a very key role, important role in modifications or in changing or reshuffling the genome of rice in a better way. And that would be very much combined with the conventional breeding. Now, one of the things that particularly the Green Revolution that when came, led by Norman Borlaug, and then in rice, which is mastered by Gurdev Singh Ghosh, and a follow-up from many other scientists. Fortunately, in India, we have great number of rice breeders and rice scientists, and next generation young scientists are also coming up. Sundaram is there, even next generation, Kutub is there. So we should be very happy that we have plenty of different generation of young scientists are there. A.K. Singh at Bhushan Institute, IRI is there. So it's great thing. We could feel very confident and comfortable that we have an excellent number of rice breeders and rice scientists are with us to continue a good rice work. Now, definitely one of the components that might come, because land is reducing, the speed breeding. And the speed breeding, particularly the new genetic gains, and this breeding with the DNA chips that is available, Cornell University, Susan McCoos made some wonderful work, and some collaboration is going on with NRI. And I'm sure that in future, this particular area might accelerate the crop improvement in a better way. So as Dr. Kush requires, say, 10 years or longer, or having multiple field evaluation in different countries and different ecosystem of his material that he developed at IRRW. But today, that can be shortened, can be done in the laboratory. And with the genetic marker, one could detect the trait that required or desirable, and dragging genes can be avoided. So that way, this will be much faster in selecting the event, selecting the material, either by conventional breeding or by mutation or genetic engineering or genome editing. At the same time, that material can go to the speed breeding for faster development of homozygous line, and then finally can be released to the farmers. But at this point, one thing I must say, that even we know that there are some quality rice, like it is IR64, or in India there are many, particularly in Basmati and many other varieties that across the country has been developed, including Dr. Esad Das from Odisha that contributed significantly on developing new rice varieties. But still, we haven't got the precision or precise parameters to determine the quality rice. So that we have certain parameters. These are the parameters that should determine that we have developed a quality rice. And the quality rice of particular trait that need to be seen and eventually that can go to the field. This I have been discussing quite sometimes at ICR, and also at IRRW while I was at IRRW, and even IRRW, many IRRW scientists were surprised that we do not have that parameters. But unfortunately, still we don't have it. And we don't know how to make another IR64 because we don't have that parameters clear to us. That's the reason we cannot predictably make another IR64 variety. Same with many other rice variety. We just get even better rice, but still today is a matter of luck and matter of hard work. But we need to develop certain parameters, certain marker that could give a clear direction to develop a high quality rice. And that would make our life very easy. And that one thing has been now contributed very much in Indian rice breeding, that is shortening the plant height and adding with the multiple tillers that with the reducing the apical dominance of the plant. That was the key architect of the Green Revolution. And Dr. Ekeshing at Delhi, he has made a few of those material now ready, and more to come that I'm sure in other centers as well. Now, a bit of climate change. I really don't need to talk much because there are two eminent, very eminent scientists around. One is Himanshu Pathak, as well as Dr. Agarwal, Pramod Agarwal. But to me, what I feel that climate change, again, like a plant breeding or rice breeding, is a continuous process. And will change, will keep on changing, and more rapidly probably in future. And that's the reason the new technology would help you to monitor what are the changes taking place and what are the things need to be done. And that way, no matter what climate change is going on, but I think with the better technology and management would be able to get the climate resilient crop. And I remember one of the Indian Science Congress, probably at Chennai. I think APJ Abdul Kalam, our president, former president, he was giving an evening lecture. For each subject, for agriculture, he just mentioned that we need to develop crop climate independent crop we have to develop. So that was something reminds me, although in rice, we have made tremendous contributions, particularly now rice can be grown 2 times a year, even 3 times a year is being grown. And I'm sure the days will be coming, we can grow rice anytime and every time. And now we have to adapt that sort of strategy, whether that would be good for environment or good for our profitability, etc. That's a different thing, but I'm sure these are the things would be coming in future. Now, the last part of this livelihood and security, food security, nutrition, etc., and also the policy. I think these are the parts is very tricky because science is straightforward. We succeed or we fail. But when we talk about food security, and also the equity and as well as the policy. And I think Ajay just mentioned a little bit of policy. He just left it for others to elaborate on it. And I think in the policy matters where we are basically failing in many aspects. Fortunately, our rice scientists, the rice across the country for a century. They have done tremendous work, significant contributions they made it, and that country is today, we can be proud of it. Basmati, one example, is mentioned, and there are many others also can be mentioned. That way, I think agriculture is one sector country should be proud, and rice, of course, the #1 crop, not only in the world, but also for India. So in that way, we can feel very happy about that. But as NRI developed high protein rice, the golden rice with the carotenoids rich rice, high iron rice, and low phytate rice, and many others have been developed. But it did not move further. And where the country very much required those nutrition-rich rice, that combining protein, iron, and vitamin A or carotenoids together, or low phytate, these are very much needed, but we are not moving ahead, accepting publication of our science. Golden rice now being already evaluated in Bangladesh and Philippines, and many countries now already released it. They have released it. They are allowed to release it, and but we haven't taken any decision on that. Even for genome editing, which is now today is a particular science, a feel-good science, I would say, a feel-good science that across the world they are continuously working and modifying it. The change is going on for good reasons, and several products now already have come in the country. But we are simply struggling. What should be our policy on golden rice? On genome editing. We have been writing many of the requests and to the government level, and so I would request the organizers also from this meeting, as this meeting focusing on technologies. So with the considering the importance and significance of the new technologies to be adopted, at the same time, they must also make a specific recommendation for genome editing technologies, so that should be immediately adopted. And not only that, particularly all these regulatory aspects need to be eased, so that this material can move fast and can be utilized in the country. So these are the few, definitely the things that what I thought I would focus today. And there are many aspects of rice can be talked about it. But one good thing is that India is now at least 10–15% population rich enough they can afford to purchase any good, including good quality rice at any price. So that we must ensure that not only basmati rice with aroma, or non-basmati or other rice, or even ready-to-cook rice in 2 minutes microwave rice, this kind of rice must be developed, and this should be given encouragement, so that the future dimension of rice use could be more easier and more sort of desirable. So the designer rice for tomorrow should be as such, it not only provide high productivity for general public, but at the same time, quality rice for the people who can afford to purchase. If it's expensive, even the expenses for that particular rice, and that would also will fetch higher price, and that higher price would benefit to the farmers. The farm community also would benefit from those particular quality rice production, because that would generate more income. So I think in a society like India, as a heterogeneous society, we must ensure that, first of all, freedom of science need to be there. Policy need to be more user-friendly, and the policy must encourage science to move on. At the same time, we must produce different kinds of rice for different sections, for different sectors, for different types of people, so that across the country, with the desirable taste and also a type that our rice is available. And that way, India, not just as an exporting country today on rice, but at the same time, would be dominating in producing designer rice, and it will dominate in rice science, rice research, rice productions, and also rice market. So this is an opportunity for us, and this opportunity we must avail so that we can reach to our goal. With that, again, once again, thank you very much for all our rice scientists in the country that made a tremendous, significant contribution in rice research, as well as organizers, and particularly Dr. Pathak and Dr. Beg, Dr. Shayan, Dr. Sundaram, also Kudu, all other people that who made this meeting feasible and possible in this difficult time of COVID situation. But I'm sure it will be great success of this meeting of 2 days deliberations, and I'm sure this will go on with a much more in a bigger way in future. So thank you and congratulations of celebrating the Diamond Jubilee of National Symposium of ARRW. Thank you very much.
Thank you very much, sir. With that, immense gratitude being expressed to our chief guest and guest of honor, we have now come to the end of the inaugural session of ARRW Golden Jubilee Symposium. It's time for a formal vote of thanks from the secretary, ARRW, and one of the organizing secretaries of the symposium, Dr. M.J. Beg. Sir, please for your vote of thanks.
Thank you, Kutu. Good morning to everybody. Respected today's chief guest, Dr. S.K. Datta, former DDG CS, ICAR New Delhi, and Vice Chancellor, Vishwa Bangla Vishwavidyalaya, Bholpur, West Bengal. Today's guest of honor, Padma Shri Dr. Ajay Kumar Parida, Director, Institute of Life Science, Bhubaneswar, Dr. Himanshu Pathak, President, ARRW, and Director, ICAR Niazam, Baramati, Dr. Padmini Swami, Director, NRRI, and Dr. R.M. Sundaram, Director, IIRR, and Vice President, ARRW, Dr. A.K. Nayak, Head Crop Production Division, ICAR NRRI, and convener of the symposium, both my associate organizing secretaries, Dr. Kutub and Dr. Totan Adak, dignitaries on board, all the participants who have joined this symposium across the country, ladies and gentlemen. It is indeed a great pleasure to propose a vote of thanks on behalf of the association, NRRI, and my personal behalf. I extend my sincere gratitude to Dr. Swapan Kumar Datta, former DDG Crop Science, ICAR New Delhi, and Vice Chancellor Vishwa Bangla Vishwavidyalaya, Bholpur, West Bengal, for accepting our invitation and grace this occasion, this inaugural function as chief guest. Thank you, sir. I extend my sincere thankful to Padma Shri Ajay Kumar Parida, Padma Shri Dr. Ajay Kumar Parida, Director, Institute of Life Science, Bhubaneswar, for gracing the occasion as guest of honor. Thank you, sir. My sincere thanks for Dr. Himanshu Pathak, President, ARRW, and Director, Niazam, for his meticulous guidance in success of this symposium. I am highly thankful to Dr. Padmini Swami, Director, NRRI, for the wholeheartedly support in organizing this symposium. I am thankful to Dr. R.M. Sundaram, Director, IIRR, and Vice President of ARRW, for his wholeheartedly support in organizing this symposium. Thanks goes to Dr. A.K. Nayak, Convener and Chairman of Organizing Committee, and all the members of the Organizing Committee for the active involvement in organizing this function. Thanks goes to both of my fellow organizing secretaries, Dr. Totan Adak and Dr. Kutubuddin Ali Mullah, for sharing the responsibility in organizing this symposium. Special thanks for Sri Santosh Kumar Shetty and Sri Sunil Kumar Sinha for their active involvement in designing the link for different sessions and providing the inputs for organizing this symposium through virtual mode. I express my sincere thanks to all the dignitaries who have accepted our invitation and joined this inaugural function through virtual mode. Thanks goes to all the participants who have joined the symposium through virtual mode. Thanks to all those who are directly or indirectly involved in success of the symposium. Thanks one and all. Thank you. Over to Kutub.
Okay, sir. Thank you very much. Try to start, I believe, and with the direction received from the chief guest and the guest of honor, it could not have been better. Thank you all for your participation, ladies and gentlemen. I believe you would enjoy a great scientific deliberation, and I do hope you have a productive and fulfilling 2 days ahead. But before we end this inaugural session, the organizers have a few very important announcements to make, which is a little bit changes in the program. So please take note of it. Number one, as per the program distributed to you, this session is supposed to be followed by the plenary lecture by Dr. T. Mohapatra, Director General ICAR. But due to some unavoidable circumstances and a time conflict with the program from Prime Minister Office, the session for plenary lecture is postponed. And the same plenary lecture will be delivered by the Honorable DG tomorrow at sharp 12:30 p.m. 17th December tomorrow at sharp 12:30 p.m. We will be sharing a separate link for the plenary lecture very soon to your email. So keep checking your inbox. Number two, as a result of this change, the valedictory session is rescheduled on 17th at 5 p.m. Valedictory session on 17th at 5 p.m. Number three, we would assemble back today at 1 p.m. for an interesting panel discussion on the theme, Preparing Future Ready RISE with Next Gen Technologies. We got eminent panelists, and the discussion will be chaired by Dr. T.R. Sharma, DDG CS, ICAR. I repeat, exactly 1 p.m. we will start our panel discussion today. Thank you very much all for your time and active participation. Back to you, sir. Pathak, sir.
Thank you very much, Kutub. Of course, with this, we conclude our inaugural session. And as already mentioned, we will be joining back at 1 p.m. today, 1 p.m. sharp, to have our panel discussion. And you are really going to have an interesting panel discussion with very eminent persons who are going to deliberate very briefly, of course, in a very interactive mode on the next gen technologies for crop improvement, protection, climate change, and also livelihood, gender, and several other issues. So with this, we conclude it. As you all know, that now all of us have to join for our Honorable Prime Minister's address to the nation, particularly to the farming community and agricultural scientists, which is going to start at 11 a.m. So let us join there and then reassemble here at 1 p.m. Thank you very much, all of you. Thank you, Kutub.
Thank you. Okay. So this same link will be active for the panel discussion. The same link will work.
खत्म हो गया कौन है
ஆமா இந்த காலத்துல யாரும் பேசலாம் சொசைட்டி தெரியும் வெளியிருந்து வரது பேச முடியல வெளியிருந்து வராங்க
वीडियो स्टॉप वीडियो
Good afternoon, ma'am.
Good afternoon.
How are you?
Fine. Actually, we had that Prime Minister program. It is still going on.
I
And we had to go to our auditorium.
Oh, I see. Okay, okay. Hi, Amtul.
Yeah. So, thank you very much confirming.
Thank you. Yeah, yeah.
We'll start within 2 minutes, I think.
No worries. Yeah.
Sir Sundaram has joined. Sir, shall we start?
Sir, I have joined, sir.
I think Dr. Sharma has also joined.
बोर्ड में
Good.
Please check if he has joined on some other name. He just called me.
You need not worry. Yeah. If it is below 15%, that's all, Dr. Satyendra.
Hi, Dr. Patak. Hi.
Hello, madam. How are you?
I'm good, thanks. Hey, Dr. Baig.
Hi.
How are you?
Fine.
Long time.
So, sir, I don't see Dr. Sharma has joined.
Yeah. Sorry, there was a phone call in between.
Yes. Okay, I shall call him. He only called me that he has joined.
Oh, yes, sir. So he is there. So I can see him in the audience.
Kutub, Dr. Sharma has already joined.
Yeah, okay. So should I start now?
Yes.
One more thing, I think, let's see whether Dr. AK Singh has joined.
Dr. AK Singh बोर्ड में नहीं दिख रहा है.
Dr. Sundaram. Dr. Sundaram, any information?
Not exactly, sir. Should I contact him, sir?
Okay, what I shall do is, I think Dr. Sharma has already joined, so let us start it. I shall call him. I shall call Dr. AK Singh, and probably even if he's late, so probably we can have his presentation maybe at the end.
Yes, sir.
If he's taking a few more minutes. Okay, Dr. Sharma, so should we start now?
Yes, good morning to all.
Yes, good morning.
Good morning.
Okay, Dr. Sundaram, over to you.
Yes, sir.
Okay, sir. Welcome back, ladies and gentlemen, to the ARRW Golden Jubilee Symposium. Respected Dr. T.R. Sharma, DDG Crop Science, Indian Council of Agricultural Research, Dr. Padmini Shwai, Director NRRI, Dr. R.M. Sundaram, Director IIRR, and all the eminent panelists and all the participants. Now we will have a scintillating panel discussion on preparing future-ready rice with next-gen technologies. I believe you already got an sense from the program schedule that you received that the organizers, especially the convener and organizing committee chairman, Dr. A.K. Nayak, organizing secretaries, Dr. Beg and Dr. Totunadak, have worked day and night with full of their heart to figure out the best possible things to fit in these 2 days for you. And the enormous guidance received from President ARRW, Dr. Himanshu Pathak, Director NRRI and Director IIRR made our job easy and smooth. So this panel discussion is their brainchild. And coming to the exciting panel discussion, this panel discussion would be on the theme, preparing future-ready rice with next-gen technologies. And this would be chaired by our Honorable DDG Crop Science, Dr. T.R. Sharma. And the two conveners we have, Dr. Padmini Shwai, Director NRRI, and Dr. R.M. Sundaram, who is the Vice President of ARRW and also the Director of IIRR. And we have 5 panelists, Dr. A.K. Singh, Director IRI, Dr. Ranjita Pushkur from ERI, Dr. Himanshu Pathak, Director NIASM, Dr. Prashan Mukherjee from BARC, Mumbai, Dr. Abhishek Barman from General Aeronautics Limited, Bengaluru. Sir, now I would hand over the floor to Dr. Padmini Shwai and Dr. Sundaram sir and request them to take forward the panel discussion as per the schedule. Over to you, sir and madam.
Thank you, Dr. Kutu. Without wasting much time, I think we'll start the program, and it is my pleasure to introduce Professor T.R. Sharma sir. Professor Tilak Raj Sharma, Deputy Director General Crop Science, Indian Council of Agriculture Research. He is a well-known plant molecular biologist. He is presently leading the Indian agriculture sector as DDG Crop Science, Government of India. Earlier, he contributed in the establishment and development of several prominent Indian institutes like National Agri-Food Biotechnology Institute, Mohali, as Executive Director, Center of Innovative and Applied Bioprocessing as Chief Executive Director, National Institute for Plant Biotechnology as Project Director, and Indian Institute of Agriculture Biotechnology as OST. He obtained postdoctoral training on genome analysis and bioinformatics at University of Alberta, Canada, and Cold Spring Harbor Laboratory, New York, USA, and PhD from HPKVV Palampur in 1990. For his outstanding research contributions, Dr. Sharma has been awarded various awards like University Gold Medal and Certificate Honor in PhD, Young Scientist Award, NAS, ICAR Young Scientist Award, Crop Science, Professor Umakan Sinha Memorial Award. Many awards he has got, out of which many important awards I am telling that DBT National Bioscience Award for Career Development, Vasrik Award in 2011, NAS Recognition Award in 2008, Rafi Ahmad Kidwai Award, NASI Reliance Industries Platinum Jubilee Award, JC Bose National Fellowship also, and he is the Professor MGK Menon Lecture Award, Vishan Singh Samudra Memorial Award. All these memorial awards also he got. He is the fellow of all 4 national academies, that is Indian National Science Academy, Indian Academy of Sciences, National Academy of Science, and National Academy of Agriculture Sciences. He is the major research, his major research interests are in the areas of genomics and plant disease resistance. He has contributed extensively to the improvement of rice for over 30 years and cloned a new rice blast resistant gene PI54, which has been deployed in more than 40 rice varieties in India and abroad. He has been associated with the decoding complete genome of rice, tomato, pigeon pea, jute, mango, tea, and many plant pathogens. Dr. Sharma has guided 25 PhD students in agriculture biotechnology. He has published more than 180 research papers with citation index of more than 12,000. His H index is 51 and I-10 index is 137. He has 4 patents to his credit, and he is associated in the development of 3 blast resistance rice varieties, Pusa 1637, HPR 2880, and Pusa Sambhava. Sir, I welcome you to this panel discussion for preparing future ready rice with next gen technologies, and as the chairman. And in this program, we are having 5 panelists: Dr. A.K. Singh, Dr. Ranjita Kapoor, Dr. Himanshu Pathak, Dr. Prasun Mukherjee, and Dr. Abhishek Barman. If allowed, Dr. A.K. Singh will be joining shortly. Can I?
Madam, he has already joined.
I am there. I am there.
Sir,
I am
sir,
there.
sir, sorry, sir, sir. Sir.
No, it's okay. Yeah.
Sorry, yes, sir. Yes, sir. I also feel proud to introduce you, sir. So, Dr. Ashok Kumar Singh is the present director of Indian Agriculture Research Institute, IRA, New Delhi. He did graduation and post-graduation in plant genetics and plant breeding. Sir, anything? From Banaras Hindu University, Varanasi, and PhD in genetics from Indian Agriculture Research Institute.
15 August. Again,
Dr. Salgotra, can you please mute yourself?
Dr. Singh joined as Director ICAR IRA New Delhi in 18th January 2020. Earlier, he worked as Joint Director in charge and Head Division of Genetics IRA New Delhi. Dr. Singh has been actively involved in Basmati rice improvement for last 2.5 decades. He is associated with development of 13 rice varieties, including 5 mass derivative Basmati varieties. These improved Basmati varieties occupied about 1.8 million hectare area, bringing prosperity to millions of Basmati farmers while earning 25,000 crores of foreign exchange annually. He has been associated with the teaching of 3 postgraduate courses in genetics of last 20 years and guided 15 PhD and 5 MSc students, with 3 of them winning the prestigious ICAR Jawaharlal Nehru Award of 7, and 7 of them awarded with IRA merit medals. Dr. Singh has published 120 peer-reviewed research publications in rice genetics, molecular breeding, and grain quality. He co-authored a book entitled Marker-Assisted Plant Breeding Principles and Practices, published by Springer. Dr. Singh pioneered the public-private partnership model for commercialization of first superfine grain aromatic rice hybrid Pusa RH10 and several Basmati rice varieties, generating revenue of more than 2 crore. He has served as an expert member in DBT, in APEDA, RAC, ICAR NRRI, ICAR NBPGR, ICAR IIRR, and SAC NIPGR NABI. He has been awarded with prestigious ICAR
You can keep it brief. We can devote the time for discussion.
Okay, sir. Okay, sir.
Yeah.
Also, he has got the ICAR Bharat Ratna Dr. C. Subramaniam Award during 2013. Along with this, he has also many outstanding awards like Borlog Award and Om Prakash Basin Award. He is a fellow of National Science Academy, National Academy of Agriculture Sciences, and Indian Society of Genetics and Plant Breeding. Again, I have the opportunity to introduce Dr. Ranjita Puskar. Dr. Ranjita Puskar leads the research program on gender and livelihood at International Rice Research Institute, IRRI, and is IRRI representative to India. She has been with the consultative group of International Agriculture Research, CGIAR, since 2002, working at International Water Management Institute, International Livestock Research Institute, and IRRI. Her work focuses on generating knowledge, learning, and evidence that can translate into technical and institutional innovation and lead to more equitable outcome for women and other vulnerable social groups engaged in agriculture. She also leads the evidence module on the CGIAR gender platform. The evidence module of the gender platform aims to deliver new evidence to fill key gaps in the gender and food system domain, to inform research, development, practice, and policy, to facilitate design and implementation of solutions and trajectories to reduce gender inequalities. In her sole role as IRRI's representative to India, she engaged with government, non-government, civil society, private sector, and investor to garner support for its R&D program and policy engagement in India to contribute to agriculture sector development. Thank you, sir. I think Dr. Sundaram will introduce other three dignitaries who are panelists in this discussion. Dr. Sundaram, please.
Yeah. Thank you, Dr. Padmini. With the kind permission of Chair, let me give a brief introduction for Dr. Himanshu Pathak, who is one of our panelists. Dr. Himanshu Pathak is presently Director of ICAR, National Institute of Abiotic Stress Management, Baramati, Maharashtra. He obtained MSc and PhD in Soil Science and Agricultural Chemistry from Indian Agricultural Research Institute, New Delhi. Previously, he served as Director of ICAR, National Rice Research Institute, Cuttack, Odisha, and also as Principal Scientist and Professor, Indian Agricultural Research Institute, New Delhi. And he also was co-facilitator, Rice Wheat Consortium, New Delhi, and visiting scientist of Institute of Meteorology and Climate Research, Germany, and University of Sussex, United Kingdom. His research includes soil science, climate change, and abiotic stress management. Dr. Pathak has published more than 200 research papers and has recorded a Hutch index of 66 and ITEN index of 188 and more than 17,000 citations, which is a unique achievement. He was the lead author of IPCC's 5th assessment report and refinement to the IPCC guidelines for national greenhouse gas inventories. He is a fellow of Indian National Science Academy, National Science Academy of India, National Academy of Agricultural Sciences, and Humboldt Foundation, and also a winner of the prestigious Rafi Ahmad Kidwai Award of ICAR. Dr. Pathak has been included in the Reuters top 1,000 global climate change scientists in the year 2020 and 2021 by a study carried out by Stanford University. So thank you, Dr. Pathak, for being here, sir. Now let's take this opportunity to introduce another eminent personality, Dr. Prasoon Kumar Mukherjee. Dr. Mukherjee currently holds the position of Scientific Officer G at the Baba Atomic Research Center, Mumbai. He obtained PhD in plant pathology in 1991 from GB Pant University of Agriculture and Technology, and has been a visiting scientist and also scholar at the Israel Institute of Technology, Haifa, and Texas A&M University, College Station. Dr. Mukherjee has been working on the biofungicides, Trichoderma species, for more than 20 years and has made seminal contributions in genetics and genomics of these fungi, especially in the area of signal transduction and secondary metabolism. He has also developed novel mass multiplication method for which a patent has been filed and the technology has been transferred to a private entrepreneur. He has published more than 50 high-impact, outstanding research papers and review articles in refereed journals, many of which are very widely cited. He has won several awards for his contribution and is an elected fellow of the National Academy of Sciences, India. To name, some of the awards are Dr. K.S. Krishnan DAE Research Fellowship, Professor M.J. Narasimhan Academic Merit Award, J.F. Dastur Award, Boys Case Fellowship, Government of Vasvik Award for Government of India, and also several other awards like Fulbright Nehru Academic and Professional Excellence Fellowship and others. Sir, I welcome you for this panel discussion. And our last panelist, but not the least, is Dr. Abhishek Barman, who is the founder and CEO of General Aeronautics Private Limited. He believes in solving agricultural problems with advancement in sustainable agri-tech. Coming from a strong aviation background, he is passionate about exploring drone-based solutions towards sustainable agriculture. He has close to 2 decades of experience in the field of aircraft design and project management. Prior to starting General Aeronautics Private Limited, he has worked in Aeronautical Development Agency, which is under Ministry of Defense, for 17 years and was Deputy Project Director and Head of Systems Engineering for the prestigious Light Combat Aircraft project called Tejas in his last role as at ADA. He was also spearheading configuration design of regional transport aircraft at National Aeronautic or Aerospace Laboratories. Sir, we welcome you for this panel discussion. Thank you, sir. Now request Chairman to take over, sir.
Good afternoon. Am I audible?
Yes, sir. Yes, sir.
Okay. Thank you very much, Dr. Sundaram and Dr. Padmini. We have to start now the actual session now. And if I see watch in front of me, we have already consumed 15 minutes. And you know the panelists, which we have 5 panelists. I would first like to congratulate the organizers for putting up a panel of such a distinguished scientists, and they are really expert in their own areas. And you have just now listened to Dr. Padmini and Dr. Sundaram about their contribution in rice research. So we are going to have a very wonderful discussion today, and would be having very interesting points which probably come out of this discussion. As this whole session is structured, first of all, we would be having a first round of discussion in which each panelist will speak for 3 minutes about the area in which they want to talk. And then after that, again, second and third round, in which there will be no discussion and no interjection. So that's what the panel has been structured. And the second round, we would be having specific presentations by our panelists, and I'm sure that they are not going to use slides, otherwise we may waste time when this panel discussion would be without slide. It will be more interactive, I would say. And then third round, we can have a open discussion for 5 to 10 minutes. So in total, we have now 42 minutes with us, and I'm sure that we will try to complete our whole job within these 42 minutes assigned to us. So the topic which we are going to discuss today are very, very interesting, and I would like to see the title, which has also been very, what you say, future looking, preparing future ready rice with next-gen technologies. So we all know that the science of rice is changing very fast as compared to other crops. It's just like moving neck to neck with Arabidopsis, being a model species for studying all molecular basis of interaction of all biological systems. This crop has really attracted a lot of attention world over. And we have now seen not only the basics which we are going to discuss today, but also its applied aspects, which are related to genomic assisted breeding, marker assisted selection, genome-wide association mapping, speed breeding, and also issues related to global climate change, which Dr. Pathak would be throwing some light on it, particularly on net zero emission by 2070. And besides that, I'm really happy to see that, which is the topic of my choice, that we are going to have one interaction with Dr. Prasun Mukherjee on non-host resistance, which is a very well-studied area now in many of the crop system, but its practical application has still been limited, non-host resistance. And then the interesting topic which we would be having by Dr. Ranjita is on what you call institutional and societal innovation and role of women, particularly in this particular crop. And we all know that the latest technologies are smart farming, which Dr. Abhishek is going to discuss. And I'm expecting that he will throw a lot of light on artificial intelligence, IoT, and also sensor-based technologies. So we have so many technologies around us which are being discussed now, our experts. And I will open the floor with the discussion from Dr. A.K. Singh, who is presently the director of Indian Agriculture Research Institute and a renowned rice scientist. Dr. A.K. Singh, please.
Thank you, Chairman, sir. It's my pleasure to participate in this panel discussion on the topic preparing future-ready rice with next-generation technology. India has done pretty well in terms of rice production with 121 million tons of total production, and being number one in export with 18 million tons of total export, including 13 million tons of non-basmati and 5 billion tons roughly basmati rice with a value of 63,000 crores. It's a remarkable achievement. But the future varieties have to address the resource use efficiency and also the major component which requires addressing the enriched varieties with nutrition, be it iron, zinc, protein, antioxidants, diabetic rice with low glycemic index. Then having varieties with higher productivity. And the third important point is enhance input use efficiency. So when we talk of input use efficiency with respect to fertilizer use, water use, pesticide use in form of nanomolecules, and then the use of herbicide tolerance in rice for promoting cultivation under direct seeded condition. Now, in addition to that, the focus on consumer preference and export market. Our export market, we are number one, no doubt about it. We have to sustain it. This year we had this opportunity because of COVID, that many countries wanted to have the food security, and therefore there was sudden demand for rice. And fortunately, we had 40 million tons plus in our godown while supplying to people in country. We were also able to spare for the purpose of export, and we reached the figure of 18 million tons. But this sustenance of export is important by promoting niche areas. There are a number of specialty rices in different states which are protected under geographical indication. Excellent grain and cooking quality and consumer preference, but unfortunately these have not reached the international markets. So there is a need to promote the cultivation of these specialty rices in organized way by developing complete value chain. Then we also need to have a paradigm shift from release and hope to realize and release. Now, this I am saying is that many times the varieties that we develop, it takes time, 2 to 3 years, 4 years, to know actually whether the variety is really getting adopted by the farmers or not. So we release and then we hope it for its wider adaptation. And sometimes it happens, sometimes it doesn't happen. And this we can see in context of, total so far 1,436 varieties have been released. And out of these varieties, only 323 varieties are in the seed chain as per 2022 breeder seed indent. And further, if we see out of the total breeder seed indent of 3,636 quintal for these 323 varieties, the top 20 varieties account for 40% of total indent. So only 20 varieties, they occupy 40% of the indent, and 198 out of 323 varieties are less than 5 quintals. Now, if we see the total breeder seed indent, 464 quintal breeder seed indent is coming from varieties released after 2016 only, and the rest 3,000 quintal is coming from the varieties which have been released prior to 2016, and that means old is gold is still. Now we need to really critically get into the reasons why this is not happening, why the adoption rate is slow, and we need to address these important issues. And that's why I said realize and release. We must do extensive assessment, evaluation, and then we go for, I think, release of the varieties. This will be the prime requirement. So in the first round, I think I will limit my address to this much, and then next round will come to technology section. Thank you very much.
Thank you, Dr. Singh, and very important points you have touched upon. So we will continue with our discussion on these points later. Now I will invite Dr. Ranjita Pushkar for her initial remarks and introductory comments.
Thank you, Doctor. Yeah, thanks, Dr. Sharma. Dr. Sharma, esteemed fellow panelists, everyone attending this session, good afternoon, and thanks for having me here. Very delighted to have this opportunity to share some thoughts on this topic. And Dr. Singh actually very nicely set the scene for what I was going to say today. We're talking about technologies. What are technologies? They're enablers of solutions. that we are seeking to address the development challenges. They are not solutions themselves. So they are the means to an end, and that end is development impact. What is important is not how many technologies we develop, it is what impact they are able to make. If you look at it, the biggest challenges that are facing us today are climate change. And it's not something that we are anticipating in future. It's happening already. Malnutrition, poverty, inequalities are rising very rapidly. And then data also shows that many of our marginal rice growing areas have high levels of poverty. And COVID, since last year, highlighted how fragile our food systems are and how shocks like this can reverse all the gains that we have made in food and nutrition security and poverty, etc. I mean, as crop researchers, we've always looked at yield as a proxy for production. And we pride ourselves, rightly so, for producing enough food for everyone. But we also know that millions cannot afford healthy diets today. It's 3 billion globally and many million in India itself. And COVID has also proven that the kind of income shocks that come with it for a large section of the people can actually make even energy adequate diets unaffordable. Forget the healthy diets that we are talking about. So we should be looking at nutritional yield rather than caloric yield and equitable access to food. And Dr. Singh has already alluded to some of that. So we need to ensure that the technologies we develop should make our food systems and the livelihoods of the people who are depending on them resilient. We need technologies that work for low-income smallholder farmers. There are a number of technologies we can list that we need to address these issues. Stress-tolerant varieties, biotic, abiotic, and these are only going to increase with the climate change that we are seeing. We need nutritious and high-yielding varieties in that context. We need resource use efficiency. We need mechanization. We need natural farming. We need geospatial and digital technologies. Food processing, value addition, something we probably haven't given much thought to, and technologies to address food losses. And I think that is something that, again, needs much, much more attention than what we have given so far. And the point I want to highlight is that technologies are not neutral. They do not benefit everyone equally. They differently impact different socioeconomic groups of people. There are a number of factors, including class, caste, gender, location, in a complex society like ours, which determine who has access to technologies and is able to use them effectively. Evidence shows, and Dr. Singh has established with very concrete examples about the varieties, there are a number of very useful technologies, but they don't get taken up because they don't suit the socioeconomic, cultural, or institutional conditions the potential users face. And we are increasingly, therefore, talking about bundling, bringing together social and technical innovations. We hardly talk about social technologies, institutional innovations, so that we can have the impact through these next-gen technologies that we develop. So what's important, speaking as researchers, is that we do include social scientists in teams that engage in technology development. They shouldn't be an afterthought when the technologies are ready. And as we said, we've released it and then hope these social scientists can make that happen. We need a thorough analysis before investing in development of new technologies. Who are they meant for? What are the expected benefits? What are the challenges you can anticipate in the uptake? Social and economic suitability of technologies are as important, if not more, as biophysical suitability in a foodscape. We talk about foodscapes now, not landscapes anymore. And given all the challenges that we are facing with rice today, it's also important that we take a systems view and we look at these commodities and technologies that we are working on as a part of a complex portfolio of livelihoods which rural populations pursue. So we need to create diversity in our systems to create multiple pathways for absorbing the different shocks that we anticipate. And when I say diversification, it's not just about crop diversification. We need to promote a diverse mix of products, supply chains, and operating in a range of markets, diverse markets as well.
Dr. Ranjita, can you wind up now?
Yes. So, and then there are a number of other innovations that we could talk about. So I'll come back to that in my next round. Thank you.
Thank you, Dr. Ranjita. And you have really touched upon a very important point, how social scientists can be associated with the concept of any project or program so that we can see its societal and other impacts in the society. So with these words now, I would like to request Dr. Pathak, who is with us now. Dr. Pathak, please.
Thank you, Honorable Chair, very distinguished panelists and my distinguished colleagues, delegates. As you know that climate change is a reality. The IPCC in its latest report, published just this year only, has emphatically said that it is widespread, rapid, and intensifying. We also all the time say that either we stop climate change, otherwise climate change will stop us. So this is the time to say enough. Enough is enough, and this is far and no further. Now, in this background, all of you know, in the very recently concluded COP, Conference of Parties 26 meeting in Glasgow, our Honorable Prime Minister has made 5 big commitments from India. We call them Panchamrit. And the most important of the commitments is attaining net zero emission or carbon neutrality for the whole country by 2070. And therefore, the question which has been given to me is very, very pertinent. Can Indian agriculture become net zero or carbon neutral? And if it is so, then what are the technologies and how we will be able to do that? But before, Chairman Sir, I answer this question, which I shall do in my next round, let me give you some numbers of how much GHG we emit from Indian agriculture. You know, currently the whole country, including all the sectors of economy, emit around 2.8 billion tons of carbon dioxide equivalent. Equivalent means including methane, nitrous oxide, and everything. Energy sector contributes 75% of it, followed by, of course, agriculture, 14%, industry, 8%, and waste, 3%. Indian agriculture, putting livestock, crop, everything together, emit 408. So let us say 400 million tons of carbon dioxide equivalent. 55% of this emission comes from the enteric fermentation. 19% comes from soil, mostly nitrous oxide emission from fertilizer as well as manure. And 17% from rice, mostly methane, and 7% from manure, and so on. So therefore, crop sector, if we just for our today's discussion, it is responsible for 40% of India's emission. And of course, rice is one, as I said, it emits around 17% of that one. Just for our audience to remember 1 or 2 very easy numbers, conventionally grown lowland rice fields of our country, lowland continuously summer rice fields emits around 80 to 100 kg methane for the whole season, and around 1 kg, 0.7 to 0.8 to be precise, of nitrous oxide per hectare, with a total global warming potential of around, say, 2.1 to 2.3 tons per hectare. Of course, rice is followed by sugarcane, potato, and many other crops where we apply more amount of manure and fertilizer. One good thing or good development in India in agriculture, as Dr. Singh also mentioned about, that the food production, particularly rice production, is increasing over the years. Very true. But per unit emission of greenhouse gases, emission per hectare is also increasing. But the good point is, if we calculate the same thing in terms of emission per unit production, so how much we are emitting to produce 1 ton of food grain, say for example rice, that value is going down. And in the last 4 decades, that value has gone down by around 20%. Even then, emission is quite significant. And if we have to attain net zero, of course, 2070 is a long time. But what I argue that in the crop sector, for today's discussion, I shall not include animal sector, for crop sector, we will be in a position to attain carbon neutrality or net zero emission, and we need not wait up to 2070. We can do it by even 2040. How? Which technologies will be useful for this? That I shall discuss in my next round, sir. Thank you very much. Thank you.
Thank you, Dr. Pathak. Very interesting points you have raised. And one of the important points which immediately picked up attracted me to this particular discussion is that we will attain carbon neutrality even before 2070. And now probably next round, you will tell us how we are going to achieve that. Thank you very much. And now coming to our next panelist, Dr. Pasun Mukherjee, please, from BRC Bombay. Dr. Pasun?
Yeah. Can you hear me?
Yeah, please go ahead.
Yeah. Okay. Yeah, thank you, Dr. Sharma, and I'm very happy to see Dr. Pathak, Dr. Raman, and Dr. A.K. Singh. Actually, when I was invited, I was a bit reluctant to accept because it's not my area of research as such, rice research, as well as I specialize in trichoderma. But I thought it would be a learning experience for me. So anyway, coming to the topic is that plant pathogens, they continue to pose like significant challenges. Despite the best efforts, we are still having like 10 to 30% crop losses in global yield average. When we were students, we used to go to the field and then see like crops getting damaged due to pathogens and diseases. And unfortunately, when you go now, also I see very similar picture. So probably this figure has not changed in the past few decades. So it's really a very challenging and area of research. And fortunately, we are having lots of new developments in the field. And we hope that with the new developments, we'll be able to cut this figure. 10 to 30% should be like average 10 to 15% max. And that thereby we can close the yield gap, which is a huge. In rice itself, I was reading somewhere like, the highest yield and lowest yield difference is about 30%. I mean, difference is 60%. So classically, as you know, like plant breeding has dominated the field of disease management as well as the chemical pesticides and fungicides, antibiotics. But there is an issue of durability of such a practice because of the emergence of new biotypes. So what we can expect that the newer tools which will be discussed in this panel as well as in this conference will be with the help of that we'll be able to manage some of these menaces. So I'll stop here and then we'll take up the topic again in the next round of discussion. Thank you.
Thank you, Dr. Mukherjee, for bringing out this issue of how much losses, diseases, and insects are causing to rice and other crops. So we will be discussing this issue again. But now coming to another important topic, and I will request Mr. Abhishek Burman, CEO, General Aeronautics Private Limited. Mr. Burman, please.
Yeah, good afternoon, everyone. Hope you are able to hear me clearly.
Yeah, please go ahead. Yes.
Thank you. So first of all, it's been real pleasure to be part of this eminent panel. And I'm kind of odd man out here who has, now as I look back, I see perhaps I worked for about 17, 18 years towards Jai Jawan, and last 3 years is more towards Jai Kisan. And together it is Jai Vigyan, right? And believe me, last 3 years been much more satisfying because bringing smile to a farmer's face has always been more satisfying than anything else for me. And, though we are primarily aeronautical company, but in India we can't say that we don't understand agriculture, not to the extent you guys do, but it's in our DNA, and that's what drove us to see that how best we can utilize our technology to solve the problem in agriculture. And the problem in particular, what we are working on is how to improve any kind of application efficiency, which today otherwise is primarily with manual methods. And we saw a good match that with aerial solution, wherein we we worked with various ICAR labs, various research institutes, and we got into nitty-gritties that where the problems are in terms of why we have such kind of yield loss, why we have poor pest and disease management, and how do we solve that problem. So one of the major thing what we found the problem area of the present application method was the way we apply any kind of input, and the associated bioefficacy what we get out of it. And that is one area we found that we looked at that how we can improve that part. And that's what I'll talk perhaps a little more in details. And while doing so, especially in the context of paddy crop, here one of the major factor is because it is flood irrigated, even to do a manual spray, typically one can cover 1 to 1.5 acre in a day, and which affects the containment of any disease or pest outbreak because the time it takes to cover takes more time. And while doing this, so here we are talking about, with a drone-based solution, what we do, we are talking about going up to 100 acres a day. Of course, assuming that you have 100 acres in one place and in just about 6 hours of time. So that's the kind of time efficiency you can bring into the system. And we wanted to do it in sustainable manner, that not to affect nature or human life adversely. So if you see another major advantage of drone-based application is the water usage, what you do, say 200 liters per acres or 500 liters per hectare. Here we are talking about 6 to 8 liters per acre without causing any phytotoxicity. So that's the kind of research and we have done. And if you add this up, though it sounds perhaps a little low, but if you take just 1% of the arable land, and if you replace manual spraying with drone-based spraying, you are talking about water saving, which is equivalent to 1.5 lakhs human being for entire year. So that's the potential of water saving, what you can get out of it. And as I said, in terms of bioefficacy, we did a lot of research on that, and what we found that we can improve it significantly. Like we are talking about somewhere in the tune of 80+% vis-a-vis what you see on the ground, 20 to 25%. And we have done a lot of research on type of droplet, type of control you need, and that's what gave us this kind of numbers. And in this process, another problem what I see in the manual process that agrochemical overuse, because you don't see good control on the ground, you end up overusing agrochemical. That can be completely eliminated because you are doing it with much more precision. The residues can be controlled much more effectively, and we did a lot of control data, not for say paddy, but for crop like cumin, etc., to establish this. And drone doesn't cause any harm to the crop, right? So you can design it in a manner that it doesn't cause any harm. And all this while causing no carbon addition to the system. So the entire solution, what we have envisaged, from the drone to the logistics, everything is all electric, so it doesn't cause any carbon footprint. And one question what Madam Ranjita was mentioning, whether technology is there for say a small and marginal farmer. And believe me, it can be brought to that level. And today, the way we have optimized the solution, farmer need not pay anything more than what he is paying otherwise, and it gives him many other tangible benefits. So that's how this I'm talking about just doing the blanket spraying part, but replacing it with much more efficient method of application. Now, moving forward, I have another 1 minute, or you want me to conclude now and come back on the second?
Yeah, I think you conclude now and then come back.
Perfect. So, other modes of precision agriculture, perhaps I'll take up in the next round. Thank you very much.
Thank you very much, Dr. Abhishek. By using drone technology, how we can increase efficiency, reduce time, and then also increase speed of various applications in the field. So we would be learning more about this particular technology from you in coming session also. But in second round of discussion, now we have 20 minutes with us for 5 panelists, and I will request every panelist to take 4 minutes so that we can wind up this whole second round in 20 minutes. So first of all, now I will request again Dr. A.K. Singh for his comments. Dr. A.K. Singh, please unmute yourself.
Yes, yes, Dr. Thank you. Thank you, Chair, and I'm thankful to all my panelist colleagues for highlighting very important point related to social sciences. And Dr. Pathak rightly mentioned about the greenhouse gas emission and zero carbon balance. How do we achieve that as a challenge, and how technology can chip in achieving these objectives are extremely important. One of the areas, is new technology and their adoption. And the question is often asked whether we are slow in picking up with the new technology. Now, take for example, genome editing technology. Yesterday we had a meeting, the chair, Dr. Sharma, was also part of the meeting about clearing the guidelines for genome edited crops. And this is pending for quite some time, which somewhere, dissuades people picking up newer areas or challenging areas. But in such areas, we also need intensive human resource development, capacity building by overseas training of postdoctoral fellows, and so that the researchers in these areas can be taken up. Excellent support in terms of funding from the ICAR through NSF project from DVT has been provided in area of genome editing. So far, about 32 projects are operational, and almost 30 crores have been granted for doing research in this particular area. Policy is one constant sometimes. Also, for example, the other panelist was referring about drone. Drone policy clearance is still so much of discussion happening, but certainly these technologies will bring much needed precision and reduce cost of cultivation in terms of insecticide, pesticide, and also will address the problem of pesticide residue, which many times becomes a concern of environmental pollution and also rejection of our consignment outside the country. However, in terms of adoption of the technology, we have done fairly well. Let us take, for example, molecular marker assisted selection through backcross breeding. In the country, across the crop, more than 75 varieties have been developed. But what is most interesting is that out of these 75 varieties, 43 varieties of marker assisted backcross breeding approach are in rice. The other day, Dr. Sharma asked me to compile this information when I was doing exercise. Total 43 varieties, but major focus has been so far on the biotic stress tolerance and some for abiotic stress tolerance. But the matter of concern here is that how is the adoption of these varieties? Out of these 43 varieties which have been released so far for commercial cultivation, some of them have been released as early as 2006, 2007. How much area has gone into the cultivation for these varieties? How far they have been able to replace the respective recurrent parent, which was improved for a specific trait. So this is one concern where we find that probably the progress is not very satisfying, and we really need to look into the regions, why it is happening. Many times the farmers say that the agronomic performance of these varieties, other than the trait which is added, is sometimes not at par with the recurrent parent, whether it is in terms of yield performance or in terms of quality, market acceptance, and so on. So many of these things we come to know not during our evaluation and release process, but these weaknesses of the varieties, they are brought to the notice once they are released for commercial cultivation. So this is one matter I think we need to see and how this can be corrected. The second concern in relation to this approach of breeding that I have is that the marker-assisted backcross breeding approach does not create a mega variety. It can only help rectifying the specific defect of a otherwise good variety. If we have to create mega varieties, which have enhanced yield, better adaptation, then probably we'll have to diversify our breeding approaches to marker-assisted recurrent selection, to genomic selection, the whole lot of population improvement scheme. On that, the focus is not so much. So that is another area where I think we need to look into. Also, once we realize that there is insufficient recovery and the quality of mass varieties, for some reason they are not getting adopted, whether we can, you see, generally we go by recovery in terms of, say, set of few markers, 60, 70 markers for background genome. And that estimation gives 90% or more recovery. But still, I think that recovery is not sufficient. Some critical traits are missed somewhere. And another reason for non-acceptance of these varieties is that in the process of developing these, in the meantime, the better varieties come from independent breeding program. So these varieties have to compete with them. We need to identify the strengths and weaknesses of the breeding program and try to do midterm correction so that whatever investment is made, that investment is brought to help the productivity of the farmers. I think this is what I would like to say at this point. Thank you.
Thank you, Dr. Singh, bringing out a very important issue of policy intervention, and then we have to identify strength and weaknesses of each program, and then one can do midterm corrections. So naturally, for adoption of new technology takes some time. But I think the rice is a crop where we have seen the intervention of technology and its impact on overall crop improvement program. So thank you very much, Dr. Singh. Now I will request Dr. Ranjita. Yes, please, again.
Thanks.
4 minutes, Dr. Ranjita.
Yes, thanks, Dr. Sharma. And again, picking on where Dr. Singh left, talking about policies and institutional changes that we need. What kind of innovations do we need to bring together with these technical innovations, new technologies to making impact happen, with a particular focus on smallholder resource poor farmers? Connectivity is critical. And when I say connectivity, it isn't just about a mobile phone or, or digital connectivity, but also it's those social and institutional networks that these people have, and the links, the rural-urban ecosystem links. And digital technologies are fantastic, but then digital divide is also a reality, something that needs to be taken care of. And then if we look at engaging with the markets and so on, which is really critical to make these food systems and the livelihoods resilient, we need to focus on developing small and medium agricultural enterprises. They can play a very critical role, and collectivization is very important. We have a very vibrant self-help group movement of women in India, which has transformed and continues to transform the rural economy. And then we now have a pretty good policy on farmer producer organizations, which should be a very crucial element of this. But we need to make sure we don't get into the numbers game there. How many FPOs do we establish? But we should rather focus on developing viable and sustainable enterprises, fewer, but good quality. I think that's what we should be doing. And then we need much more forward-looking risk management and insurance programs. We need social protection programs to go hand in hand with the technology or productive support programs. Cash transfers, school feeding, food subsidies, extremely important for the vulnerable groups that we are talking about. And we definitely need investment in public goods that reduce the risks, and irrigation and drainage systems, crop varieties that we have been talking about. And then one of the things I did want to mention briefly is about, women and youth. And I think women and youth, I think, have a very significant role to play in making these transformations happen. And contribute to, getting these technologies out into use, but also benefit from them. And men and youth are migrating out of rural areas, leaving agriculture. Why? Because agriculture is not remunerative anymore. And then the major and leaving women to take care of the farming. But then women continue to face challenges like access to productive assets, finance, access to lucrative markets, and so on. They face risks that are intrinsic to agriculture, and over and above this, these are the risks. So a double, triple, multiple times the burden. And we are worried that youth are leaving agriculture. Who's going to produce our food tomorrow? How do we make sure millions of poor we have to feed have economic access to food? And there is a very simplistic notion that young people can be lured back into agriculture. Give them a tractor or a mobile phone and they'll come back. It's not as simple as that. What we need is remunerative employment or entrepreneurial engagement in the sector. We need to understand their aspirations, motivations, and needs. And not all youth are the same, just like not all women are not the same. No, not everyone can become an entrepreneur, because that's what we seem to be talking about all the time. Employment is equally important. Employment in this largely informal sector, employment that is decent, safe, and remunerative, both for women and youth. And we need evidence-based strategies to support that. And both women and youth need financial products that meet their needs, taking note of the constraints they face. No collateral, low interest, flexible repayment periods, less bureaucratic procedures. They need business, financial, and digital literacy, mechanisms for access to product markets, particularly for perishables, to avoid the loss. We've seen a lot of that during COVID. We need to invest in technologies and infrastructure for post-harvest management, agro-processing, and we can do a lot by capitalizing on women's collectives. They have proven to be a huge asset to the rural economies. But what's really holding a lot of this back is because these perspectives are not included in the policy-making processes. And that is all mainly also because we don't invest in generating adequate and robust gender data that can support the development and implementation of such policies. So long ways to go there. Thank you.
Thank you, Dr. Ranjita. I'm sorry I have to intervene in between, but I'm acting here as a referee. So my job is to manage time, and I'm sure that you all will agree with me that these topics are very, very important and burning, and we should devote more time on those. Particularly, I think the crux of what Dr. Ranjita said, that remunerative agriculture, that will attract and change the whole landscape of agriculture, I'd say, in nutshell. So now coming to Dr. Himanshu Pathak, now I will request you to please continue with you.
Okay, thank you, Chairman Sir. As I told in my first round, that Indian agriculture, particularly the crop sector of Indian agriculture, can attain carbon neutrality by 2040. Why I put 2040? Because that is the year which has been projected that by that time, the world temperature will cross that 1.5 degrees Celsius mark. So let us keep that 2040. Now the technologies are which we are already having, we are already working with those technologies for some time. Those have got sufficient potential to mitigate. I shall give you just few of our own examples. Rice, if we go from continuously flooded to alternate winter and drying, apply neem-coated urea, which we are already doing, through leaf color chart, a very simple tool, all of you know, and using whatever information on soil health we have got. If we can combine all of these things in any farmer's field, the emission could be reduced by 40 to 50%. And there are n number of experiments which we have done on this. If we can shift to dry, direct seeded rice, then the emission is drastically reduced to 70%. 70% of what is actually done. Conservation agriculture, all of us are talking about. If we can follow that, then the GHG emission is reduced by around 30 to 40%. And sir, in last few years, what we have seen, if we start using renewable sources of energy, solar energy and so on, then the emission is zero. Net emission is zero. And of course, if we can diversify from rice, wheat to some other upland kind of crop, then the emission is reduced by around 70 to 80%. So these are all experimental data which we could collect over the years. And our observation shows that whatever of these technologies which we are following today, without upscaling, whatever we are following today, these are already reducing the emission by around 15 to 20%. Now, how to achieve 100% neutrality? My suggestion, and that is probably doable kind of thing, if we can upscale conservation agriculture, I'm not saying to 100% of Indian land, not 140 million hectare, to 25% of net cultivated area. Government of India has got another program of rehabilitating 26 million hectare by 2030. I am saying do not do it in 2030, but even if we can do it by 2040 and not into 26 million hectare, just to do it by only 25% of this area. And then precision agriculture, including some of these things which I shall mention, diversification of all of these, and also including not zero budget natural farming, but certainly natural farming or nature friendly farming. My calculation, which I was just doing in the morning, that the combination of all of these things putting together, the mitigation is going to be 160 million tons. And I said in my first round that crop sector of Indian agriculture emits 150 million tons. And if we do this, then the reduction is going to be 160 million tons. And over and above the next technologies, some of those what Dr. Singh mentioned, then of course Dr. Burman mentioned, and Dr. Prashant Mukherjee is also going to mention a few of those. I tell them smart TIFR, smart tillage, like conservation tillage, smart irrigation using macro and sensor-based tools, smart fertilization, demand-driven, smart energy like solar, and smart residue management. So this smart TIFR, if you can really do, certainly the emission is going to be very, very small, very, very small. Besides these field level technologies, sir, we also need to do some kind of macro scale adjustment, and just few of those, as I said, rehabilitation of degraded lands, use of renewable sources energy, and also agroecological planning, which I all the time say, growing a crop in the most suitable area where you will be using less and less amount of external resources. So these are some of the options by which Indian crop sector can be made carbon neutral. If I find opportunity in the final round, I shall tell some of the policy requirements which are very, very important to attain all of this. Thank you very much, sir. Thank you very much.
Thank you, Dr. Pathak. In this round, you have really touched upon various intervention and adoption of different technologies to mitigate carbon emission. And today morning, we had a very interesting conclave on budget natural farming. I think that's a part of conservation agriculture. Conservation agriculture, which Honorable Prime Minister was also telling today. So we all have to think very seriously to mitigate carbon emission. So thank you very much. Now we will move to Dr. Prashant Mukherjee, and I'm sure that he will touch upon certain points related to plant immunity and non-host resistance. Dr. Mukherjee, please.
Yeah, thank you, Dr. Sharma. The question is like where we stand in terms of our ability to modulate plant immunity and broad spectrum disease resistance. So this is really a very important issue. As I said before, like broad spectrum resistance and durable resistance, they are somewhat difficult to achieve, but they are the need of the hour if we want to really close the yield gap. In this context, I must mention that plant pathology is one subject in agriculture that has benefited immensely from basic science research, and that has resulted in the availability of novel tools and candidates that can be deployed for better disease management. For example, as you said, like understanding of non-host resistance. We have several candidates that are involved in pathogen perception, pathogen effector binding, defense signaling pathway, gene for susceptibility. It's a relatively new concept. Of course, our genes are there. We have several genes involved, identified that are involved in biosynthesis of secondary metabolites and antimicrobial peptides, and of course the RNAi-based pathogen suppression strategies. it has been unambiguously proved that several microbes can modulate plant immunity. As you know about mycorrhiza and trichoderma, they are very successful examples where the microbes can really, sometimes they do wonder. And of course, some chemical modulators of plant immunity are also available in the market. Now, when it comes to making use of these innovations, we are certainly lagging behind, as other panelists also told. As with other technologies, like here also we are really lagging behind. Even though we have tools available like transgenics and genome editing, we are unable to properly use commercially these new developments. Of course, one issue is the regulation, and but science is moving very fast. So we hope that with the new technologies that are coming in science, some of these hurdles can be overcome. Can I go to the second question now? Or?
Yeah, please go ahead, because we don't have time for another round. If you see the
I think yeah.
Quickly.
Second question was like to have a chemical pesticide. I mean that it is related to that. As you know, like most pesticides are used in a few crops, which means that very little pesticides or no pesticides are used in majority of the crops. So there is a big scope here to go for pesticide-free crop protection, especially using microbial intervention plus plant breeding. So these two, this point I want to emphasize, like getting very high level of resistance is possible, but they are most of the time not durable. But if you have a moderate level of resistance, and that can be combined with microbial intervention, probably that will give you a more sustainable disease management strategy. And now with that, a new concept of microbiome and endophytes, these things have come in a big way. Even the plants are modulating their own microbiome, to achieve resistance against pests, and even cultivar-specific modulation of microbiome is also has been reported in many crops. So these two things are intertwined, and we should try to combine what I mean is durable resistance or moderate level of resistance with microbial intervention for achieving a better crop management practices. Thank you.
Thank you. Thank you, Dr. Prasoon. But I would like to conclude from here that gene deployment is most important in all diseases and insects in different varieties and different species, instead of cultivating only one gene for resistance in particular variety, so that we should not have vertifoliation effect or genetic vulnerability of a particular variety. So thank you very much. And now again moving to Mr. Abhishek. Mr. Abhishek, please kindly unmute yourself.
Yeah, thank you. Sorry, I was on mute. So, with permission of chair, before I start, I just want to show you one image. What I was talking about, why bioefficacy we can improve much better with the drone. And this is an image with drone-based spray with 6 liters per acre dosage, covering 1 acre area in foam coverage. You have every leaf, and look at the underside of the leaf. Be it leaf, stem, everywhere you get the coverage, and that's what gives you, in fact, one of the factors that gives you much better bioefficacy, and while causing no damage to any of the flowers, right? So just wanted to show you this before I proceed further. So, continuing on what I was saying, so this is also, I would say, a part of phase 1 of precision agriculture, where we are improving the application efficiency and making it much more precise. Now, other part of it, agrochemical side, whether I can use any agrochemical which is available, or it is just, some agrochemicals. So far, whatever data we have from elsewhere in Asian countries and also our experience in India, what we got to know is about 95% of agrochemical can be used with this kind of dilution. Of course, it depends on type of spray system, etc. But there lies definitely a possibility wherein, today we just go by CIB-RC recommended dosage and we use it for spraying. We don't change the active ingredient part. But because your application efficiencies are far, far better, you can look at formulation, where you can perhaps look at reducing even active ingredients. So that opens up a new, I would say, a new technological improvement which can be brought into this. So that's one part of it, and this, I would say, phase one of precision agriculture. In phase two, why I see precision agriculture going to the extent wherein you will detect everything using artificial intelligence and spray only where it is needed. Finding acceptance of such a tech today with farmers is not going to be easy. So I would say the phase two of precision agriculture would be something wherein you have a severity map of entire field. You still spray in a manner where you are spraying in the entire field, but the dosage would change depending on the severity. And that's not too far. You already have sensors which are available, which gives you the kind of stress level the crop is into, and you can, using variable rate technology, which our drone has, you can always spray different amount depending on the severity of the infestation. So that would be, I would say, the next phase of precision agriculture, taking from spraying, just uniform dosage. The third would be wherein you need to detect first using the already trained AI model, and in fact, with one of the ICAR lab and with Coconut Development Board, we have developed one such technology over the last 2 years for coconut plantation. And now we are doing for chili and going to start for paddy pretty soon. Now there, what we can take it up to a point, extremely sorry, there is some to a point where one can go to the level where you spray vigilant, and it should not happen the being more vigilant. So if you have to do more and more, compensated, and as I said, it is also difficult to convince a farmer. So these are the things which comes to precision agriculture. Now, another areas where we are using this is pollination. Pollination is one very good possibility with the drones, where you can improve the quality. People are using for missing tassel or doing the stand count, apart from the pest, just the pest and disease management. On the greenhouse gas emission, we are talking about doing some kind of aeration, but if you have to earn the carbon credit out of this, you need to also give certain audit of that the water was really taken out, and that's where again drone comes to help. So these are the areas where drone or the associated sensor technology can make a difference. And going forward, it's not only drone, it would be integrated farm management where you're using some ground-based sensor, weather information, combining all this to make it possible.
Thank you.
Thank you. And just the last point, which was the point asked to me on the regulatory side, as Dr. A.K. Singh also mentioned, on the regulatory front, I would say last 6 months, there is huge amount of acceleration, because when you talk about drone, there are two elements. One is from the drone side, which is DGCA, and other is CIBRC on the agrochemical side. And as we all, majority of us may know that agrochemical guidelines, almost it is in the final stages, and it is made really industry friendly. And drone side, it is really made easier to do especially for agriculture, where you don't require any special permission. So yeah, I think I've taken a little more time, but thanks for this opportunity.
Thank you, Mr. Abhishek. Yeah, this is a field probably you need 1 hour to discuss, because it's a very interesting field. And I would add one more point here, that we can use drone or sensor-based technologies for high throughput phenotyping in plant breeding, which is very, very important now when we talk about high throughput phenotyping and breeding. So now with this, we have completed all the presentation by all the panelists and discussion points. I have left with me only 5 minutes because we started at 1:20. So I would like to conclude it at 2:20. So for 5 minutes, we can have discussion. Any quick emerging point from the participants? We have 111 participants here. And I'm sure that they might have certain questions. Yeah, anybody, they can raise hand or they can come. It's very difficult to manage such discussion through online system.
I have one question to Abhishek
Yeah,
from his area, if you permit.
Yeah, please go ahead.
Abhishek, you said about the drones for pollination. I don't know if you have experimented, because hybrid seed production, under which we have about 60,000 hectare area in 4 districts of Andhra Pradesh: Karimnagar, Warangal, Khammam, Nizamabad. And it is all hybrid seed production in rice field is done manually by stick pollination or rope pollination. If you can design your drone for pollination in hybrid rice seed production program, we can arrange some field right from coming crop season, and that will be a revolution in terms of bringing down cost of cultivation, because that's a major activity for hybrid seed production.
Absolutely, sir. So we have done some such experiments. I hope you're able to hear me. We have done some such experiment which have given good results, and in fact now we are also starting a project in UAE that is for date palm, where problems are different in nature. But out here for paddy, we have done some experiment, and this can definitely be done. And it's a very cost-effective manner, like in a drone, like if I cover 3 acres in one flight, here for pollination I can cover 10 to 12 acres. So the cost comes down drastically.
Thank you very much. So I don't see anybody now have any question here. Person, quick question now. 1 minute, only 1 minute I have.
To Dr. Abhishek again, like the precision agriculture you touched upon, which has basically developed in US and other developed countries, which huge plot area, hundreds of acres, where they could not micromanage the soil or the field. But in Indian context, like where the plot size is very small, how do you see like it is applicable?
So, drone-based technology that way makes it more easier for small landholding. For large landholding, in fact, aerial sprays are better, where you use helicopter or airplane. So that way, I would say bead spray. Of course, the imaging part requires a little bit larger, but I'm sure as the technology finds inroads in the market, you will see people joining hands together, and perhaps entire village, you will do the complete phenotyping in a single flight. So that will reach. But when it comes to the spray and precision type of spray, this is ideally suited for small farmer. I would not say less than 1 acre, because their farmers generally they do themselves unless they combine together. But for small farmer, this is the perfect solution with drone.
Thank you. Thank you very much. Thank you all. It was really very interesting 1 hour discussion, 1 hour 20 minutes now, although we consumed 20 minutes in introductory part. But that's also important, because people should know who we are talking here and in which capacity we are talking on these subjects, which are very, very important. And all our experts are, as I told in the very beginning, they have touched upon all the latest areas related to crop improvement and its cultivation, and also greenhouse emission, and also their role in society as a whole. And then use of drone technology. Probably we can organize one separate conference on drone technology, its application in different crop management practices. So with such type of discussion, there are so many points which need to be further deliberated in an extended seminar or conferences. But many good points have been brought out in the notice of all the participants by our panelists. And I would like to thank all our panelists for sparing their time and having a very precise and to the point discussion today. So with these words, I will stop here. It's exactly 2:20 because I have to leave for another meeting. So thank you very much.
I'll just take a minute, sir, to offer a vote of thanks. Sir, on behalf of Association of Rice Research Workers, and also on my own behalf, we profusely thank our beloved Deputy Director General Crop Sciences, Dr. T.R. Sharma, for chairing the session and then guiding the session in a very nice manner despite his busy schedule. We also thank all the panelists, Dr. A.K. Singh, Dr. Ranjita, Dr. Himanshu Pathak, Dr. Prasun Mukherjee, and also Dr. Abhishek Barman for kindly sharing their viewpoints and also guiding us. And I also thank my colleagues, Dr. Kaushik, Dr. Bishwajit Mandal, and also Dr. Amtul Varis, who served as rapporteurs. Thank you, one and all. Thank you.
Okay. Thank you very much. Namaskar.
Thank you very much.
Okay.
Kutub, I think you should announce about the breakaway groups and all these things. Yeah.
Yes, sir. Yes, sir. So what an amazing panel discussion. Indeed, it is tempting to keep a good thing going on, but that is not possible due to schedule and time. I thank the chair and the two conveners for nicely conducting the panel discussion on time. But before we break for lunch, it's not lunch, for a small break, but for a reminder, we have 4 simultaneous sessions after lunch. They will start from 2:30 p.m., which is from here 8 minutes only. Session 1 have 4 different lectures. Session 2 have also 4 different lectures. And session 3 and 4 will have lightning talk from the participants. So please click on the respective links where you want to listen or you want to present. So we now break for this 8 minutes, and we would start the respective link at 2:30 respective sessions. Thank you, sir.
Thank you. Thank you very much. Thank you.
Thank you. Thank you.
Thank you, Dr. Kutub.
Thank you very much, sir.
Thank you. Thank you very much, ma'am.
Thank you.
Hello.
Hello, sir.
Am I audible?
Yes, sir. Yes, sir. You're audible. Yes, sir. You are audible.
Okay. Thank you.
Thank you, sir.
Okay. Thank you, Dr. Kutub.
Thank you, sir.
वेलकम कर लो। वो आए कि नहीं पूछना पड़ेगा।
Wensing sir, good afternoon, sir. सर अनम्यूट कीजिए।
Yeah.
Yes, sir. Sir, good afternoon, sir.
Good afternoon to everybody.
Yes, sir. Sir, nice to see you, sir. I think Dr. Kutub, we can start now.
Yeah.
I think this session technical session 1 on GNX technologies in rice breeding. This would be co-chaired by Dr. Wen Singh, Vice Chancellor, Birsha Agricultural University, and Dr. P.K. Agarwal, Vice Chancellor, OUAT, Bhubaneswar. And the convener is Dr. Sangamitra Shamantarai, Principal Scientist, National Rice Research Institute. And both of the rapporteur, Dr. Jyoti Badri, Senior Scientist from IIRR, and Dr. Kaushik Chakraborty, Scientist from NRRI. So I hand over to Madam for smooth conducting of this session. As I know, the first speaker of this session, Professor Kevin Ji, already has joined from China. Ma'am, unmute, please.
Thank you, Kutub. A very good afternoon to one and all attending this session through virtual mode. Distinguished scientists, heads of various institutes, senior colleagues, research scholars, students, Ladies and gentlemen, I am Dr. Sangamitra Samantray, Principal Scientist, Agriculture Biotechnology, convener of this session. Welcome you all to this technical session, Gene Next Technology in Rice Breeding. In this ARRW Diamond Jubilee National Symposium on Gene Next Technology for enhancing productivity, profitability, and the resilience of rice farming, organized at NRRA Cuttack with collaboration of ICAR and ICR and NRRA Cuttack. I am very happy and grateful that many distinguished scientists and scholars from different organizations are attending this session to share their knowledge and experience and also explore a better ways for rice improvement with the latest technology of precision breeding. I extend my special thanks to Dr. Pavan Agrawala, VC, OUAT, who has agreed to co-chair this session. Further, I would like to take this opportunity to express my deep appreciation for Dr. Wen Singh, Vice Chancellor, Birsa Agriculture University, Jharkhand, for accepting our invitation within a short period of time to co-chair the session of this symposium. Now, I request both of them, Dr. Agrawal and Dr. Wen Singh, to co-chair this session. Now, it is my privilege to introduce our co-chairs of this session. Though both the chairs do not require any introduction, however, as a customary, I have to introduce to the participants attending this session. Firstly, I introduce Dr. Pavan Kumar Agrawal, who did his postdoctoral studies at the prestigious John Innes Centre, Norwich, England. He was awarded with Sardar Iqbal Singh Gold Medal for his meritorious performance during the MSc. He was also bestowed with the F.B. Joshi Award, the highest award by IRI New Delhi. He is also a fellow of National Academy of Agricultural Sciences, India. Dr. P.K. Agrawal joined the Indian Council for Agricultural Research as an ARS scientist and was placed at the National Rice Research Institute, Cuttack. His interest of research was conventional and molecular breeding rice, maize, and finger millet. He has visited and worked in many foreign laboratories. He was a visiting scientist to Erie, Philippines in 1997, where he worked on marker selection in rice. During his stay in England as a postdoctoral fellow, he reported a novel biologistic system for multiple gene transformation called clean DNA transformation. He has mapped a number of genes in maize for amino acid modifiers, iron and zinc content in kernels. He is also a visiting scientist toward the Ivory Coast, Africa. During his research career, for more than 26 years, Dr. P.K. Agrawal has many scientific contributions. He has developed more than 25 crop varieties in maize, rice, and other crops. BBEC QPM9 is the first mass-derived QPM maize. Similarly, CR839, a basmati line, satisfied the new plant type named limited tillering plant type, which was conceived and developed by Dr. Agrawal. He is also one of the pioneers in starting work on DNA marker selection, breeding work in India. He has pyramided a number of agronomically useful genes in maize, rice, and wheat for quality traits and biotech stresses. Dr. P.K. Agrawala joined ICAR headquarters in May 2014 as Assistant Director General and Director National Agriculture Science Fund, ICAR. He joined as Vice Chancellor of Odisha University of Agriculture and Technology, Bhubaneswar on 14th May 2009, and also he is continuing till date. Then Dr. Wen Singh, everybody knows at CRRI, Dr. Wen Singh is the VC, Birsa Agriculture University, Ranchi, Jharkhand. He was also holding the position of Technical Member, Plant Varieties Protection Appellate Tribunal, Government of India, before joining to this VC. He was also the ex-head and principal scientist of CID, NRRA Cuttack, Odisha for 16 years. He has vast experience of rice research of over 30 years, along with 15 years of teaching experience in ARRW Pusa, Bihar, and NDUAT Faizabad, UP. During his career span, the significant accomplishment made by Dr. Singh, releasing 36 rice varieties for various ecosystems. Besides, under his able leadership, NRRA could develop and release world's first high-protein rice, Siardan 310, which carries 10% grain protein. Further, he has developed 5 Arabic rice varieties, first of its kind in India, in collaboration with IRRW Philippines. Dr. Singh has over 100 research publications of national and international report, and also published several books and book chapters. For better known to rice community as expert, he has visited several countries like Philippines, Malaysia, Bangladesh, Nepal, and Vietnam. He is fellow of various professional societies and received several honors like Plaque of Appreciation Award 2015 from IRRW Philippines, Distinguished Scientist Award 2014 from Society for Scientific Development in Agriculture and Technology, Art Director of Rice Research, Bio Fellowship Award 2015 from Professional Society, Bio Research Society, and Best Worker Award 2009 from ICAR-NRRI Cuttack. Sir, once more, I again welcome you, both of you, sir, to this session. And sir, now over to you, sir, to conduct this session very nicely. Thank you, sir.
Dr. Agrawal.
Yeah, should I talk, Dr. Sir?
Also, good afternoon. Very good afternoon.
Good afternoon, Dr. Sir. Good afternoon. Should I start or you are starting, Dr. Sir? I will start.
Yes, please.
Yeah. Thank you very much. Thank you, Dr. Sangamitra, for a excellent introduction to me and Dr. Wen Singh. As you are aware, during the symposia, we are going to have a deliberation related to next generation technology in rice breeding. As you are aware, among all the crops, rice was the first crop where a institute was created dedicated for a crop particularly. That was the beginning of the concept of the crop. And from 1946 onwards, breeding part work in rice particularly, NRI contributed or ex-CRI contributed significantly to the global rice research. Breeding is always a very important part because whether it's food security, it is nutritional security, it is a productivity, breeding always contributed to the maximum to the global food situation. So it is right time that we need to deliberate how coming another 20-30 years, breeding will be seen. And that is very important in one context, that any sciences you see last 100-150 years, for example, last century, first 50 years, there is a lot of development related to physics and chemistry, and biological research took advantage of all the learning from those sciences. Similarly, last 15-20 years, if you see, whether it's genome editing or gene manipulation, for the 1980s, let me give you an example. Gene manipulation and understanding of transformation were very well studied, and that made an impact on today how we make a gene transfer in different commodities, whether it is plants, animals, any commodity. Similarly, recent development, 2012 or something around that time, the genome editing concept where a gene can be very precisely manipulated and can be altered and make either you can make a loss of function or gain of function, and both are very, very critical. Similarly, one more issue comes that how you can make a very good breeding cycle for breeding, different commodity for breeding. And experience of NRI for RGA and other things paved a way almost 40-50 years back. Today, we have a better understanding of how being a plant, the reproductive stage is coming, flowering, crossing, still we can many generations, 4 generations, 5 generations, 6 generations. The scientific developments has happened last 10-15 years. Even this, the breeding program or many generations in a short time was done, even a space shuttle also. A lot of experience from space shuttle was used in development of those kind of science. And today we have 4 speakers, all are learning speakers. Professor G from China, talking for CRISPR technology. As you are aware, CRISPR has made a huge change to the biological research today, what probably was not possible 10 years back or 15 years back. Every small one nucleotide also you can either add or delete or manipulate. And every day you read a research paper, you'll find a difference. You are learning more. Similarly, Dr. Ajay Kohli, my earlier colleague in UK, he will be talking about next generation plant breeding technologies for food security and climate change. As you are aware, today climate change has become a big issue for food security point of view, and of course, breeding program always takes care of the climate. But still, a robust scientific base will give a strength to the output in a short time. Our third speaker is Dr. Wang from China again, and he will be talking about apomixis. If you see the research in apomixis last 40-50 years, China always took a very big lead, and experience of China and IRRI, some way. China got some experience from IRRI and vice versa, and the whole rice world was benefited. I'm sure his talk and deliberation will help all the participants, the speaker, to learn more. And our third speaker, Professor Savala from Australia, she will be talking about stress physiology. And as you are always aware, as a man in application, our phenotyping is based on whole plant or whole organism. And today's talk is about the cell-based phenotyping. That means the phenotyping at the cell level and phenotyping at the whole organism level should be same. Very difficult job. Lot of understanding has to be there. You have to have a right candidate marker and right candidate traits, which can talk that even if at cell level you see some character that will be applicable at the whole organism level. 80, for example, you see, where proline stress was tried to be correlated with the abiotic stress of drought particularly. And there's a lot of debate whether it is giving a good result or not. But today we are having better understanding molecular mechanism of cells. We have a better understanding which trait to be correlated to which trait at the adult level. So I'm sure listening from all the learned speakers, 4 speakers, will be more wiser after listening them, and we have a deliberations. I thank all the speaker and organizer for inviting such good, well-known speakers, and topics are very timely, very challenging. So I welcome all the speakers, and I request also my co-chair, Dr. Owen Singh, to kindly continue the session, sir. Thank you very much for co-chairing, and rather you will be chairing. After some time, I will be leaving because of some personal requirement. And when I get a chance, I'll join. But profusely thank the organizer, the director NRI, and Dr. ONC, Honorable Vice Chancellor of Birsa Agriculture University, and everybody of you. Thank you so much, and giving me a chance. Thank you again. Thank you.
Good afternoon, everybody. Honorable Professor P.K. Agarwal, Vice Chancellor, Odisha University of Agriculture and Technology. My all friends from CRRI, I still call CRI because I love CRI. I consider my institute at Cuttack, that is my professional home. And I always will consider Cuttack as my professional home. Friends, Dr. P.K. Agrawal, I can understand is because of his wife departure, and he could spare some time. I'm really very much we all indebted because he's sparing some time because of he's still he's in so much pain. I know. So first of all, I thank organizer for giving me opportunity. Though I have one another meeting going on about QRT. QRT is running in my university, but still I thought Cuttack. Normally I don't say no for Cuttack, whatever it could be, but I try to adjust with Cuttack. Friends, it's a very, very important topic. I really thank to my colleague at Cuttack that they have chosen a topic which is very, very relevant because we all feel that things are still stagnant as far as overall productivity is concerned. So it's a very good topic, and what very good topic what people have chosen. All speaker really they have. The CRISPR-Cas. It's a very relevant topic in today's time because it will be very much useful as far as practical breeders are concerned. They will be very much. I believe that in future they will be using this technology from Cuttack Institute also. I think Dr. Kutubuddin Molla, he is also having expertise. So this by interacting with these kind of people, he will still fine tune himself. I will not speak much because time is also, I have to also leave quickly, but I will be here for some time. So I thank to everybody, including Madam Samantre, who was very much keen to request me. Friends, go ahead with Madam Samantre, please go ahead with the program. I request Dr. Who is the first speaker? Perhaps Dr. G? Dr. Kutub?
Yes, sir. Yes, sir. Dr. Kevin G.
He is the first speaker. I think already Dr. Agrawal Saab has introduced about him. I request Dr. Kevin G. Please go ahead with your presentation. Dr. Kevin, please.
Okay, thank you. And I share my screens. So, is everything okay?
Yes, yes.
Yeah,
So
yeah.
Please go to slide. So, yeah, okay, wonderful.
Wonderful. So first, I want to thank you, the organizers, to invite me to give to present my research here. And I also want to say big congratulations to the Association of Rice Research Workers in India. So I know it's a Diamond Jubilee National Symposium for the association, and congratulations. So today, my talk is about some CRISPR technologies we developed in rice. So here is my outlines. We are talking about some Cas9 gene editing tools, Cas12, and a gene editing pipeline we recently developed. So at the beginning, I wanted to use a couple of slides to introduce some background about CRISPR-Cas9 technologies. So about 10 years ago, I think 3 scientists, very bright young scientists, they find that the CRISPR-Cas9 from bacteria can be used for gene editing. So we normally call it RNA-guided gene editing because the Cas9 protein can be directed to target the DNA by a single guide RNA. So I think in the past 9 years, many scientists and many from different countries developed a lot of CRISPR-Cas tools for gene editing and for other technologies. So in plant, CRISPR-Cas9 is considered as a next generation plant breeding technologies. So it will have many advantages comparing to some traditional breeding method. So in CRISPR-Cas9 is I think many people like to consider as a Swiss Army knife because it has many different functions. It can be used for genetic manipulations, For example, we could use CRISPR-Cas9 to mutate genes, and also can do genome-wide functional screen. These two parts we're going to talk about it today. And also can be used for base editing, RNA editing, prime editing. In addition to genetic manipulations, CRISPR can be used for basic molecular biologies. For example, we could use a CRISPR-Cas9 to deplete unwanted DNA sequences. We also can use a CRISPR-Cas9 to enrich wanted DNA sequences. So it is very particularly useful when we want to remove something in next generation sequencing or enrich something in sequencing. For plant biology, or particularly for plant pathologies, we can use a CRISPR-Cas12 to use as a DNA or RNA detection tools. So we could diagnose plant disease in the field using CRISPR-Cas9. So here is some simple introduction about these different CRISPR-Cas9 technologies. In most of the cases, we use the CRISPR-Cas9 to lock out the genes or lock in a genes. So here we use the Cas9 and a single guide RNA to cleave the target DNA, then use the endogenous DNA repair systems to mutate the gene or to lock in a foreign DNA fragment. We also can use a Cas9 linkase with a deaminase to convert one base to another base, is base 18, and then we can use the deactive Cas9 fused to a suppression or activation domain, and then use a guide RNA to put the Cas9 to the promoter. So it enables us to control gene expression. And I think 2 years ago, the prime editing allowed us to change, make small DNA sequence changes using a reverse transcriptase fused to linkase Cas9. So basically my work is focused on some the optimizing the CRISPR-Cas9 gene editing efficiencies. But 8 years ago, when I'm in Yang's lab in America, we developed a vector, we call it PRGB32. This vector can usually have a high efficiency for rice gene editing, but we only can edit one gene in one construct. Then we hijacked the tRNA systems for multiple gene editing, and then we put the tRNA GNAs in the introns for gene editing. And recently we developed technologies for CRISPR reconstruction. So I think I will begin to introduce my work from our tRNA systems. We did, I think 6 years ago. So here is a simple introduction about the tRNA systems we used. We had jacking the endogenous tRNA processing machineries to process GNAs. So this photo, I think, is a simple introduction of how tRNA works. The tRNA can be cleaved by 2 enzymes, amylase P and amylase Z. Both enzymes existed in all cells. So if we fuse the tRNA and guide RNA GNA together and construct an array of tRNA GNA units, these transcripts will processed by the 2 enzymes and cut the GNAs to individually. Then we could use this simple strategy for multiple gene editing with high efficiency. In our experiment, this approach have a very high efficiency. Some of the sites have 100% gene editing in rice. So I think this system all works in all cells, like in fruit fly, in yeast, and in human cells, and in many different organisms. tRNA and guide RNA can be used for multiple gene editing. So I just show some results from the other labs. I think they like the GNA strategies. They could use our TRNA system to edit multiple genes at the same time with high efficiency. So after we introduced the TRNA system, we are thinking about can we put get RNA, gRNA, and Cas9 using one promoters. This is because we think when we make a CRISPR-Cas9 construct vectors, the gRNA expression, the promoter we use the gRNA expression, we can use a U3 or U6 promoter. These two promoters may sometimes not very high, the efficiency sometimes not very high. So we think if we can put the gRNA and the Cas9 in one genes, we could drive this combined gene using the 35-way promoter or ubiquity promoters or active promoters. And this synchronized expression of Cas9 and gRNA maybe increase the efficiency. More importantly, using this structure, we could make some inducible CRISPR tools. For example, we could use a disease-induced promoter to drive the expression of Cas9 gRNA, and so we could make a disease-induced gene editing tool. It's also we are reduce the vector size. So we look up some DNA sequence and the genetic element. Finally, we think the intron may be a good choice for our purpose. We know that the intron are spread from the primary mRNAs, so it will not interrupt the gene expression. If we put something in the intron, in plant, we also found some no-coding RNAs like microRNA and SNL RNAs are processed from introns. So we believe intron may be engineered to get RNA with Cas9. So we developed a strategy we called intronic RNA systems, and we call it IRMPDG. So in this system, we put a tRNA cassette in an intron, and this intron can be fused with the Cas9 protein sequence. So when we express such a hybrid genes in plant or in other organisms, the primary mRNA we are spliced, and the intron we are cut out, and the exon we join together to express Cas9. Then the intron will be processed by the tRNA systems as we show here, and the gRNAs we put in the intron will be cut from its primary transcript and get Cas9 to edit a different target. We made a couple of different constructs as we show here, and all these plasmids are available under edit gene. So in our first batch of vectors, we put the intron before Cas9. These introns and 5 UTR of Cas9, and we have a cloning site here, so we could cloning the tRNA in the intron. So I already showed 2 examples when we compared the intron strategy and the conventional U3 vectors. So we can see from these 2 examples, if we use the intron to express Cas9 or to express gRNA, it will sometimes increase the efficiency as we found in the 5 example. But sometimes its efficiency may be reduced a little bit. Anyway, this strategy worked, and the thing looks very functional, very efficient in mice. Another important thing is this strategy is very flexible. We can express these hybrid genes with different promoters. I showed 2 examples here. We could use a PR1B and a PR5. Is a passenger-related 1 and passenger-related 5 promoters to express Cas9 and gRNA. So the editing efficiency is good here using these 2 inducible promoters. And then we also can put the intron, the engineered intron in 3 UTR or in the middle of Cas9 without a trade-off of editing efficiency. If we do not want to put the engineered intron with Cas9, we can put these TRNA introns with hygromycin, which we did it for RAS transformations. And also the efficiency, AD efficiency is good for if we put the TRNA intron in favor into hygromycin. So anyway, I think the intron is a good choice to express the GMAs. So besides the Cas9, the Cas9 tools we developed. We also have some works about Cas12. Cas12 is also an alternative of Cas9. They have 3 enzymes that can be used for gene editing, but I think today we have many different tries about Cas12. In the last 2 years, many scientists find different Cas12 enzymes for gene editing. The advantage of Cas12 seed is it can process the CRISPR RNA arrays. It means we don't need a TRNA system. We just put a different CRISPR RNAs, that is the RNA guide, in one fragment. Then the Cas12 will cleave this array to individual CRISPR RNAs for multiplex gene editing. So the Cas12 also can recognize the T-rich pi, and is cleavage size distant to pi, and have low off-target activities. So we tested this the Cas12 in rice. We used two Cas12. One is FN Cas12, one is ARRW Cas12, or I forget to mention that. And at the beginning, the Cas12 was mentioned as is named as a CPF1. So I mixed the user Cas12 and CPF1 in this slide. So anyway, I just want to show these tables that in our experiment, the Cas12 is not always efficient. For example, in this target, we MAPK2 target, the FN Cas12 have high efficiency, but the ARRW Cas12 have no editing in our situation. So I think the Cas12 maybe did some site have high efficiency, some site have low efficiency. We may design the target site or design the guide RNAs. We need to pay attention to it. So I think the Cas12 has another wonderful applications. They can be used as a DNA detecting tools. If we combine the Cas12, RPA, and a field paper-based DNA extraction method, so Cas12 has a very unique features. If we recognize the target DNA and cleave the target DNA, it also has a collateral single-stranded DNA cleavage activity. So it means it can cut all the single-stranded DNAs in the same reaction. So these features can be used to develop a DNA testing tools. So the RPA, maybe some of you may be not familiar with RPA. RPA is something like PCR. It can amplify the DNA fragment from a template, but it's a template, but it's only need it performed at low constant temperature, and is optimal temperature 37 centigrade. That means if we use RPA, we could amplify the gene fragment in our hand. So here is another field paper-based DNA extraction method. That if we only need a field paper, we normally use in laboratories, can extract the genomic DNA from rice leaf, from the leaves. So we combined all these together and developed a all paper-based DNA testing method. So here is the procedure. We put a plant leaf in a tube, then grind these leaves and put the field paper into the solution and extract the DNA. Then transfer the field paper to the wash solution and transferred to a RPM mixtures. So we added the Cas12a and CRISPR solutions in this tube for maybe 10 or 15 minutes. And they put a lateral flow assay field paper to this solution. It can detect the gene exists or not. So this lateral flow assay paper can detect the single strand DNA reporters. So I think I'm not going to the details about these mechanisms because we already published the paper. Just to show you the result. So for rice disease, for rice blast disease, if we cut a loop and put in the tube and run this testing, we could find a positive line here and here. If we cut a rice leaf from transgenic lines, both can detect it is transgenic or not. So the testing may be not perfect because sometimes we find that this binding is not a dark, not very sensitive. But I want to emphasize this method. We could do DNA testing without any instrument. We did a couple of tubes and a couple of solutions. We can run this DNA testing in the field. So I think it will be very useful for disease diagnosis and GMO testing. So I think I will move to the third part of the topic of my talk. After we develop the CRISPR-Cas9 gene editing tools, we are thinking about can we use CRISPR-Cas9 for genetic screening. That means we needed to establish a hexagon pattern gene editing pipeline so we can edit many genes together, and then we make the mutant and to study the function of these genes. This is not new ideas. Actually, in animals, I think 6 or 7 years ago, they already used CRISPR laboratories for genetic screening. There are the two formats. One is a pod laboratory, one is a original laboratory. So in the pod laboratory, they just synthesize a lot of guide RNA construct and pour the construct together, then delivered into cells in one tube. So then they could apply the positive and negative screening of these cells and using them as the hexagon pattern sequencing to analyze the DNA boundary, then could find out which genes is associated to these selection screening conditions. In original laboratories, they just put the Cas9 construct in a multiple wear plate. So each wear have one plasmid and to lock out one gene. And then they deliver these plasmid into cells and do phenotyping in these wears. So the phenotyping could be used a microscopy and or reported genes. These can be used for very complicated or high content phenotypic screen. Anyway, both strategies are based on the cell culture systems, but in plant we do not have cell culture systems as animals. So I think both format of laboratories are difficult to implement it in plant. But some groups do CRISPR laboratory in plant. Here is the two Chinese laboratories. They constructed a mutant population with a transformation of tens of thousands of CRISPR-Cas9 plasmid. So I think the strategy is very simple. They synthesize the tens of thousands of guide RNAs and link it to the vector and put all these constructs together, then make a lot of transgenic lines. Then they will get a mutant population. So in the past 3 years, such a pod CRISPR library has been used in maize, soybean, and tomato. So I'm thinking about it, is there any easy ways to generate a CRISPR laboratory with high coverage? Because in my opinion, most of the researchers want the CRISPR laboratory covering maybe 100 to 1,000 genes of functional analysis. But they want their laboratory covered all these genes. So that means they should have a high coverage. So 2 years ago, I started to design a method to meet this requirement. So I outlined the gene editing workflow here, and we think about we optimized the step we optimized. Finally, we find the already CRISPR laboratory with the barcoding vectors and Fourier transformation may be a good choice to if we wanted to mutate hundreds or thousands of genes. So I'm going to some details about this method. The first thing, we used a new method to barcode the vectors. We call it a flash tag. Flash means PCR fragment length markers for distinguishing guide RNAs. This is very simple. Actually, flash tag is a DNA fragment with different lengths, as we show here. We have 12 vectors. Each vector have a flash tag. The flash tag have different lengths. Okay, the first one is 91 base pairs in length, and the last one is 200 base pairs. So the vectors can be, the identity of these vectors can be read out using PCR and gel electrophoresis. So here is an example of we selecting the flash tags of individual plasmid or mixed plasmids. So in either case, we could read the identity of the vectors information clearly. Yeah. So then, based on this barcoding strategy, we developed a gene pipelines for already CRISPR library construction. So in the first step, we assemble the plasmid in the barcoded vectors. Each vector have a flash tag, and so we assemble the plasmid using hash product cloning method. That means we make these vectors using 96 wire plate from cloning. After we get these plasmid, we put them in a multiple wire plate, and in this plate, each vector in one row has a unique tag. And then we mix the vector in the same row to one group. And each group have 12, this mixture only have 12 vectors. And we use these mixed agrobacteria to transfer rice. Then after we got the transgenic lines, we can use PCR and gel to find out which guide RNA or which genes we are targeted in the TCR lines. So in one word, we use the PCR and the page to read out the GA information after in all these steps. So it will save a lot of time. After we design this pipeline, we want to find a gene family to test our pipeline. So we think receptor kinase may be a good choice because it is the biggest gene family in rice. And the receptor like kinase are also important for biotic and biotic stress and development. But in rice, less than 10 RNA genes are categorized. Most of them, we don't know their function. So we use the flash pipeline to edit all the
please restrict your timing.
Oh, sorry. Okay, so I use the pipeline to make a laboratory to target all the RNA genes. So we just skip to our result. If we use a flash tag, we could take all the vectors when we mix together, and we also can read out the gene information in the TCR plant. So we did 89 transformations and generated a population with 5,000 TCR lines. These population covered 955 RK genes. So the coverage is very good. And among these genes, more than 800 genes have more than 2 independent gene entity lines. So I think they were generally useful resources for research. So I think the flash tag our pipeline we analyzed the genotype, and the mutation efficiency is reached 90%. So I think it's suitable for genetic screen or functional analysis for RK genes. So I guess I will sweep these slides here about the TD transit gene event in our laboratory. Finally, we tested we make a pilot screens about the disease-resistant genes, and we screened 40 genes and find 8 genes have changed the resistant rice blast. So I think we could use these RK mutation populations to do screening, like we want to screen the disease-related genes or stress-related genes. And so everything could find in our database. We put the mutant information here and the gene information here, and our seeds information in the database. And okay, like we give a short summaries about our already crystal library construction is flexible to edit 2 or 1,000 genes and fast, low cost, high efficient. So in my lab, one PhD student muted all these 1,000 genes in 1 year. So the speed is very fast, and we can do faster gene function discoveries using these resources. More importantly, different laboratories can easily collaborate with each other using the crystal library strategies to study the rice genes function. So, and last, I would like to thank my students, my collaborators, and my funding agencies to support my research. So I would like to show a last slide. Thanks for everyone to join, and welcome to Huazhuang University. So I have here, and I'm welcome to take any questions. Okay.
Thank you so much, Professor Kevin. Indeed, we are very much indebted for, explaining many more things inside the CRISPR-Cas and genome editing. Thank you so much. Now I request Professor Ajay Kohli, Director of Research at International Rice Research Institute. He will be talking about next-gen plant breeding technology for food security and climate change.
Sir, any questions it might be with participants? Yeah. They should write to the chat box.
Yeah. Okay, very brief, please. Yeah. 1 or 2.
I think, Madam, there is one question in the chat box. So, Kevin, would you mind taking the question directly from the chat box?
Oh, I see that. Yeah, I could answer questions by typing, so it may save some time. Yeah. So I would like to do.
No, Priya, hello. The last question to everyone. The last one.
Last one. So the CPF1 question. Yeah, I see. Under the promote so in my case, I think CPF1 is not so efficient as Cas9 in rice. So if you wanted to target the edited gene, I think Cas9 is the best choice. CPF1, the efficiency is reduced a little bit, but it still works. The advantage of CPF1 is have some big mutations, maybe a couple. If you use the U3 UBI promoter, I think U3 may be better. U3 promoter may be better, but it depends on the target site. In our experience, some token site we use the U3 is better. On other side, using the UBI promoter is better. So you need to test the different promoters. Yeah.
One more question if anybody has. Otherwise, we can go ahead.
Hi, Kevin. So I have one question, sir, if you permit me.
Yeah, please.
Yeah. Okay. So Kevin, so have you compared your PRGB 32 efficiency with 33? Means the intron approach.
The intron?
Yeah, the intron approach that you said that you express guide RNA and Cas9 using the same promoter.
Okay.
Yeah, so that PRGB 33 probably, that one.
Oh yeah, so
Yeah.
You want to compare the in intron express the GNA and the U3 express the GNA, their efficiency. Yes, we compared. Actually, we think U3 is better. U3 is better if we added multiple genes. But U3, if we use a U3 promoter, we cannot do inducible expression.
Yeah.
So, but in rice is the situation in rice. We also make some construct for white seed, the ripe seed. In ripe seed, we found the intron strategy is better. I don't know why, but we compared the intron and the U3 expressed GNAs in ripe seed. Then we found that the intron is a little better. So I guess if you can find a very efficient U6 promoter, that's okay, that's very good. But if you don't know the U3 or U6 promoter is efficient or not, you can try the intron strategy, because if you use the intron, you can use a 35S promoter or agonist promoter. That's very easy to find a +3 promoters to express intron. Is it clear or yeah?
Okay, thank you very much.
Thank you for the question.
Yeah, Dr. Kohli is now online.
Sir.
Dr. Kohli.
Sir, I would like to request you, sir, to introduce Dr. Kohli before his presentation.
I think Dr. Kohli, he was in, but let me again introduce, no problem.
Excuse me, sir. So actually, my name is Nese Srinivaslu from IRI. I'm representing Dr. Kohli. Unfortunately, he could not make it as he's traveling right now.
Okay.
So I will be presenting on behalf of him.
Okay. I think you are Dr. Srinivaslu.
That's right. Yeah.
Yeah. So I request you please to speak, because I mean, I have nothing to. So I directly request you to please go ahead and try to finish in 15 minutes. Is it possible?
Yes, Dr. Singh. I will try my best.
Go ahead, please. Go ahead.
Can you confirm whether you could see the screen, what I showed?
Yeah.
Okay, perfect. So first of all, thank you so much for this opportunity to really present IRI's recent work in terms of next generation rice breeding technologies, which has been deployed to address food security and climate change. So, I mean, we all have actually confounded with quite a number of challenges what we are facing. On one hand, we see that there is dramatic change in the climatic factors, which impacts basically the productivity. On the other hand, consumers are actually demanding higher quality as well as meeting the nutritional needs. So we have to really tackle not only just the productivity and its sustainability under the changing climates, but also we need to make sure that the varieties what we are breeding really meet the targets of grain quality as well as nutritional trials. So from that context, what has become very clear is technologies have been changing very rapidly, and the demands are also emerging, and we need to adapt. So here I would really like to quote Dr. Fred Emery, where he mentioned that instead of constantly adapting to change, why not change to be adaptive? So what it really reinforce the statement is, if we are adapting its nature, it is easy to accept the changes, and then we could really deploy the technologies what is in our hand. So how can we really apply this in case of breeding? And what has been really done quite lately here at IRRW is we are looking more into next generation breeding technologies as an interface, connecting actually the basic science, but advancing basically the downstream breeding. And we really need to come up with state-of-the-art breeding lines, meeting those emerging threats. And as a result, we really need to look into deploying very effective technologies, what is there with us. So in this regard, Dr. Hans Bharadwaj, who is actually leading the rice breeding innovation platform, he has been orchestrating really the pipelines, the breeding pipelines, particularly both the population development in terms of genomic selection pipelines, and also bringing in wherever state-of-the-art technologies are needed to tweak selected set of triads in the pre-breeding pipeline. And at the end, we really need to think about varieties what we are developing, how that could really cater the need of market demands. So that is actually a demand-driven approach, what we need to deliver. So just a brief reflection in terms of IRRW's history. Always the demands and challenges what is there on the table will really motivate us actually to think about the potential solutions. And when there was a famine in 1960, IRRW has come up with high-yielding varieties, particularly the semi-dwarf one like IR8, which really launched a green revolution. And it really saved millions from the starvation. And when we moved into 20th century, climate change becomes so apparent, and we really needed to bring in both marker-assisted selection technologies as well as triad discovery to address the changing climates like drought, salinity, submergence. So here is one example, the clone gene of sub1 introgressing into multiple mega varieties has really transformed the agriculture production in those ecologies. And as we moved into, there is also a demand in terms of changing market demands. And there is really a premium set for high quality rice varieties. And it also, the aromatic rice is one such example where jasmine and basmati from Thailand and India has really taken a predominant stage in terms of value fetching for the farmers. And we do have quite a bit of opportunity, particularly on aroma and texture. And in terms of nutrition, we have to also think about double burden or triple burden nutrition problem, like low glycemic index rice, rice with enriched antioxidant capacity, and also addressing malnutrition. So the challenges, what we are really facing is basically climate change, labor shortage, consumer demands, and imbalance between quality and quantity. So when we really look into those multidimensional factors, we cannot think of just breeding variety per triad basis. We need really a more holistic solution. And this is where one rice breeding strategies have been put in place to address these grand challenges. And a couple of examples, what I really would like to highlight here is that deploying state-of-the-art technology, we have actually identified a set of genes which addresses basically a trade-off between yield and grain quality. So traditionally, we have been really looking into the genetic gain for yield, and there has been an approach here mainly through genomic selection pipeline where we could look for the genetic gain of 1.5% to 2%. And in this particular case, we have identified a gene called OSTPR, which balances basically between yield and quality, and we were able to overcome the trade-off with quality. And the second example, in the triad space, we also have identified an exerted stigma, particularly from the wild rice. When we have actually the missing alleles in the main breeding pool, we look towards bringing in the rare alleles from wild rice or any other diversity pools. This exerted stigma is an example where we have introgressed from one of the wild rice germplasm, and that has created long stigma phenotype, and we are currently testing for higher outcrossing, which could be beneficial for hybrid rice production. Likewise, in the space of disease tolerance like BPH, bacterial blight, where IRRI has deployed CRISPR technologies by targeting sweet genes, and they have developed quite a number of interesting lines which are resistant to bacterial blight disease. In the space of nutrition, we have actually identified a set of novel genes to tweak actually the quality of amylose, amylopectin composition and addressing the dietary fiber. Thereby, we have reduced the glycemic index in its nature to low or even ultra low GI. And also we are looking at mainstreaming really the micronutrients such as zinc. And initially that was mainly screened through phenotyping measures with XRF as well as with the ICP OAS technologies. But now we have been really mainstreaming this through genomic selection pipeline. And for the climate change, when we move forward, when we produce enough rice, we also really need to think about environment, and particularly mitigating the methane emission will be an important strategy. And currently IRRI is putting in place the mechanisms around to address this set of triads. And in breeding, what is really important is it's all about selections, right? So traditionally we have been looking through either phenotyping technologies or through novel technologies for which aid in selections. And then we continue really to enrich the rare alleles in the breeding programs, and then the population development strategies could be taken forward. And here is an example where CRISPR technology has been deployed, particularly to address the nitrogen remobilization mechanisms, particularly through this GDA1 target gene. And also by targeting the star structure alterations in the glycosylation sites, the glycemic index and star structure composition has been manipulated. And also through CRISPR and transgenic technologies, basically IRRI has developed high iron and high zinc rice, where zinc reaches more than 30 ppm, and iron actually meets the daily requirement criteria. And these are the specific sets of examples what we could really deploy in terms of precision breeding targets through CRISPR engineering. And when we really move into one rice breeding strategy, what we are really looking is we are looking at what are the demands in terms of markets, and based on the foresight information, we have been identifying basically the demand-driven approach and the target environment where breeding products has to be derived. And then we have been setting up actually the core collections in the breeding pipeline, which really meets the quality criteria, nutritional criteria, and looking into the genetic gain for yield and stress tolerance. And then through rapid generation advancement technology, we could really fast track the population development, and then we could really deploy the market development technologies and go for the selections. And then by working very closely with the national partners, we are now targeting to test this material in the target environments, conducting observational yield trials and advanced yield trials, and also coordinating with the national system to conduct national testing systems to really check about the performance of these varieties. Any best varieties which are coming out, we will stage that in for the on-farm trials, and we could really demonstrate the value to the value chain stakeholders in rice. And this kind of a strategy, on one hand, really will help us really to address multiple grand challenges what we have seen That could be done through genomic selection and combining the speed breeding technologies through one rice breeding deployment strategies. And mechanization is really a problem. The labor is a problem. So we really need to think about mechanization. And IRRI has been conceptualizing about the direct seeded rice breeding and also testing the best practices for the DSR breeding technologies. And wherever we really need entry point for the hybrids, it is also looking at tool and hybrid production. And I gave you a couple of examples about how we can really tap into wild rice to identify important rare alleles and bring that in case of long stigma or disease resistance examples. So moving forward, we really need to think about a bigger picture, that's land, water, energy nexus. And in this particular scenario, we really need to combine the technology. I extensively talked about the technology in breeding, what we are deploying, but together with our partners and with other departments, we have been really looking into deploying geospatial technologies, combining with site-specific nutrient management, fallow farming, and diversification. So these combinations of technologies will really help us to move into rice-based system. And of course, we have to keep in mind that climate change scenarios like methane emission has to be addressed. And there is an ambition really to create actually the methane emission maps in the rice growing areas so that we can come up with policies and then we can deploy the material what we have been developing and come up with effective dissemination strategies. And there, IRRI, together with partners, have developed this seedcast, the database, which will really help us to penetrate important material in the seed chain. So while addressing these, there are these 5D driven, technologies needs to be put in place in a circular fashion. First, we have to identify basically the demands from the markets. And then we have to really put in technologies for the gene discovery and doing basic science. And then combine that for developing important breeding materials, that's novel varieties. And then how do we really disseminate in the target regions and then test the best outcome material and then link it to the policy and then take that forward towards markets. So this kind of a circular approach will definitely help us to overcome those grand challenges. And particularly such technologies were possible at IRRI with stalwarts like Gurudev Kush, who have immensely contributed about making the green revolution, addressing yield and quality. And now with the latest leadership of Dr. Hans, we are now really putting into combining state-of-the-art technology to improve rice breeding. So again, this would be possible to implement only with the partnership, and we really look forward to work very closely with Indian partners to make this happen. Again, thanks a lot. So I will stop it over there, and if there are any questions, I would be happy to take them. Thank you. So Dr. Singh, can you hear me?
May I request to our audience, anyone who would like to speak, raise some question, maybe one or two. Anyone, please?
Sir, one question.
Yeah, please.
From Devaspita Panda. Could you please explain that how OSGDA1 is effective for nitrogen metabolism?
Right. So basically this GDA1 is actually the target gene, which is involved in this, the methylation targets. And what has been really done is the methionine metabolism has been manipulated, and that actually helps to support in terms of effective remobilization of nitrogen. So currently, the target transgenic lines, what has been generated, it exhibited basically higher root biomass. And also there is this sourcing coordination happening, which also increases basically the panicle branching.
Yeah, anyone else, please? If not, then thank you so much, Dr. Srinivasalu. I hope that people may, I mean, by mail also, they can just have some interaction in future if anything is there.
Sure,
thank you so much again. Now I request Professor Wang. Dr. Wang, he is a professor from China National Rice Research Institute and Vice Director of the State Key Lab of the Rice Biology. He received his bachelor degree of the agronomy from Yangzhou University, China in 2004 and PhD of Science from Institute of Genetics and Developmental Biology of Chinese Academy of Science in 2009. His career research is mainly focused on two topics. The one that is developing novel genome editing system and applying the system for both basic research and crop improvement. Developing a strategy to fix heterosis in crops. I think this is very challenging topic to fix heterosis. But somehow or other, if this dream could be fulfilled, I do believe that coming green revolution from the rice, it will be accomplished if at all we are able to fix heterosis in crops, maybe especially in rice and wheat. I request Professor Wang for his very limited, because he is a very renowned and acclaimed scientist. So I request Professor Wang for his talk. Please, Dr. Wang, please go ahead.
Hello, everyone. Can you hear me and see the slides? My slides?
Yes, everything is okay.
Yes. Yeah, it's there.
Okay. First of all, I would like to thank Dr. Sim for your introduction, and then thank the organizing community for giving me the opportunity to report our work. Today, I will talk about establishment of POMEX in hybrid rice. As we all know, heterosis is a phenomenon that in the first generation display increased vigor compared with the homozygous parents. Heterosis has been widely applied in agriculture and plays an important role in increasing yield, improving quality, and enhancing stress and resistance in many crops. For example, in maize, in sorghum and tomato and rice. For example, in this picture, this is the hybrid. It grows much higher and much more seeds than the homozygous parents. This is the first generation, but in the second generation, we can see from this picture, and the heterosis will be lost because of genetic segregation. So if you want to use hybrid plants, yearly hybrid seed production is essential. In this picture, the farmers are using traditional methods to produce hybrid seeds. This process is very tedious and increases the seed cost and prohibits heterosis application in many crops. For example, heterosis has not been used in wheat and soybean. In last century, many scientists proposed to fix heterosis by introduction of apomixis. In this strategy, this is a normal plants. It undergoes sexual reproduction. We undergo segregation. But in apomixis, the hydrolysis will be preserved in each generation. Then what is apomixis? Apomixis is an asexual reproductive strategy that has been found in more than 400 plants, including some common fruits such as apple and citrus. In most cases, the plants can produce both normal seeds via sexual reproduction and clonal seeds via apomixis. Due to its great potential in fixing hydrolysis, many scientists argue that apomixis could revolutionize agriculture, and apomixis is considered to be plant breeder's dream. 20 or 30 years ago, apomixis study is very popular, and everyone talks about apomixis at that time. Many projects were funded to develop apomixis in crops, but because apomixis is very complex and it remained largely unsuccessful. Apomixis can be classified into two major types: sporophytic and gametophytic apomixis. Also, the embryo develops from different cells. Both types generate clonal seeds without meiosis and double fertilization. Here we propose a strategy to achieve apomixis. The left picture is showing normal sexual reproduction. The red line and then the blue line indicates the homologous chromosome from parent to parents. During meiosis, the homologous will undergo recombination during meiosis and produce haploid gametes. After fertilization, the diploid and recombinant inbred embryo will be generated. And the right picture is our post-synthetic apomixis. You can see from the first they include two essential steps. Step one, bypass meiosis and produce clonal diploid gametes. Step two is bypass normal fertilization and then resulting in parthenogenesis of the egg cell. And by combining both steps together, theoretically, the hybrid will produce clonal seeds or clonal plant. Normally, homozygous varieties are used for rice study, but when it comes to apomixis study, homozygous plants may not be the best choice because we can't determine whether seed is clone or not. So before our study, we screened more than 20 hybrid varieties and found a hybrid variety that easy for genetic transformation in the genome editing. So we choose it as our model variety. This is the hybrid, and this is 3 lines that used to produce a hybrid plant. In the past 10 years, our lab did a lot of work to reviewing the mechanism of meiosis. Also, we did a lot of work to try to optimize the multiplex genome editing system, which is important for the for crop improvement. And we then tested the feasibility of the strategy I mentioned about. The first step, production of clonal and diploid gametes. In 2009, Lafayette from France developed a strategy to turn meiosis into mitosis in allelopathosis. Mutation of OSD1 and OSD1 punishes meiotic recombination, and mutation of recreatin will cause the separation of sister chromates after the first meiotic division. Both SPOI11 and replicator mutants and are stereo. Mutation of OSD1 abolished in the second cell division. By all combine the 3 mutants together, and the meiosis can be turned into a mitosis. And the triple mutant will only generate clonal gametes, leading to the doubling of the protein after each generation. The 3 genes was selected. We also select in rice and choose the 3 genes used for our for genome editing. After that, it means OSD1 and the pair 1, which is similar to SPOI11 and replicator. And after DNA sequence, genome editing and the DNA sequencing, we found and get the triple mutants meiosis instead of, we named the mutant mitosis instead of meiosis, Miami for short. We identified and used it for our analysis. This is this picture, and the first, this is the white type. You see why at the point it's a hybrid. In the meiosis, in the white type, white hybrid, in the meiosis, you can hear 24 chromosomes will undergo a normal pairing and the recombination. Here you can do 12 pairs. After 2 rounds of cell division, so we have produced diads. Diads is here, you can see from here. And but in the I'm sorry, it's in Miami, no pairing will happen, and it will undergo only 1 round cell division. This will produce diads. This is a tetrad. This diads. And to determine whether the diploid gametes were produced, we conducted fixed experiments. In this, the blue signals indicates the DNA, and then the red signals indicates the 5S rDNA that located on the 11th chromosome of rice. You can see from the normal gametes of white type, you can see only 1 5S signal in each gamete. But in Miami, you can see from here, there are 2 signals. From this result indicates that the clonal and diploid gametes are generated in Miami haploid. And we next investigated the fertility of the single mutant. First is the single mutant. This is a replicator mutant, and this pair 1 mutant. And this is the panicle. You can see from here. There are no seeds were produced. This is the white type. And this is the triple mutant. You can see from here. The triple mutant is very similar to the white type. It can produce seeds normally, which is very close to. We cannot tell the difference from it from the white type. This phenotype is different from previous study in homozygous varieties, such as in the background might affect the fertility. And next, with the other seeds of the Miami were planted in the field. We can see from this picture that this is the upstream of white type, and this is the upstream of the Miami. You can see from here the panicle. You can see. This is Miami. It shows increased grain size and elongated all lengths. All of phenotype are typical characteristics of tetraploid rice. The ploidy of the plants were investigated. You can see from all the, this is the progeny of white type. It's all of them, all the spleen are diploid, but the progeny of Miami, you can see and all the plants were tetraploid. Next, we developed 10 indoor mice that are on chromosome 1 and chromosome 8 and determine the genotype. The blue and the red colors indicate the genotype of the C84 and the 16A. But then the hybrid it will displayed yellow color. It means it's heterozygous. And we found that all the plants of the progeny of Miami, we found that all locals it displayed yellow colors. It means it retained the heterozygous genotype, and no recombination will occurred in the plants. This is the first step. Next, we test the feasibility of the second step, induction of parthenogenesis. Because the induction of parthenogenesis is hard to observe directly. We therefore try to screen the methods to induce haploids. Till now, there are 3 strategies that have been reported in plants to introduce parthenogenesis of haploid. So first strategy that developed in Arabidopsis and centromere-mediated general elimination strategy was first reported in Arabidopsis. It was developed about 10 years ago. And another two. The second strategy is found that ectopic expression of baby boom gene can induce parthenogenesis in maize in rice. And the third strategy that it was first found in maize, and 3 groups reported that a mutation of MTO or PL in maize can trigger haploid induction in maize. We test the first strategy but failed in rice. Between the second and the third strategy, we choose the third one because it can be achieved by simple genome editing. By screening the genome of rice, we found an MTL gene in rice. Therefore we edited the MTL gene in hybrid rice and to test its feasibility to induce haploid. We found that this is the wild type. This is the MTL single mutant. We found that the mutant grows normally during vegetative stage, but the number of seeds decreased significantly compared with the wild type. It can only produce that about 11%. We harvested all the MTL seeds and 12 indoor marks on each chromosome were developed to determine the genotype of the offspring during normal sexual reproduction. Because of the occurrence of recombination and fertilization, the theoretical frequency of homozygous recombined inbred diploid is pretty low. Is about 0.024%. Is pretty low, and in most cases we can always found the heterozygous genotype. But in some plants of MTL, we can find that all markers are homozygous at all loci, indicating that those plants might be undergo parthenogenesis. Next, the plurality of those plants were investigated using flow cytometry. Of them, of 11 plants, 9 plants are found to be haploid plants, and then 2 plants were found to be double haploid. those plants grow normally, but in the haploid plants, it shows the dwarf and the sterile phenotype. Next, the whole genome of those plants were and parent plants were resequenced. The red and the blue colors indicate the two parents respectively. Yellow colors shows heterozygous F1 hybrid. By informatical analysis and revealed that the yellow colors are always observed in recombinant inbred and diploid yellow colors, besides blue and the red colors. But in the haploid or double haploid plants, only blue and blue and red colors can be observed, and we can't find any yellow colors. Together, those results indicate that those plants are generated from one parent that from the egg cell. We then tested the feasibility of the two steps together, and combine the two steps together, and want to if their apomorphism can be occur. We want to know. We by simultaneously editing 4 genes, we just used both MTOS-D1, pair1, and RECATE. In CY84, we obtained 3 plants containing mutation on all those 4 genes. The mutants were named fixation of hybrids, fix for short. The meiotic chromosome behavior of fix were also investigated, and we found that it displayed also undergo cell division like that of Miami, that like mitosis. And the fixed mutants were grow in the fields, and found that it grows normally during vegetative stage, but the seeding set, we also found that its seeding set is much lower. It's about only 40.5% seeding set. It's pretty low. And we harvest all the seeds and tested those seeds. We gluted them. All seeds we found among of 149 plants of spring plants, we found that most of them displayed and are tetraploid by flow cytometry. But the remaining 7 plants we found to be diploid plants. And all those plants, both diploid and tetraploid plants, were sequenced by whole genome sequencing. We found that we found all the markers about more than 10,000 snipper marks. We found all those markers are heterozygous. It's as same as that of CY84, the first generation of hybrid, and the next generation, the next diploid and tetraploid, and next diploid plants, all of them are yellow colors. It means that the seeds are clonal seed, a clonal of the mother plants.
Yeah, please.
As those seeds are clonal seeds, it's very important to know whether fixed genotype can inherit to the next generation. In winter, the clonal plants are grown in greenhouse and tissues tiller. But when they grow in fields, we found that grows as same as that of the white, except it displayed low seeding rate. Those results suggest that clonophytes can keep the capability to produce clonal seeds by self-fertilization. Those plants will those plants are growing in different years, and next in each year we retain some seeds and grow them in the same field. We found that when they grow in the same field, it displays the very similar phenotype, and also very similar to the Y type, except the seeding set. And then the fixed plant were also very similar to each other. We also compare the plant and panic morphology of tetraploids from different generations, and this is tetraploid. We can found that it's a very same. Tetraploid is also very similar to each other, and then the seeding rate is also very low. Next, we also investigated the expression of the, and also the DNA methylation. We also found that different plants of different generation is very similar to each other. That means item can remain stable in each generation after it. Now, our working improves the feasibility of apomixism in hybrid rice. Now we are trying to, but it is still some questions remain to resolve, especially the seeding rate. Seeding rate is low, and the haploid frequency and is very low. Now we are trying to looking for the germ present or genes that increase the seeding rate and haploid frequency. And we want to clone more genes involved in parthenogenesis, which is very important to improve the thing and the system. Now, also we are, because most of the genes are very conserved among crops, so also we are trying to testing the strategy in other crops, for example, maize. Last, I would like to thank the collaborators, Rafael Moshe and Juquan and Mingguo for meiosis study, also the materials, also the lab members from my lab, and then the funding support. Also, this is my lab. Also, I thank you very much for your listening.
Thank you so much, Professor Wang. Indeed, it's a very, illuminating talk. And only one or two quick questions, please.
Sir, Professor Wang, it was an excited presentation. From my side, whenever you are editing that MTL1 gene, you have achieved 2 double haploid and 9 haploids, you are telling. Then double haploids, whatever that is spontaneous doubling in nature, it is taking place, or how you have got?
I'm sorry, I cannot hear clearly.
That when you are editing that MTL1 gene, that haploid inducer line, that haploid induction system you are developing, you have shown that you have got 11 plants where that
11 plants.
2 are DH, double haploids, and 9 are haploids. Then that DH, is it through spontaneous doubling or any other this thing in nature? I don't understand actually.
Because among the 11 plants, 2 are diploid and the 9 were haploid. Okay. Why? And we think that it can normally produce a haploid first, but in some cases, the haploid will undergo doubling, or without any treatment. This is also found not only in rice, but also it was found in other crops. For example, in maize, it can undergo doubling without any treatment because it in haploid might affect its normal growth. So in some the doubling occurred in very low frequency. It will undergo a doubling. So actually, the exact mechanism remain unknown. But if we were treated with some in some cases, it will undergo doubling.
No, that's you are utilizing that antibiotic agents like colchicine for double haploid production.
What?
You are utilizing colchicine, that antibiotic agents that for doubling of the haploids.
Double haploids, yeah.
For doubling of the haploids, you are using any that colchicine. You are utilizing colchicine for doubling the chromosomes in haploids. Whatever haploids you are getting.
I'm sorry, I'm not can hear clearly.
Okay. I will interrupt through your mail because I am working in the androgenesis, this double haploid also in haploid induction system. I will write a mail to you. Okay.
Through mail.
Okay. Thank you.
Through mail, anyone can interact with him, and then he will.
Thank you very much.
Okay. Thank you very much.
Thank you, Professor Wang, for your good talk, and we dream that this epomixis will come true at sometime in future. Now I request Professor Sergey Sabala from the University of Tasmania, Australia. Professor Sergey is a head of the stress physiology laboratory at the University of Tasmania. He also holds a distinguished professorship and a director of the International Research Center for Environmental Membrane Biology at Fosun University in China. His area of expertise in plant stress physiology and mechanism of their adaptation to harsh environmental conditions, such as drought, salinity, waterlogging, with specific focus on halophyte. Over his research career, Professor Sergey has published more than 360 peer-reviewed papers and successfully supervised 42 PhD students. He is also an ISI highly cited research during the last 5 consecutive years. He was ranked as the most cited researcher in the field of botany in the world in 2019. His H-index, that is 93, and his work has been cited over about 30,000 times. So I request Professor Sabala for your talk, because stress physiology, I do believe that it's a really very challenging. Stress is the most challenging compared to even, biotic stress. So I request you that those who are participating in this one, they will be very much benefited with their talk. Now, without taking time, I request Professor Sabala to please give your talk, please.
Thank you for introduction, and I hope you can see my slides.
Yes, it's visible, Sergey.
Okay, great.
Yeah, you can make it a full screen.
Look, I cannot, because for some reasons I'm trying to press it here and it does not. Okay, yeah, that's now, yeah.
Yeah, it's fine now.
Yeah, I'll be talking about physiology today, so sorry for you guys for mostly geneticists here. And I also will challenge some of the classical concepts of phenotyping, because I believe this is now the narrowest part. We have all these very nice molecular tools which allow us to do basically whatever we like with the genomes and structure of proteins and the numbers and quantities, but we still limited pretty much like a bottleneck of what to look for. And again, my apology, I'll be using mainly barley as an example. I'll show 1 or 2 slides on rice because the focus of my lab was on cereals in general, and only 3 or 4 last years I started actively working on rice. So papers are still coming in large quantities, but not really as much as we have in the last 10, 15 years. So abiotic stresses in general, I will probably skip this slide. We all know that it's become more extreme. So we have drought, we have flooding very often in the same place, just different times of the year. We have the gradually increasing number of these catastrophic climate events. And predictions are really, they're not going to disappear. It's already cost $180 billion in lost production and is only going to increase due to the current trends in global climate change. That has very major implication for global food security. Once again, I'll probably skip the details here, but what I want to emphasize here, this is a very nice paper published about 10 years ago by Mark Tester and Peter Langridge. And what they did, they analyzed the total production of cereals in the world, including rice, and the blue one is really what was going for 50 years. And the red one here is what is needed to meet the global demand for food for population. So if we extrapolate the business as usual, so the current agronomy breeding practices, we continue as we've been doing for the last 50 years, we will end up somewhere here. And this is where we should be. And I want to tell that by that time, we expected that will be 9.3 billion people in the world. And now the number changed to 9.9. So we have a huge gap. Actually, the line will be somewhere here. So we really have a huge gap, and it's not really achievable with food security by existing practices. So we need to shift the paradigm of breeding and agronomy, or both of them, to something which will be outside the square and not going for traditional things. And what I'm trying to do may be slightly controversial, but I think I have pretty strong supportive arguments for the phenotyping things. So this is a very classical way, which you already listened in many talks, how we do. So we just pick up something interesting in extreme field, some interesting germplasm. We go through the selection of promising varieties in the fields, and we use the marker-assisted selection-based integration of desirable things. And we usually phenotype plants at the whole plant level. You can do it in these lamina-like conveyor belts and things which are very popular around the world. You can use the drones, you can use different types of things. And it's all nice and it's all working for the traits which are relatively simple, just a few genes. So if you're interested in plants which is greener or taller or different leaf angle, or something related to the quality where it's 1 or 2 genes in a biochemical or developmental pathways which can be modified, that's all working nice. When you talk about more complex traits such as stress tolerance, specifically salinity and waterlogging and drought tolerance, this phenotyping fails to work because the function of 1 or 2 or 3 genes which are really important for trait are really shaded by others. So you have the mix of different things. So it's largely really empirical trial and error method. And people use screening methods based on convenience, like there's a need for few thousand plants screened per day. So people decided to do things which are easier to achieve to match these numbers. It's not necessarily the best traits that they're doing. So this approach also comes with undesirable traits because you really introduce some things, some genes, you have pleiotropy, because not everything you transfer is good, but unfortunately, there's a negative perception of the genetic engineering. So CRISPs offer much better approach, but still you really need to know how the gene operates in plants. And with whole plant phenotyping, you cannot do it. You look at the overall effect of 20 or 50 or 100 genes, and you really don't know which one making a major contribution. You just see that your plants are better looking, but you cannot explain which genes doing that. Salinity tolerance is really polygenic, and it's conferred by at least 10 major physiological traits. Each of them probably rely on operation of 3 or 4 or 5 genes. So we're talking about hundreds of genes which make a difference. And practical implementation of that in breeding programs is very difficult, particularly because we don't really know where it's operating. So the biggest problem from my point of view as physiologist is that the whole plant phenotyping, which is the most popular these days, fails to account for tissue and cell-specific gene operation. To give you an example of salinity, this is one paper on rice from Tim Flower's lab years and years ago. Again, salinity is a big issue, costs money, but we still don't have the tolerant varieties, which will be even halfway close to halophytes, salt-loving plants. And explanation is very simple. When you do the QTL mapping and you look at the sodium exclusion traits, which was targeted by breeders as a major one, you will see that it's really pretty widely distributed on 4 different chromosomes in different regions. So really, it's really not just one nice and sharp pick. You have multiple genes just spread across the genome of plants. So that means it's really nearly impossible to recommend which ones should be targeted. And again, this technique completely fails to account for tissue-specific location or cell-specific location. If sodium is in a vacuole, as in halophytes, it's safe and sodium quantity doesn't matter. But if it's in a cytosol, even a smaller quantity can kill plants. And whole plant phenotyping, whole plant shoot or root sodium analysis, nutrient analysis, does not deliver that. To give you again another example how this approach largely fails, I use a paper from my colleagues from Adelaide. So Rainer Mans and the people in the University of Adelaide published a very nice paper in Nature Biotechnology. One of their few things which went as far as a field. What they did, they looked at the HKT15 gene from wild ancestor of the durum wheat, and they look at the QTL and they overexpress it in elite varieties, and they did field trials, did lab trials, did some experiments, and they reported 25% increase under saline conditions. That's all nice, and it's Nature paper. It's one of the best examples of breeding in wheat for salt tolerance. However, when you start to analyze the actual numbers here, and this is a table from the same paper, you can see that there is no difference in 2 field sites between the Tamaroi and this modified plant harboring this HKT15 gene, which is really operate in removal sodium from the xylem back in the root. So you see there is no difference in 2 field sites out of 3. And indeed, we have 25% increase in a yield in transformed plants in one severe site where salinity was really high. The problem is that it's still 50% loss of the control, 3.2 versus 1.6. So we still have 50% yield loss. It's not really the major improvement, so farmers can be happy. So we are not really a step closer to achieve the tolerance known in halophytes. And this is Salicornia, which grows in a double seawater, and it's looked pretty happy to me. So I'm advocating for the whole plant phenotyping, and it's really all will account for this tissue-specific expression of genes. So Jose Dineni published a very nice paper years and years ago in Science showing there are hundreds and thousands of genes which are expressed in a highly cell-specific manner in different root tissues. So we need really to account for that, and we need really to find the most critical genes, where they are operating, what they're encoding and operating, and later use the QTL approach for making the pyramid of these genes. So there's not a single gene for abiotic stress tolerance, and we need to go for 5, 6, maybe 10, the most important. So it should be hypothesis-driven approach, and it should rely really on the techniques which understand and quantify operation of specific transporter proteins in planta in a specific cells. So I'm advocating essentially electrophysiology and fluorescence imaging as tools. And in the second part of my talk, I will really give you examples of that. So the major tool in my lab is a MIFE technique for non-invasive ion flux measurements, which is really the very nice and elegant technique, which allows you to count number of ions crossing membrane. So you can pick up one of the ionophores, which are commercially available from major companies like Sigma. It can be sodium, can be potassium, can be zinc, can be ammonium, can be nitrate, can be lead. You just name it, whatever is available. And basically what you measure the concentration gradient around the root by moving electrodes up and down, all computerized, and you count the number of ions and express a flux of ion in a nanomoles per square meter per second. So in lay terms, you count the number of ions crossing membrane per surface area per second. And we applied this technique for a variety of different purposes. What I want you to show is examples of application to salt stress. Years and years ago, PhD student in my lab, who's now Dean in Western Sydney University, Zhonghua Chen,
applied this. He was my PhD student. He applied this approach to study salinity tolerance in barley. And what we found that when you do the glasshouse experiments, you grow your plants. This is tolerant variety treated with 300 millimolar sodium chloride, not much difference from control. And this is sensitive variety, which will be dead in a few days. This is a result of 1.5 months of treatment in glasshouse. But if you use 3-day-old seedlings and you apply the MIFE technique, you can really see the difference between the tolerant and sensitive varieties. Sensitive varieties lose much more potassium, 6-fold more compared with tolerant ones. And when you do the crosses between them, like you see really that the crosses with the tolerant and tolerant remain tolerant, and crosses between sensitive and sensitive, F1 is still sensitive. So we have, in our words, we have very nice proxy. You don't have to do 2 months long experiment. You can grow your plants for 2 or 3 days in Petri dish and bring it in a lab, put in a MIFE system and measure flux for 20-30 minutes, and you'll see the difference, and you'll see, you can predict which variety will be tolerant. That has very strong scientific foundation because high systolic potassium is essential to prevent the programmed self-death. So varieties which are losing potassium, like these two here, they are really going through the PCD, and the roots are dying and plants are dying as well. So we did large-scale validation, and indeed it was very nice correlation. So 60% of genetic variability in salinity tolerance in barley was really explained by the ability of roots to retain potassium. So he spent 2 years or 2 seasons in a glasshouse screening 70 varieties, and he did that in 1 month in a lab. The same results, all very nice. We start to look at how we can quantify the tissue tolerance traits, and really this is a vacuolar sodium sequestration, which is conferred by the exchanger called NHX, which pumps sodium in vacuole. And we showed that if you use a Corona sodium green dye, you can really profile distribution between cytosol and vacuole, and difference between sensitive and tolerant varieties can be easily predicted. Again, it's relatively fast. I would not say it's super fast, but you can still do dozens, if not hundreds of varieties per day if you get it automated. So there's a possibility for that as a tool. So we further apply MIFE to screen for the donors of the SOS1 exchanger. So this is a very famous protein discovered by Zhang Kanjun, which is really pumps. So when sodium comes into a plant through one of transporters, either non-selective channel HKT, 95% of sodium is pumped back by this protein. So this is an example of screening. We develop protocols. So we look at some varieties and see when we put them after salt treatment into no salt solution, how much they're pumping out. We see that this one is only 300. So this is really low source activity. This one is 600. This one is over 1,000. So these varieties can be used as plants with high source activity. If you do the DH lines between these ones and these ones, you got really the possibility to look for QTL for source one. Again, it's not really that high throughput, but we still can do 30, 40, 50 plants per day, maybe with this protocol, maybe even 60, 70. So it's not that bad. It's not really as efficient as field screening with drones, but nonetheless, we're talking about operation of specific protein. And I can tell you, it will be just one very sharp QTL, not the distributed chromosomes. Why it's important to look at the tissue specificity, because if you look at different root zones, you'll see that the profiles of sodium are very, very different here. In mature zone, there's no doubt most of the sodium numbers here are the relative signal values. So highest concentration vacuole in a tolerant group compared with sensitive one. And in cytosol, it's 3 times less. But when you look at the meristem, it's the other way around. Tolerant plants have much more sodium in its meristem because meristem operates as salt sensor. So plants which have rapid accumulation of sodium here send a signal to a shoot for osmotic adjustment and tissue tolerance. So the whole plant root analysis for sodium is useless because it does not account for the specificity of different tissues. We also look at the RS stress because salt and drought comes with production of rectified species. We explain difference between the apex and mature zones, and one of my students from China, Yang Wang, just look at the barley, durum, and red wheat, and she showed very nice correlation between the magnitude of RS-induced potassium and calcium fluxes and overall salt tolerance in plants. And later she used the double haploid lines for barley, and she found 2 peaks on chromosome 2 and 7 for both fluxes, which were responsible for this oxidative stress tolerance, which correlated with salt stress tolerance later on. So we are now trying to understand what these genes are doing specifically. Finally, come to rice. So here is an example how the same approach can be used for rice screening. So we have 3 different varieties here: tolerant, sensitive, and intermediate one. And if you look at the results, this is response to oxidative stress. You put hydrogen peroxide. This is tolerant variety. This is sensitive one. 3 times more loss of potassium. And this is response to sodium chloride. Again, the sensitive variety here, tolerant here. You see the 2 to 3-fold difference in responses. So we can screen cereals, rice, wheat, barley by MAF technique. And again, here, these are big plants, but these experiments done only on a 2 or 3 day old seedlings. You don't really need a lot of space and human power. Last few slides related to waterlogging. So here we talk about the essential role of membrane potential. The problem with waterlogging is anoxic conditions. So all the transporters which require energy of ATP pump stop functioning because we have not enough ATP produced by mitochondria. So membrane is depolarized, normally from 120 millivolt to probably as low as -60, -50. One of my Pakistani students who worked in my lab and now my postdoc, he did measure membrane potential in DH lines. So essentially what you're doing, you're impaling the electrode in a root cell and you record it. And what he did, he looked at the profile and distribution of the membrane potential between the 2 DH lines, 2 DH lines in barley. And what he found just one very nice QTL peak, which was coincided with the overall salinity tolerance in there. What was interesting really was that none of the HTTP subunits was in close location of that. So it's one of the kinases, which probably control a proton pump. So we are looking at that now, but it's not really related to structural things. So to wrap up my last slide, I believe that cells-based phenotyping offer a unique advantage of narrowing QTLs and avoid pleiotropic effects. In fact, we're talking about one protein, its operation. So one protein should give just one QTL peak because it's just one-to-one things. One protein, one QTL principle. And it can be applied, I'll give you 2 examples of salinity and waterlogging, but believe me, it can be applied and we already done it to a variety of stresses: drought, heat, cold, frost, acidity, aluminum toxicity, heavy metal toxicity, nutrient use efficiency, anything. You just name it. It's just the concept in general that we stop looking at the whole plant and we try to quantify operation of transporter in planter, because you might have enough transcriptional increase by 10, 20-fold, but if the protein is misfolded, it's not functional. And you cannot tell it by this. And when you look at how big, how tall is a plant or how green is a plant, it's also a problem because it may be not because of the gene you believe you did, but because of feedback response of the organism. So what we are suggesting here with these cell-based phenotyping platforms, we can really quantify operation of protein, and later we can be sure that what we did with these genes is right. We can overexpress it, we can upregulate it, and we can see that it's working in reality. So later on, you just probably painfully slow, but pyramid these genes one onto another one, and you get the ideotype, which will be suited for conditions. Thank you for your attention, and thank you to all these people which have shown on a screen, which really make a contribution to this work over the years. Thank you.
Thank you, Professor Sergey, for your excellent presentation on cell-based phenotyping in relation to abiotic stress, particularly to salinity and waterlogging. And I hope our scientists must have enriched the knowledge on this area, and also that your knowledge definitely it will be utilized for their future program, like physiological aspects. Like, thank you, Professor Sek.
Thank you.
Any question from any side?
Yeah. Yes, madam. Shall I?
Can I ask you a question?
Yeah.
I'm Krishnendu Chattopadhyay, plant breeder. Sir, it is a nice talk, and I'm actually working in salinity breeding aspect, and along with Dr. Kaushik, he got your training. So we are basically doing the work in collaboration. And actually we have found some of the genotypes which are having variation in exclusion mechanism. Some of the land races which are Pokali type, which showing the clear-cut exclusion in the root level. But some of the genotypes which are showing the similar kind of uptake for sodium and as well as potassium at the same time. So we also discuss about this, that there are different type of transporters which are working in the different genotypes actively. So what is your observation in this particular aspect first? And second one, because of this tolerance in the seedling stage, we have found that some of the genotypes which are showing highly tolerance in even 12 or 14 decisiemens per meter, these are not working in the reproductive or in the flowering stage. So they are giving very less yield, even the low yielder tolerant genotype. For example, one Pokali accession we found, which is showing the similar kind of tolerance in seedling and reproductive stage. But this is very low yielder. This is a problem. That's why it is very difficult to transfer this character to the high yielding background. So what is your views in these two matters?
Okay, I'll try to be brief because these are very good questions, but the detailed answer require a lot of time. We just have a paper accepted 2 days ago in Molecular Plant, where we advocate for the essentially halophytism of the crops as the future prospect for salt tolerance. I think it's already online, at least I've seen there, sort of not Gallup approved, but something like that. So if you just search for the most recent accepted papers, you'll find that. So what we are saying that the approach one suit fits all or horses for courses should be really kept in mind. So one suit fits everyone, one size fits everyone, does not applicable for salinity. If the stress is mild or moderate, some plants, and we talk about the annual plants, some plants can deal with sodium exclusion because this way they will not need to do much else. And that's relatively straightforward. Just the question is exclusion from the shoot or exclusion from root uptake. These are two different things which are confused in literature. If the stress becomes more severe, using sodium as a cheapest modicum comes with higher energy efficiency compared with pumping it out, because when your salinity is high, you got in futile cycle. You pump sodium out by the source one and it's keep returning back. You cannot close all these channels. So under these scenarios, it makes sense for plants to take sodium, transport it to a shoot, but sequester it in vacuole safely. And the problem with vacuole sequestration is that everyone is looking at NHX transporter, but no one looking at the back leak through the slow and fast vacuolar channels. And that's the problem with that. So you really need to complement, you need to have at least 4 different genes overexpressed in mesophyll cells to get the sodium sequestration working. That explains why sometimes in some varieties you have just a lucky combination of genes, everything is in place, and in some you don't have it. Again, I'm very happy to communicate with you by emails and sort of send you reprints and point out to the right direction.
Thank you, sir.
Yeah. Madam, may I ask a question? Yeah. Hi, Sergey. First of all, nice talk and seeing you after a long time, and also the Wellington Mountain in the backdrop.
Yes.
Yeah. So I was following your some of your recent publications for last 3-4 years. You are also working on the halophytic rice species, what is the Quacktata. So yes. I would specifically like to know what are the traits you can suggest, so which can be transferred from Quacktata to our cultivated background, so that we can improve the salt tolerance of our sativa lines.
Yeah. Look, Kaushik, my dream is to modify trichomes for secretory function. So Kirk-Tata is famous and a nice model system because it has these microhairs and which can really secrete the salt. There are a few other things, but that's a major one. And obviously, trichomes are present in every plant. It's present in Rhiza sativa, present in every plant. The problem is that they simply not operate for sodium inclusion in them. So what you need to do is ideally is to look at the, and this will be HKT1. So in a quinoa and in Kirk-Tata, HKT1 operate as very selective sodium channel, right? So nothing to do with the name, high-affinity potassium transporter. It's sodium channel. It's more selective in quinoa than the mammalian sodium channels. So all you need is HKT1, HAG5, and I think one of the amino acid, or no, proline transporter, I think. And you need tissue-specific promoter, which will be specific for trichomes. So if you can do that, you'll have a chance to have salt accumulated in trichomes, and later on, secretion can be just by natural exclusion, or it can be probably by rupture of trichomes. I'm not sure about that. Again, if you play with the size of trichome through developmental process, increase the density and the size of that, it's endoreduplication mechanism. So really, the mesembryanthromy results show very nicely that the size of the bladder correlates with this amount of reduplication steps. Once again, this molecular plant opinion paper or focus paper we just published has all the details and tables with genes and things. Just look at that.
Okay. Thanks, Sergey.
Yeah, we'll add that Ashwani Parikh is the senior author on that paper. So we just have in molecular plant. So obviously, again, if he's next to you somewhere, you can talk to him directly.
Yeah. I can contact him also. Yeah.
Okay.
Yeah. And one more question also from Gayatri, one of our participant. So she was just asking about the cost of, I think, the MIFE system, which you have shown. So she was asking about the cost of that particular instrument.
Okay, UTES does not produce it anymore. We license it to my former postdoc, who is now running his own company in China. So in the past, the cost of the electronics and hardware from MIFE, excluding manipulators, was about $40,000. The full system was about $80,000.
Okay, so now it can be purchased from that Chinese company through global tendering also. Is it so?
It's called Flux Advance. We, University of Tasmania, license them the rights for selling and production.
Okay. Thank you.
Yeah. Or you're welcome to come back to my lab and do the my 8 systems here.
Yeah. Thanks for the offer.
Yeah.
Any question? If there is no question, then we are coming to an end. Then, Kaushik, any question you have?
No, madam. Currently, we don't have any other question on the chat box. So I think
now we'll be coming to an end.
Yeah, we can close the session.
Just due to some technical problems, we could not introduce our first speaker, Kabin Ji, Professor Kabin Ji, and this Srinivasanulu. That first speaker, Kabin Ji, he is a professor in National Key Laboratory of Crop Genetic Improvement, Huzhang Agriculture University, China. Professor Kabin Ji received his BSc degree in 2003 and PhD in 2008 from Huzhang Agriculture University. He worked as postdoc fellow in Pennsylvania State University from 2008 to 2015. Since 2015, he was appointed as a professor at Huzhang Agriculture University and joined National Key Laboratory of Crop Genetic Improvement in 2017. Dr. Z received Chang Jiang Scholars Program Young Scientist in 2018 and National Natural Science Fund for Excellent Young Scholars in 2017. Dr. G.S. research focuses on elucidation of the molecular mechanism by which plants interact with pathogenic microbes and microbiota. Besides, his group used rice and blast pathogen as a model to dissect plant microbe interaction by integrating genetic, biochemical, genomic, and microbiomic approaches. Further, his group also developed a new gene editing tools for plants, which has been published in PNAS. Their long-term goal is to improve rice production with cutting-edge biotechnology for sustainable agriculture. Professor G published a number of research papers in International Journal of Report with high impact factor, such as PNAS, plant cell molecular biology plant. Then coming to Srinivas, he is a senior scientist at IRRW Philippines, and he is working on grain quality and nutritional laboratory. Thanks. Then now we are coming to an end. It is my time to give a brief vote of thanks to all of the participants and the speakers and the chairman here. Good afternoon to one and all again. I deem it a great honor and privilege to propose the vote of thanks on behalf of each and every members of ARRW and also on behalf of all collaborators who are organizing this program. Then firstly, I express my sincere gratitude to Dr. Owen Singh, BC, Visa Agriculture University, and Dr. Agarwal, BC, OUAT, for co-chairing this session. And again, thank you for sparing their valuable time for nicely conducting this session. Since they are in higher post, they have actually they have been assigned other programs. That's why they have left. Sorry for the this interruption. Then I am also extremely grateful to the Professor Kabin G, Dr. Srinivas Lu, Dr. Ajay Kohli, Professor Kejing Wan, and Professor Sergei Savala for delivering the enthusiastic presentation, which will definitely help in updating and enriching the participant knowledge of the rice researchers who are particularly working in these specific areas. Further, it will definitely help us to reinforce our future research activities, which are going on in different institutes. I also thank to all participants for their active participation in this session. I am also very much thankful to our rapporteurs, Dr. Jyoti Badri, senior scientist from IIRR Hyderabad, and Dr. Kaushik Chakrabarti, scientist, NRRA Cuttack, for recording the proceeding of this session. Finally, I thank them who have directly or indirectly helped us, whom I might have forgotten. Once again, thank you all. We are coming to an end. Thanks.
Thank you, madam.
Kaushik? Kutu?
Yes, madam. So I think we end here, but this link will also work for the evening lecture. So all the participants who are interested to listen to the evening lecture, they may come back at 7 p.m. tonight.
Okay. This link it will work, no? For this.
Yes.
Okay. Thank you, Kutu.
Dr. Kaushik. Dr. Kaushik.
Yeah, madam. Jyoti, madam.
Yeah. We'll discuss later about how to go ahead with writing the proceedings. We'll contact over. Yeah.
I think we need to present it tomorrow in the valedictory.
Tomorrow itself?
Yeah.
Okay,
so we need to just you can do what thing you can whatever you have.
I have noted down. Yeah, we'll discuss in the evening otherwise. Once.
Yeah. Okay.
Sure. Thank you.
Thank you, Dr. Jyoti, madam.
Thank you, ma'am. Thank you, ma'am.
Okay, thank you.
Let us
Dr.
sleep.
Kutub. Dr. Kutub.
Yes, yes, ma'am.
From this session, we can take break.
Yes, 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 ma'am, sure.
Because
So we will again assemble exactly at 7 p.m. We will start our program of
Okay.
evening lecture.
Okay. So why exactly at 7 you tell people to join at 6:30? So slowly they will assemble
Yes,
by
yeah,
7.
I think yes. From 7 we will start our
If you
proceedings.
tell 7, no, people will join by 7:30. So better you tell by 6:30 kindly start
Yes.
start joining. So people
Okay,
will
okay,
slowly.
okay, ma'am, sure.
Okay. Okay. So I'll attend the other one that is
Yes.
going on simultaneously.
Okay, okay, ma'am. Thank you very much for your presence.
Okay, sir. Thank you.
अपा
कौन हला
देखुଛନ୍ତି କେମିତି ମାନେ ହଚପଚ ଦେଖୁଛନ୍ତି ଇଏରେ
अच्छा वो सेम
ନା
सब
ମୋ ବଟେ ନା ନା सब छोड़ दिया ना ओडिया में कौन समझता है ओडियाରେ କିଏ ବୁଝୁଛି
ସମସ୍ତେ ବୁଝୁଛନ୍ତି
ହଁ
ସେ ଶୁଣ ଏମିତି ସବୁଠି ହୁଏ ତେଣୁ ବ୍ୟସ୍ତ ହବାର କିଛି ନାହିଁ କଣ ଅଛି ଡକ୍ଟର ଅଜୟ କହିଲି କୋଉଠି ରହିଲେ ସେ ଆସିଲେ ଆଉ କଣ ଆଉ ଜଣେ ତ ଆସିଲେ ତାଙ୍କ ଜାଗାରେ ଆମର
କଣ
ତ ଜାଗା
ଆପଣଙ୍କ
ଖାଲି ପଡିବ
ୱେଲସିଂ ଛାଡି ପଳେଇଲେ ଅଗ୍ରାଲା ଛାଡି ପଳେଇଲେ ମତେ ତ ଛାଡି ଦେଇଥାନ୍ତି
ଡକ୍ଟର
ମୂଳରୁ ଆଉ
ଅଗ୍ରୱାଲଙ୍କର ପ୍ରୋବ୍ଲେମ ଜାଣିଛଟି
ନା 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 ମୁଁ ଜାଣିଛି ତ
ତେଣୁ
କିନ୍ତୁ
ଆଉ
ମାନେ
ନଟ୍ ଏକ୍ସପେକ୍ଟ ଟୁ ମଚ୍ ଯେତିକି ହେଇଛି ଆମର ବହୁତ ଭଲ ହେଇଛି ଡୋଣ୍ଟ ୱରି
ଭଲ ହେଇଛି ତ
ଆମେ
ଆଉ
ବଢିଆ
ଠିକ
ବଢିଆ
ଅଛି
ସ୍ପିକର ପାଇଛେ ବଢିଆ ବଢିଆ ସ୍ପିକର ପାଇଛେ ଆଉ କିଛି ବ୍ୟସ୍ତ ହବାର ନାହିଁ ହେଲା ମୁଁ ଅନ୍ୟ ସେସନ ଟା ଜଏନ କରୁଛି ଜଏନ ଅଛି ମୁଁ ଆଉ ଗୋଟେ ସାଇଡ ବାଇ ସାଇଡ ଜଏନ ଅଛି ଲାପଟପ ରେ
ଯାଆନ୍ତୁ ଯାଆନ୍ତୁ ଆପଣ
ତା ଭିତରେ ଯୋଉ ହେଇନଥିଲା ପ୍ରାଇମ ମିନିଷ୍ଟର ପ୍ରୋଗ୍ରାମ ତାର
ହଁ
ରିପୋର୍ଟ ଯାଇନଥିଲା ବୋଲି ଚିଠି ଆସିଗଲା ରିମାଇଣ୍ଡର
ଏ ଭଗବାନ
ମାନେ ଦିଟା ବେଳକୁ କହିଥିଲେ ମାନେ ଦିଟା ମଣ୍ଡଳ କୁଆଡେ କଣ ପ୍ରେଜେଣ୍ଟେସନ ରେ ରହିଲା ପଠେଇଲାନି ଏବେ ଚାଲିଗଲାଣି
ଆମର କିନ୍ତୁ
ହଉ
ଠିକ ବେଳେ ସରିଛି ଏଇଟା
ହଁ ହଁ ତମର ଟାଇମ ବି ସରିଗଲା ହଉ
ନାଇଁ
ହଉ
मैडम हेलो
हाँ उमाकांत
हाँ मैडम कुछ समझ में नहीं आ रहा है मैडम
ए क्या बात करता है तू हाँ तेरा तेरा फेस देखा फेस
नहीं वो
देखा
अंधेरा है मैडम दिखाई नहीं देगा
हाँ वो ठीक ठाक था
हाँ बहुत बहुत अच्छा था मैडम
अच्छा और कैसे है तू तू तो फोन फोन कुछ नहीं करता तू फोन करके बात करना अरे हेलो उमाकांत
हाँ मैडम
और क्या काम चल रहा है तेरा
मैडम ज्यादा काम नहीं चल रहा है यहाँ पे
हाँ ज्यादा
आप
काम
कैसे
नहीं
हैं मैडम
ठीक हूँ मेरे को थोड़ा आज बुखार बुखार है
ओ तबीयत तो थोड़ा ध्यान रखिए मैडम
हाँ कुत्तू हाँ हाँ बढ़िया हुआ अच्छा मेरे को क्या है ना मेरे को आज बुखार है कुत्तू मैं जा रही हूँ घर पे कनेक्ट करूंगी ठीक है ठीक है चल हमें बंद कर दबा चल बजते हमें पड़ेगा
म्यूट कर दियो
हाँ
म्यूट कर दियो
Rice, the golden grain, satisfies the hunger of more than two-thirds of the Indian stomach. National Rice Research Institute, Cuttack, a premier rice research institute of India, presents its glorious 75 years of journey. The seeds of Green Revolution were sown at National Rice Research Institute and spread to the rest of India. Once, India was dependent on other countries for food. Under the leadership of Indira Gandhi, Chidambaram Subramaniam and M.S. Swaminathan, first semi-dwarf rice variety Taichung Native 1 was planted in the field of this institute in 1964, which led to the famous Green Revolution in the country. In 2015, National Academy of Agricultural Sciences awarded NRRI for its contribution to Green Revolution in making India self-sufficient in food grain production. During its 75 years of remarkable journey, NRRI released 140 rice varieties and developed many crop production and protection technologies for the country. In 1968, the institute released its first variety, Padma. Successively, several mega varieties like Jaya, Ratna, Pooja and Satabdi were released. Today, varieties of this institute occupy 18% of rice area of the country, producing about 28 million tons with Rs 48,000 crore gross return annually. 1943 was a disastrous year in our history. India was at the forefront of the Second World War, while internally trapped in the devastating claws of the Great Bengal famine. Its outbreak was chiefly attributed to the deadly brown spot disease of rice. To intensify research in rice, Central Rice Research Institute was established in Cuttack on 23 April 1946. Dr. K. Ramya, the first director of CRRI, Dr. P.K. Pareja, Director of Agriculture, Orissa, and Maharaja Krishna Chandra Gajapati, Prime Minister of Orissa, were the founding father of this great institute. In 2015, CRRI was renamed NRRI, National Rice Research Institute. All good wishes to this Rice Institute, first of its kind in India, in Asia and in world. May it solve the problem that affect us in agriculture, said Pandit Jawaharlal Nehru during his visit in 1948. Food and Agriculture Organization sponsored CRRI to execute the first Indica japonica rice hybridization program in 1952. Crosses made at CRRI led to the release of Malinja and Mahasuri in Malaysia, Sirna in Australia, and AD-T27 in Tamil Nadu. This institute made vital contribution in hybrid rice breeding. A new source of cytoplasmic male sterility was identified in the institute back in 1990. The institute released hybrid rice varieties Ajay, Rajalakshmi and CR Dhan 701 that give 15 to 20% more yield than conventional varieties. Donor plants for bacterial blight resistant gene XA21 and submergence tolerant gene SUB1 have been identified from NRRI, which assisted developing stress tolerant rice varieties throughout the world. Work at CRRI has drawn attention of Indira Gandhi, former Prime Minister. During Silver Jubilee, Indira Gandhi said, "The Central Rice Research Institute in Cuttack has already done good work in introducing new varieties of rice, which will improve yields." Today, climate change threatens agriculture. This institute is at the forefront of developing climate-smart rice varieties like drought-resistant Sahabhagi Dhan, combined submergence and drought-tolerant CR Dhan 801 and 802. Climate change increases incidence of pests and diseases. The institute bagged a patent for inventing an alternate energy light trap for insect management. Double haploid technology can speed up breeding process. Being a leader in double haploid technology in the country, the institute released 2 double haploid varieties, Satya Krishna and Falguni. The institute is strongly contributing to combat malnutrition in the country. Towards a successful step, the institute released rice varieties with high protein and high zinc. Prime Minister Narendra Modi has dedicated high zinc variety CR Dhan 315 to the nation on the 75th anniversary of the Food and Agriculture Organization. Visionary directors of the institute have fostered the development of extraordinary infrastructure and research facilities. electron microscope, instruments for ecological prospects of microbes, rice quality analysis, pesticide residue analysis, C4 Rice Laboratory for improving photosynthesis, advanced facilities for climate change studies, genomics building, auditorium with 500 occupancy. The institute made exemplary effort in collecting and preserving valuable rice germplasm during 1955 to 59 by conducting the landmark Jaipur Botanical Survey. It played crucial role in establishing the secondary center of origin of rice in Jaipur. Today, the Institute Gene Bank preserves more than 35,000 rice accession for future prosperity.
National Rice Research Institute of Indian Council of Agricultural Research caters to the need of all rice stakeholders, including farmers, researchers, students, entrepreneurs, traders, and industry. It has signed 89 memorandum of understandings with various industries for commercialization of NRRI technologies. For its enormous contribution towards rice science and national food and nutritional security, it has been bestowed with the prestigious Sardar Vallabhbhai Patel outstanding ICAR institutions in the recent past.
I will continue to say, has dug the seeds of the great revolution are sown here in the fields of CRRI. I hope we will also sow the seeds of the evergreen revolution, which will take our country higher yield and perpetuity, so that food security is not a problem, and the repetition of Bengal famines will not take place.
Dr. Kutub, I am online.
Yes, yes. Okay, thank you, sir. Yeah, I have seen Dr. Rajiv Bharsne and also Dr. Holger Pukta has already joined.
Good evening, Sundaram sir.
Good evening, sir.
Hi.
Good evening, sir.
Kutub, I think we can start now.
Oh, yes, sir. Yes.
Good evening, everyone. Good evening, Kutub.
Good evening, sir.
Sundaram and all the rest.
How are you?
Good evening, Dr. Rajiv.
Sir, namaskar. Pathak sir, namaskar.
Namaskar, Lankavu, namaskar.
Namaskar, sir.
Sundaram, good evening. Madam, good evening. Good evening, everybody.
Good evening.
I think it is already 7 o'clock.
So we can start, sir.
Yes, sir. Start now. Yeah. Rajiv ji, should we start?
Yeah,
yes. This is your meeting, so please go ahead.
Okay, sir. So let me start then, sir.
Yeah, go ahead.
Please.
Good evening. This is Kutubuddin Mullah from National Rice Research Institute, Cuttack. Respected Dr. Padmini Shoail, Director, NRRI. Dr. R.M. Sundaram, Director, IIRR. Dr. Himanshu Pathak, Director, NIASM. Professor Rajiv Bharsne, Research Program Director, Accelerated Crop Improvement, ICAR-Central, Hyderabad. Professor Holger Pukta, Director of the Botanical Institute, Karlsruhe Institute of Technology, Germany. All distinguished participants in the ARRW Symposium, as well as other participants who exclusively registered for this evening lectures. It's my real pleasure to welcome you all to the distinguished evening lectures of ARRW Diamond Jubilee Symposium. Good evening, ladies and gentlemen. You know, as a unique and most exciting component of ARRW Symposium, we host distinguished evening lectures. These evening lectures are delivered by scientists of eminence, very well known all over the world for their contribution, and they are indeed highly acclaimed. We open up this lecture to the public who are interested but not registered for the symposium. Last year, Professor Pamela Ronald from University of California, Davis, and Professor Swapan Datta, former DDG Crop Science ICAR, have delivered evening lectures. And that was grand success. And we are also expecting this year a lot of attendees. So this year, we are lucky to have with us two stalwarts in their own field for these evening lectures. Both are very well known for their seminal contribution to the next gen technologies for crop improvement. Guess what? One from genomics, Professor Rajiv Varshney, who is the Research Program Director, Accelerated Crop Improvement, and Director, Center of Excellence in Genomics and System Biology, ICAR-Central, Hyderabad. He is highly acclaimed for his work on genome sequencing, genomic-assisted breeding, and translational genomics. And another from genome editing field, Professor Holger Pukta, Director of the Botanical Institute, the Chair of Plant Molecular Biology and Biochemistry at the Karlsruhe Institute of Technology, KIT in Germany, who first showed that genomic DSB can mediate genome editing in plant and did extensive research on how the DSB is repaired in the cell. So without further delay, and we'll be knowing about them, about the speakers in later time of this evening. So without further delay, I would request Dr. Padmini Shwain, Director, NRRI, and Dr. R.M. Sundaram, Director, IIRR, for chairing the session. And over to you, Sundaram, sir, for introducing our first speaker of this session.
Yeah. Thank you, Dr. Kutub. And on behalf of Association of Rice Research Workers, I offer you all a very warm welcome for this particular evening lecture. It is indeed a proud privilege for me to introduce my beloved friend and also a renowned scientist, Dr. Rajiv Kumar Varshney, who is presently serving as Research Program Director, Accelerated Crop Improvement at ICAR-Central, Hyderabad. And also, he's also working as Adjunct Professor, Murdoch University, Australia. And then he'll very soon be moving to a higher position there in the university in Australia. So Professor Varshney is a clairvoyant analytics, highly cited researcher in the field of agricultural sciences, who specialized in genomics, genetics, molecular breeding, and capacity building in developing countries. He is engaged in discovering, developing, and delivering innovative R&D solutions to tackle wicked problems facing global agriculture. Dr. Rajiv has made significant contributions to improve food security in Asia and Africa by creating genomic resources of major orphan tropical crops. He has developed and deployed DNA marker technologies for the identification of useful genetic variation in tropical crops. Dr. Varshney, together with his team, has used these resources and technologies to identify genetic loci and also candidate genes for drought and pest tolerance in key staple crops for sub-Saharan Africa and India. He has initiated and led major programs that are creating and delivering superior crop varieties to some of the world's poorest farmers. Dr. Rajiv Varshney has supervised large international teams consisting of up to 200 members representing a range of diversity in ethnicity, nationality, and gender. In these roles, he has provided expertise in R&D management, product development, innovative ideas, and promoted an inclusive culture and interdisciplinary and collaborative research ecosystem in India. His leadership efforts have led to the mainstreaming of genomics in crop breeding programs at many institutes in several countries, including India, China, Ethiopia, Kenya, Malawi, Ghana, Mali, and Burkina Faso. And I believe the example set by him could also provide a very good lead for gainful application of genomics in India, particularly in rice crop. Professor Varshney is a fellow of all three National Academies of India, that is NAS, NASI, and then INSA. And he's also a fellow of Third World Academy of Sciences. He's the recipient of the prestigious Swanti Swarup Bhatnagar Award from Government of India, Rafi Ahmad Kidwai Award of ICAR, and he has acquired many more laurels. Being a prolific writer and having more than 47K citations, and with a H index of 108, understand that Dr. Rajiv has published more than 1,000 research papers, of which are highly cited. Yeah. And with this particular small introduction, I would like now request Dr. Rajiv to continue his, begin his talk. Dr. Rajiv?
Thank you very much, Sundaram. You are a great host, great friend, and that's the reason you have given my introduction in superlative degree, what I really appreciate. And before I start, I'm having some problem in sharing my screen. I do not see the window sign. I don't know why. And this is really a challenge for me now. I don't know what to do. Do you need to, somebody needs to give that, what do you call it?
Let us see to make you a co-host then.
Yeah, so I don't know that why I'm having this problem. I don't see this thing. Otherwise, we will ask Holger and I will fix my problem. I don't know that why this, generally this is not the case. I see different windows, but not this PowerPoint thing. I don't know what is this file, then Dropbox. No, I really feel sorry.
Maybe if, try to unshare and then share, Dr. Rajiv.
What's that?
Can you unshare and then share the screen once again?
Yeah, I have done that one many times when you were giving that. I don't see this thing. I don't know why this is happening. So I'm really feeling very sorry. I see a lot of things.
Yeah.
Okay. So can you please, my sincere apologies. If Holger is ready, maybe you go ahead with his talk and then I try to fix my problem. I don't know what is that thing.
Yeah,
well, I can try if you want, but I'm not sure whether it works in my case. You have to decide.
You try maybe because you are.
Should I try? Organizers, should I try?
Yeah. Sir, go ahead, sir. Yeah, go ahead. Dr. Krishna can go ahead. Okay. Maybe first, before we start your presentation, I request my co-chair, Dr. Padmini, to introduce the Dr. Holger Pukta. Madam.
Madam, please unmute yourself, madam. Please unmute yourself, madam.
Yes.
Yes. Yeah. No, okay.
Yes.
Yeah.
I am introducing again very warm good evening to all of you. And already Dr. Sundaram has made nice welcome to everybody. So we are going to have Professor Holger lecture now. I think in between Dr. Rajiv's problem will be solved. So it is my pleasure to introduce Professor Holger to you people. Dr. Holger Pukta is a director of the Botanical Institute and holds since 2002 the chair of plant molecular biology and biochemistry at the Karlsruhe Institute of Technology in Germany. After his study of biochemistry at the University of Tübingen and his PhD at Max Planck Institute for Biochemistry in Munich, he joined in the laboratory of Barbara Hohn at the Friedrich Meister Institute in Basel, Switzerland, before he became, in 1995, group leader at the Leibniz Institute for Plant Genetics, Gettersleben. In 2000, he obtained his habilitation in genetics from the University of Halle. Dr. Holger Pukta has worldwide the first scientist to demonstrate that site-specific nuclease can be applied to induce different kinds of control change in plant genomes. His group elucidated major mechanism of DNA double-strand break repair, and he was one of the leading scientists adopting the CRISPR-Cas technology to plants. Recently, his group was able to achieve another important breakthrough for breeding, that is CRISPR-Cas mediated plant chromosome engineering. For his work on plant genome engineering, he was named Pioneer of Plant Biotechnology by the Plant Biotechnology Journal, and he was awarded twice with an advanced grant of the European Research Council. And with this brief introduction, I will request Dr. Holger to deliver his talk if he is ready. Dr. Holger, please.
Yeah, it's a great pleasure. Thank you for this kind invitation. I want to thank all organizers for inviting me. I feel really honored to give a lecture at this very special occasion. And what I will do, I will tell you a little bit about my personal story, how we entered editing and what we achieved in gene editing, genome engineering over the years. So in the beginning, I will start very basic with gene editing. I will then tell you a little bit about gene targeting, which means we are changing homologous the genome by homologous recombination. And then what really fascinates me most, and what we just started to do 2-3 years ago, is to go from single genes to manipulate chromosomes by CRISPR-Cas. And I promise you, I also have some new data which I never talked about before, which specifically I want to tell you for the first time for this specific occasion. Okay, let's start. Gene editing. Well, let's be very basic. You all know breeding is very successful over hundreds and thousands of years. And in the end, what breeding achieved is, what you see here is, you have a plant, something that looks like a plant, and in the end, you have something that you can eat and that tastes well to more or less to one or the other, like Brussels sprouts or broccoli that was coming from this brassica plant. The problem is during this breeding process, genetic variability is lost. So you could go from here, from this plant to Brussels sprouts, but you cannot go from Brussels sprouts to kale or broccoli anymore. So, and if you want to further improve these cultivars, you need genetic variability, and you have to introduce some way or the other genetic variability. And the most brutal way to do this is just by making damage on this genetic information, making damage on DNA. And the most brutal way to make damage is to induce double-strand breaks. And if you induce a double-strand break, it has to be repaired, otherwise the cells die. And what you see here as an example, during this repair process, mutations arise. And now you have what you want. You enhance genetic variability. So you might argue, yeah, but this is only destroying genetic information. Can this be good for breeding? But we all know that this can be marvelous. Just one example is if you think about cereals in nature, they have to have very long stems. And the farmer, of course, in the field doesn't want to have long stems. He wants to have short stems. So if you just destroy genes that are important for long stemness, then you get short stems. And this way you really get a good trait for breeding. And this is one of the basic principles. And this was used since a very long time. So this has nothing to do with gene editing. It was used before for 70 years by just putting X-rays to these plants or chemicals inducing these breaks. The problem is, of course, that you induce thousands of other mutations. It's a slow process. You have to cross back. You have to get all the negative traits out of these plants. And you have a lot of off-site mutation. But in the end, it was extremely successful. So just two examples. I'm sure you know a lot of more as breeders. I mean, grapefruit without a seedless grapefruit was produced this way, or all the many cereals. Just what I talked about, the short stemness, they were also induced in this way. So very, very efficient technology. We use 3,000 cultivars worldwide that was produced by this. And it was, of course, clear that this brutal way of inducing breaks is not very clever. And if you think about cleverness, you, of course, think about what is nature doing? What are the organisms themselves doing? And in principle, for many biological processes, double-strand breaks are induced in a programmed way in specific positions in the genome. And this, in principle, was the starting point for us to really look for enzymes that were specific enough to induce just one break in a plant genome. And we were lucky at this time. This was a long time ago, as you see, in the beginning 90s. There was an enzyme in yeast IC1 that has a long recognition site, 18-mer. And so if you got this site into a plant cell, you can really study double-strand break repair. And then you can really understand what happens if you induce breaks at just one side. And these studies, which we followed over a row of years, and I will talk a little bit about this in the next few slides, gave us an impression what we could achieve. And this is still what we are all achieving by inducing nowadays double-strand breaks by CRISPR-Cas. So we had this technology, and of course we realized if we induce a break in plant cells, we can induce very efficiently mutations in open reading frames. And we also realized, which will be important later on in the talk, that there are two ways how these breaks are repaired. There's a so-called classical end joining pathway, where the ends are brought together. Sometimes one or two nucleotides are lost. Open reading frame is destroyed, or alternative end joining, where microhomologies play a role and you get bigger deletions. Again, this is very mutagenic, and if you have an open reading frame, it's killed. And this is the basic principle how we knock out genes nowadays using CRISPR-Cas. But what was fascinating for us at this time already was not looking at the events that normally happen. So if you induce 100 times the breaks, 99 times it's repaired by non-homologous end joining, but also on other things that happen. And nowadays, sometimes you read in the newspapers, CRISPR-Cas, other things happen, this is not controllable, but in the end, this is double-strand break repair, and it's interesting, and you can use these rare events. And one thing we are totally fascinated when we found it all those years ago was when we induced a break, sometimes we also saw insertion. So if you induce a break, DNA can insert. This can, on one side, be a transgene, tDNA. We could show that tDNA can insert in double-strand breaks. And nowadays, everybody, I think, accepts that tDNA repair is joined to the tDNA integration. But we also found that sequences from elsewhere in the genome, from other sites, can be copied into breaks. And this is also interesting if you think about genome evolution, but also we thought maybe this is also interesting for application. So we always were fascinated, not only in the general repair events, but also in these rare things that happen. And you will see in the end, concentrating on these rare things, now we can achieve also global rearrangements. Okay, fine. So we worked a long time on double-strand break repair mechanisms, and we also worked with enzymes, different kinds of enzymes, how we can induce breaks. But I think the moment that completely changed my life, but not only my life, but I think the life of many scientists, not only plant scientists worldwide, was when the CRISPR-Cas system became available in 2012. And I remember the day when I saw this, I think it was in June 2012, when I saw this paper in Science published by Chapoutier and Dutna. And two of my co-workers came to me and said, Holger, this is a new molecular scissor, shouldn't we try it? And I told them, well, guys, I think this is complete crap. This will never work. This will never work because this is from bacteria, so it will not be specific enough. Bacteria don't have chromatin structure. And so I really decided not to work on it. And I was very happy with the decision till the day before Christmas 2012. The day before Christmas 2012, two more papers came out in Science, showed by George Church and Feng San, showing that CRISPR-Cas is working in mammalian cells. And then I thought, shit, this is really, really very bad. And we completely lost the race before we started. A lot of colleagues, a lot of plant colleagues, of course, immediately started to work with CRISPR-Cas. And so we decided just in one day before Christmas to start with CRISPR-Cas. And there was, fortunately for us, there was one big problem for plant biology not solved by my colleagues. And this was the problem to induce mutations by CRISPR-Cas in Arabidopsis. And so I had a very talented PhD student at the time who was working like a madman, and he really jumped into this. And in contrast to the rest of the world, who used always 35 S promoters for the expression of the Cas nuclease, we used a UBI promoter. And we immediately were able to apply the system to Arabidopsis. You know that in contrast to many other plants, Arabidopsis is transformed by flower dip via the egg cell. And the important thing is not only to induce these mutations, of course, in some somatic cells, but to get it to the next generation. And this worked very nicely in our case. And in the beginning, we got mutation rates about 10 and 20%. And of course, we also sent out this clone worldwide to many, many different labs. And people could show that our clones also work very efficiently in many other plant species. And this was, we were happy to have this 10, 20, 30% mutation efficiency. But if you remember what I told you before, that we were really interested in these rare events, I, of course, was dreaming about enzymes that are even more efficient, that induce in almost every cell breaks. Then it's much more easy also to find this rare events to achieve other things, not just enjoy. And so we are, and this is an ongoing process, we are always checking for enzymes that work better, at least in Arabidopsis. This is Janet Steinert, another PhD student, and she really gave me a positive heart attack by checking the Cas9 of aureus. So everybody used, like everybody else, the Cas9 of Pyogenius prefers the Cas9 of aureus, and we got really extremely high efficiencies, at least in certain sites, for mutation induction, for double-strand break induction. And as you will see later on, we also use this enzyme then to really get these rare events like chromosome engineering. There's a follow-up story, and if you are familiar with the CRISPR-Cas system, you of course know that besides this originally discovered Cas9 system, we also have this Cas12 system here. This was discovered 1 or 2 years later. This Cas12 system is also very efficient in inducing double-strand breaks. It was not so efficient in plants as in mammals, because these Cas12 enzymes are much more sensitive for temperatures. And as you know, these are from bacterial pathogens of humans, and they grow very well at 37 degrees Celsius. It's of course difficult to let this enzyme work at 22 degrees Celsius. And therefore, we used one of this LB Cas12a, and by Patrick Schinnerle, one of my PhD students at this time, he's now a postdoc in the lab, optimized. So we induced mutations. There were also other people trying to improve it in mammalian cells. We partly used their data and tried then with this LB Cas12a to improve it for plant use. And by a simple change of one amino acid, which is shown here, we really got a much more efficient enzyme. And this you see here, so this is editing efficiencies at 22 degrees, and this is at 28 degrees. Just look at the blue bars and at the green bars. So the blue bars are the original enzyme, and the green bars, this is as a temperature optimized, temperature tolerant LB Cas12a, which we in principle developed. And you see we got very high editing efficiency of up to even 100%. And we then applied this also to other dicotyledonous plants. And here is shown for tobacco, and we also got higher editing efficiencies. So first take home message is, if you are interested in rare things, try to use the best enzymes you can get. So in our hands in Arabidopsis, I know that you're all interested in rice. In Arabidopsis, we are very happy with Cas9 from aureus and Cas12a, LB Cas12a, that was temperature optimized by us. What I can offer you is, of course, if you're interested, if you want to test these enzymes also in rice, just send me an email, and we're happy to supply you with both clones. You don't even have to sign an MTA. This would take much too long with our legal department. So I send you just the stuff. If you're interested, just send me an email. So in principle, what we have now is enzymes that are really very efficient in using double-strand breaks. And this is important, as you will see, for these rare events. I give you one example of these rare events. Before I come to chromosome engineering, this is gene targeting, changing the genome by homologous recombination. So if you induce a break and it's repaired by homologous recombination, then the big advantage is that if you offer a template, you can 100% controls the reaction, that exactly what you want is then integrated into the break. So if this is a homology is here, and this is, let's say, a gene you want to integrate there, then by inducing a break, you can integrate. And what you see here is our original work showing that this homologous recombination, which is a site repair pathways of double-strand breaks in somatic cells, but is very important, of course, in meiosis, in meiotic cells, can be massively enhanced if you induce a break. So without break, if you just offer, for example, a tDNA with homology, you need to screen 100,000 transformation events to find one event where here in this specific site via homologous recombination, we have an integration. But we showed at this time that you, in principle, by inducing such a break, you can dramatically, several orders of magnitude, enhance the specific integration. And we are in the percent range. This was 30 years ago, a major breakthrough, of course, also 25 years ago. The problem is a little bit that we are still fighting today, after all those years, to enhance the frequency of homologous recombination. We developed a technology in Arabidopsis, which might also be interesting in plants that are not so easily transformable, which we call implanter gene targeting. So what we do, we bring in a vector with the homology and transform it into the plant. And then in a second step, we induce the recombination reaction. And we do this by not only activating here the target site, which we want to change, but also by cutting out of the genome this vector. And that's why we call it implanted targeting. The big advantage of this reaction is that you only need one transformation event. You don't need tissue culture with thousands of events. Imagine homologous recombination is very inefficient. Imagine you have a plant species where transformation is a burden, then this will take years and years, and you use our PhD students or technicians one after the other. But we can do this during plant growth, and then we just harvest seeds, and by screening seeds, we can find this homologous recombination event. So the reaction goes like this. We cut out the sequence, it recombines with the respective target, and the donor sequence you can segregate away afterwards. Okay, since we set up these technologies about 10 years ago, we are trying to optimize, of course, gene targeting. And as you will see, what really helped was to use better enzymes. And this was partly worked by Felix Wolter, another PhD student who already left. We have a very nice readout system, which we use by inducing a mutation in a gene of Arabidopsis. This gives us herbicide resistance, as you see here, the ALS locus. And by inducing these point mutations, we can then select for homologous recombination events. Okay. We performed this, and we tried to improve the technology, and we found two things that are very important. On one side, of course, because this is happening during the plant species, you have to use plant cells that go to the next generation, and the best thing is the X cell. The best thing is really the X cell. So we got quite high frequencies with the X cell, and a comparison of Cas9 of Pyogenius with Cas9 of aureus. Cas9 of aureus, of course, gave us higher frequencies. And so in principle, this was very helpful to enhance frequencies. And you see, you always have to screen a lot of different T1 lines, and you get then frequencies up to 5–6% for some lines. So it's also important to check more lines. And I told you about Cas12 already, and obviously we also use Cas12. And the interesting thing with Cas12 is also that Cas9 is cutting within the seed sequence. So if there is an end-joining reaction going on, inducing a mutation, this enzyme cannot cut anymore. But with Cas12, it's cutting outside of the important sequence that is recognized. And so in principle, you can cut several times by end-joining and still might get a cuttable site, which then can again be used for homologous recombinations. Therefore, we hope that we can get more events if we use Cas12a instead of Cas9. And we performed this. Blue is LB Cas12a. This is now only the mutation induction, so double-strand break induction. And in this was the original LB Cas12a. This is not, at this time, we didn't have this improved version I told you about. This is not cutting better than Cas9, but if you then perform the same experiment for gene targeting, you suddenly see also blue was less efficient than red for mutation induction. Now blue is more efficient for homologous recombination. And this indicates, if you calculate it, that LB-Cas12a is 3 times more efficient in homologous recombination, most probably because it can cut several times. And this is the advantage of this enzyme. And therefore, I always recommend everybody, if you're interested in gene targeting by homologous recombination, use Cas12a instead of Cas9. And obviously, we later on also tested our improved versions. This was done by Laura Merck, another PhD student. And we got about double the amount than with the standard LB-Cas12a. So this is what we would expect just because the enzyme is more efficient in inducing double-strand breaks. And so again, if you would ask me today, what is the best enzyme for inducing changes in the plant genome by a homologous recombination, I would recommend to you use TTLB-Cas12a. This is the best in our experience. Okay, and now I come to my favorite topic, chromosome engineering. Chromosome engineering is a very, very new area, and I want to shortly let you through what you can do with this. I think what everybody is doing all the time since at least 5-6 years in the plant field is to induce deletion. So we could already show 20 years ago, if you induce 2 breaks on a chromosome, we can delete the region between. That's obvious, but there are other things, other interesting things. You can get duplications. I show you very quickly a quick method to induce duplications, which might be interesting if you're interested to change promoter regions to get a more transcription factors binding there. Then very interesting for breeding are inversions. You find a lot of inversions in natural varieties of cultivated plants. If you want to transfer genes in this region, from this region, this is not possible. And in the end, I also will tell you a little bit about translocations, where you can really get genes that are closely linked and that are very difficult for a breeder to get apart, where you can easily bring them on different chromosomes. Okay, fine. Let's start with this small duplication. So in principle, a long time ago, this was Simon Schimmel, that was in my lab quite a while ago. We not only worked with the Cas9 enzyme as a nuclease inducing a double-strand break, but you can manipulate the enzyme. I mean, we didn't invent this, as people did before in mammalian cells. You can also mutate it, so it only induces a break in one or the other strand. And in the beginning, this was interesting because people, as I told you before, specificity from bacteria, people were a little bit concerned whether these enzymes are really specific enough for the big plant genomes. And so we really used, in principle, 2 guides and brought the specificity to 40 nucleotides to induce a staggered double-strand break, as is shown here. And in principle, you can also very efficiently, via this paired nickase approach, induce mutations. But what we found was really surprising for us is that you get duplications. So we found a lot of duplications between the 2 nicks where we induced the breaks. And you see here just a few examples. We published this quite some years ago. And interestingly, in rice, Jeff Bennetson also found this natural tandem duplication, short pieces of DNA that are duplicated in the rice genome. And we both think that this is also happening as a natural repair mechanism if just 2 nicks are repaired in close proximity during genome evolution. So this really plays an important role, and you can use it nowadays for manipulations. And then we asked, of course, also, and this was just published in Plant Cell, we also asked how far can we get apart these 2 nicks, and it turns out that this is not very efficient if you go more over 100 nucleotides, as it's shown here. So, but if you think about about transcription factor binding sites, changing promoter region, you might really consider to use this technology to multiply, for example, enhancer sequences, things like that. And the mechanism is very simple. I mean, you know that I'm the guy who's always interested in mechanisms. You see, we induce here 2 nicks, and then just the polymerase is using this as primer and this as primer. And then if you fill up this region, you automatically get a tandem duplication. And this is very different than this original mechanism, insertion mechanism, which we found before, where sequences from elsewhere from the genome or from a transgene are integrated into a double strand. Okay, so far so fine. Now let's go to the real stuff, to the chromosomal stuff. Breaking genetic linkages, I told you, is something that a breeder wants, but it's very hard to achieve if two genes are close by. Like here's this green and the red one, and we thought, well, let's induce just a double strand break here and then a double strand break in another chromosome. Our species is, of course, Arabidopsis, but you can, I think that this is easily achievable in rice too. So you induce these breaks, and then you go for, so you search for the events where the chromosome arms are exchanged, and with this exchange, obviously, these two genes are now on different chromosomes, and the linkage is, of course, broken. So that's why it's so interesting to achieve translocations. And as I told you before, inversions, due to the sequencing programs, I think we will hear more of this later on this evening. A lot of inversions have been found now in different cereal cultivars, for example, and in this region, no genetic exchange can occur. So why not just bringing this inversion back in the original version, and then you can bring back a recombination in the region, or the other way around, if you have a region where you don't want to have genetic exchange anymore, just flip it, and then you conserve all the linkages. Okay, does this work? Natalia Bijing was the student that addressed the question with the translocation, so I want to go through this quite quickly. We induced breaks at two different Arabidopsis chromosomes, chromosome 1, chromosome 2, and checked whether we can get these new chimeric chromosomes. We applied in principle also a screening program similar to what we applied in gene targeting. So we go for the T1 and then we go for the T2, and we screen big bulks of T2 in PCRs. And if we have a positive signal in such a T2 bulk, then we go back to the individual plants, which really gives you the opportunity without spending a lot of time in screening to come to the right event. And we, as you see here, we got in the end a row of translocations between these two chromosomes, and they were all independent. And we analyzed the junctions, and the junctions were partly perfect. So you exchange chromosome arms without losing a single chromosome. Sometimes you lose a few nucleotides, but this was really fascinating. And of course, you might say, okay, you show us junctions, but did you really change the chromosomes? So we had to prove this, of course, with fish analysis done by my good friend Andreas Huben. And here you see in principle, so original chromosomes here, and here these are the fused chromosomes. This is in mitosis and this is meiosis, original, and these are the new chromosomes where really the two parts are now joined in a new way. And that this works, we could also show with another combination, chromosome 1, chromosome 5. I want to make it very short. Here's a junction again, and this is even nicer if you see this here. So these are the original chromosomes, and isn't it nice? Here, this is a new chromosome, a chimeric chromosome. Nature has never ever seen before this way. So you really can achieve breaking genetic linkages by translocations. How about inversions? So inversions is also something that is not so complicated. If you think about the deletion formation is very efficiently, you induce two breaks and the sequence in between is deleted. But of course, it could be that the sequence is not just gone, but it's just flipping around. And we tested this in the beginning with very short sequences, 2 KB sequences, whether this works also in plants. And we were quite surprised. So this is more efficient than translocations, by the way. So with these short sequences, we got 1–2% inversions. And we analyzed, of course, then also the junctions, because we were interested how the junctions would be. And these junctions were, and this was surprising for us, as I told you before, in most cases, in a way restored, that not a single nucleotide was lost after flipping. And if you think about the guides, and the guides cannot recognize these newly formed junctions anymore, they only can cut the original junction, but not newly formed junction. It's not too surprising. So this indicates that most probably also if you use Cas enzymes, normally it's a cutting and cutting and cutting till you induce a mutation. And in this case, because you have a flip, it's immediately frozen and you don't lose a single nucleotide. And now, talking about DNA repair, and you know that I'm a specialist of DNA repair and repeat DNA repair pathways. Remember, in the beginning of my talk, I talked about this. We could now really conclude that there is this one pathway where you don't lose sequences because the ends are protected by the Q protein, that this pathway apparently is a pathway that is required for translocation, and this other pathway where you lose sequences, it doesn't play a role. So apparently this classical end joining pathway with the Q heterodimer protecting the ends is the pathway that gives us these genomic rearrangement, and the same also applies for translocation. And therefore we now, because we are a lab that has all the factors that are involved, all the mutants, we now just check to be on the safe side what will happen if we knock out Q. And we also did this with translocations. I don't want to go into this. And this is a big surprise we got is, indeed, it's more. So you see this pathway is responsible. You knock out the pathway, expect that nothing works, but it works better. And so in principle, it turns out that these end protecting proteins Q70, Q80 not only protect each end, but they keep the break together. So this is very important to repair the right breaks in the right way. Nature has this mechanism to keep the ends together. But if you knock them out, of course, you lose then specificity in a way that the breaks are not perfectly rejoined, but the breaks can float around, and wrong breaks find each other much more easily. And so in principle, it's even better to induce chromosome engineering in a Q mutant. And this is something, if you have very rare events, one should really consider. We analyzed the sites, of course, also in case of the mutation, and as expected, you get in principle a lot of more deletions. And then we became really serious. And serious in my case is talking about Arabidopsis and a natural inversion of 1.2 megabases. And this was in plant molecular biology, an inversion that was characterized early on. It's the most prominent inversion, most probably, that was known for a long time. And it happened about 5,000 or 6,000 years ago. During the evolution of Arabidopsis, half of the cultivars have this inversion, the other half doesn't have this inversion. And in this region, if you cross two different cultivars, Landsberg and Columbia, one has it, the other one doesn't have it, you really don't get any recombination in this inversed region as you see here. And so the question was, can we really inverse it, 1.2 kb, and can we get back recombination? So we induced the breaks, and this was done by my very gifted PhD student, Carla Schmidt. And she got junctions, she got perfect junctions, like we expected it. Not a single, you inverse it, you don't get a single nucleotide lost. And we got also several independent ones. They have to screen for them. With our procedures, this is not so difficult. So we got a row of events. And then we also, of course, had to show that within the chromosome that we flipped it. And this was done by my good friend, Paul Franz from the University of Amsterdam, using fish. And as you see here, so in the original setup, you should have a red signal, a green signal, and a red signal as is shown here in Columbia. And if we inverse this region, then it should be red, red, green. And you see it here, red, red, green. So this nicely shows that we are really able to inverse it. But even much more fascinating is, of course, then to check genetic exchange between these two cultivars. This was done with my good friend Andreas Huben from the IPK in Gattersleben. And we really checked now between wild type and the inversed Columbia species, this respective recombination behavior. So this is the wild type. Crossovers, these are two different ways to see crossovers. This is the blue region, is the inverse region. So with the recombinant line, we got back genetic exchange between these two cultivars. And this means that after 5,000 years, by inverting the sequence, it was the first time we are, in the end, are able to really exchange, bringing back crossovers, bringing back meiotic recombination in regions that were recombination dead for a very long time. And now I come to the very new data I never ever talked about before. And this is in principle the same question the other way around. So can we suppress recombination? And of course you could say, okay, let's make an experiment. We try to suppress recombination and make this 1.2 megabase inversion just the other way around. But I think this is boring. So we were much more daring. So we really ask ourselves, what about trying to block recombination over more or less a whole chromosome? So we induced a very long inversion in chromosome 2 of Arabidopsis that is about 85 to 90% of the chromosome, 17 megabases. And indeed, we were able to achieve this. So the junctions were again perfect. And if you make such a big inversion, you might, of course, ask yourself, is this still viable? Also in the hemizygous state, isn't there problems occurring if the chromosomes have to pair? And indeed, as you see here, there's a problem with fertility. So this is wild type. So if you get the mutation in the homozygous state, everything is perfect. These plants are perfectly fine. But in the hemizygous state, some of the meiosis apparently do not result in viable progeny. So there might be a problem in chromosome segregation once in a while. But still, the fertility is good enough. It's more than half that you can get all this progeny. And of course, I want to make this very short. We also then had to show that we really inverse the sequence again with my good friend Andreas Huben. So here is the wild type. Here are the markers he used. Here you see the two wild type chromosomes during meiosis, and he performed this on the hemizygous state. So we induce this big inversion, and then we should have red and green very close by. And this is in principle exactly what you see here, red and green close by. And here also the two other, the other chromosomes that is partly paired, where it's still the same. So in principle, we could show we really got this big inversion. And the final question, the interesting question was, of course, can we suppress recombination? And the answer is yes, we can. We almost completely suppress recombination over this whole chromosome by inverting it. Here's the wild type, here's another chromosome. We just checked another chromosome whether we change somehow the recombination behavior, which is absolutely not the case. And what you see here is that almost all recombination now is at the telomeric ends. Meiotic recombination starts from the telomeric ends. So we are not surprised to see this, but there is no exchange in contrast to here. There's no exchange, almost no exchange, I have to say. It's not true, no exchange, almost no exchange in this inverted region. And then we ask ourselves, why the hell have we these few events? There are a few events. Why? We thought we block it completely, but this is not the case. It's a tremendous effect, but still there is something. And we analyzed this something, and this something is in principle always the same kind of patterns. You have a crossover in this inverted region. But this is not a single crossover. These are always double crossovers. So you always have two events. And here you see all the different events. And blue is one cultivar, red is the other cultivar. And you always see the marker changes. And it's always a double crossover in the inverted region. And this, in principle, safeguards that these crossovers are, in principle, viable. And you to explain this to you, I want to show this here. So what normally happens is that the telomeres interact, recombination crossovers can take place here or can take place here. Segregation occurs afterwards, everything fine. However, if you have a single crossover and you don't start with the ends, but you start in the middle with this big homologous region, and you induce a crossover, then you end up with something that's not viable. So you have 2 times the same chromosome end here and 2 times the same chromosome here. This is not viable. So you don't find it. This might be responsible that we have a reduced fertility. But if you have a double crossover, of course, then everything is restored. You have the complete genetic information of both chromosomes restored. And that's why in few cases we find this. Okay, fine. So yes, indeed, the answer is we can suppress recombination massively. And now you can speculate, of course, can we go even further? And I say, yes, I think we can go further. And this is something which we try to address in the next years. Can we, for example, get a centromere being relocalized on a chromosome? This is quite often in evolution, but the centromeric region are heterochromatic. But if you move them to a different place, they might also globally influence, at least on this chromosome crossover frequencies. Also interesting what you find in evolution is, of course, changing chromosome numbers. Are we able to get out of a 5 chromosome plant species like Arabidopsis, a species with only 4 chromosomes? Can you fuse chromosomes? There are, if you look at literature, different ways, like in evolution, chromosomes can be fused, can be mimics this. No way. So it's really getting very excited. And if you think about chromosome fusion, you can also think about making more chromosomes out of these chromosomes, that let's say 6 out of 5, for example. And you can, of course, then think about creating completely new plant species. So the perspectives of chromosome engineering, I think, are really interesting. One way, the classical way, is to use it for breaking and fixing genetic linkages in breeding. But if you manipulate chromosomes, you could also, of course, thinking about producing chromosomes where you stack the advantage traits. You can minimize chromosomes to make mini chromosomes, maybe. You can produce cargo chromosomes. Also, this might be possible using this technology. And in the end, we might end up in a new plant species which might be very interesting if you think about outcrossing. So if you have a species that is genetically isolated from everything that also occurring in the wild, you can be sure that there is no outcrossing going on. And this was always a concern in all these discussions, that we produce one way or the other super plants. And with this way, you can, of course, exclude this too. And with this, I'm at the end. I want to thank you for attention. I hope I didn't take too much of your time. I want to thank my group, and I especially want to thank the European Research Council, which gave us over the last 9 years a very generous funding, which made it possible for us to really advance the field of chromosome engineering. Thank you so much for your attention. Okay, I have to stop now my presentation. Yes.
Okay. Thank you very much. So, Madam, are you going to take the questions?
I just told that excellent talk, Dr. Pukta. You can carry on.
No, Sundaram sir. Okay, so I think it's a wonderful Professor Pukta. So, as from starting from NHEJ to inversion, translocation, all type of mutations. Now that is possible from your work that you have shown. So there are a few questions from our audiences. They have wrote in the chat box, so I read out loud for you. So the first question is, what was the overall efficacy of Cas12a over Cas9, and how it was easier to manipulate over Cas9?
So in principle, I want to be not too general. So in principle, it turns out that every site you want to cut is, of course, different. But as a general rule, due to this temperature optimization, we in Arabidopsis are now mainly using our improved TTLB Cas12 because we get better cutting efficiencies. But nevertheless, there might be sites where we still use Cas9 from Aureus because cutting is better, and you really cannot directly compare these tools because they have, of course, different pumps. But it's just, if it's more on the statistical level that you realize by applying this to different problems that you can get better and more results using TTLB Cas12 than our Cas9 enzyme. Interestingly, I want to also mention this, if other people applied our enzymes, not all for example, saw better efficiencies with Aureus Cas9 than with Pyogenes Cas9. So it depends apparently also a little bit on the plant species, but don't ask me why.
Okay, thank you very much. So another question is, in the literature, often it is seen that GT means gene targeting by HDR and also gene targeting by HR. So what is the difference between the HDR and HR, and are the mechanistically different?
I don't know what is meant with HDR and HR. For me, HR is homologous recombination. I don't know what HDR is referring to be honest.
It's so, probably homology directed repair. Homology directed repair. HDR.
So, okay. I'm not sure whether I answer the question correctly. So in principle, what we see from the beginning in our studies over all these years is if you induce a double-strand break, you have two break sites, and both break sites have to combine by homology. And so it could be that one or the other recombines by homology and the other by end joining. So you find this one-sided events. And in principle, I don't know whether this refers to these kinds of events. Sometimes if you just want to integrate something at a specific site, this might do if you have end joining and homologous recombination. But if you really want to have an event that is defined before to the nucleotide, you of course have to have homologous recombination on both ends. I also want to mention that indeed, if you just induce a break, and you integrate via non-homologous end joining, this is also an option. And if you do this in an intron, this was shown, for example, by Saisha Gao, so we showed it 20 years ago, the TNAs can integrate into breaks by a non-homologous end joining. Saisha showed it by using intron sequences, using CRISPR-Cas some time ago. So this is really also an option you can consider besides homologous recombination for integration.
Yeah, thank you. So next question is, how can we design guide RNAs to create DSB in chromosomes that have ability to remove a complete portion of chromosome, given chromosomes are bundle of DNA strands?
Again, I'm not totally sure whether I got the question. So in principle, what we see, and this is something which we didn't expect so much, is that especially if you remove parts of chromosomes, exchange chromosome arms, things like that, and we go into heterochromatic regions, that we have a lot of more problems in cutting these heterochromatic regions efficiently. So there's really a difference between heterochromatin and euchromatin, and you really have to check before, if you want to restructure chromosomes, whether in these heterochromatic regions we really get efficient cutting.
Okay, thank you very much. So would you mind if I ask you, or request you rather, so to reply in the chat box to the specific questions, so that we can start the next lecture.
Okay, it's a great pleasure. Thank you again for inviting me.
So wonderful to see your energy level, Professor.
Thank you so much.
Okay, so sir, Dr. Rajiv Bhasnak, could you please try to share again? Yes, perfect, sir.
Okay, Kutub, can you see my slides?
Yes, sir. Yes, sir. Only you need to do in slideshow mode.
Okay, let me do it. I was able. Why this is coming second? Let me just give me. Okay.
Yes, sir.
Is it okay?
Perfect.
Thank you very much, Kutub, and thank you very much, Dr. Sundaram, for very nice introduction. I'm very happy to see Dr. Swain, the director of NRI, and also Dr. Himanshu Pathak, and many other senior friends, senior colleagues, and many friends. And thank you very much for giving me this opportunity. Sorry that I had some problem, but let me congratulate ARRW for celebrating this Diamond Jubilee, 60 years. This is a really good time. And thanks, Holger, for coming in that to help us that when I had some problem. Anyway, so now here in this presentation, I will talk about the genomics and breeding innovations for the crop improvement. And as Sundram mentioned, I'm coming from ICAR-Central. So what I'm going to do that all of us are having these challenges, the global challenges for the food and agriculture. I will not go in the details, but all of us are aware that when we are talking by 2050, we need to provide the food for about 10 billion population. For doing this thing, we need to produce 70% more food. So all these issues, they pose a big challenge to the scientific community. And the challenge is that how to produce more food with the less resources. Less resources means less arable land, less water, less labor. And on top of that, we need to consider about the water footprints, carbon footprints, etc. In this regard, genetics and breedings, they have been doing a great job. And this is that very classical articles from Dr. O.P. Yadav, Dr. D.V. Singh, Dr. Dhillon, and Dr. Mohapatra a few years back published in the Current Science. And this slide shows very nicely that how these technology have been very helpful, not only breeding, but also the agronomy and other thing when you are talking about the production of productivity. So you can see that wheat, rice, maize, wheat, rice, sorghum, and fulminate in many crops. However, this has not been the case in several legume crops, and these legume crops on which ICAR-Central works, for instance, chickpea, pigeon pea, and groundnut, and there are a number of regions. One is that they are grown in the marginal environments. Second, there are very limited research community. Third is that if you talk from the genomics perspective, there were not many genomic resources in these crops. So there are several regions, and now we always think that how we can use the genomics and breeding innovations to help the breeding program. So what crop improvement community has been doing traditionally, and this is the rice community. I'm very happy to interact with this excellent rice community here in India, and I know that several colleagues, they have joined from the different countries as well. But what crop improvement has been doing, that they are basically developing the improved varieties with enhanced disease resistance, with higher crop productivity, with the pest resistance, with the environmental sustainability, nutrition, and also coping up with these environmental stresses. And in this case, crop breeding and many other disciplines, physiology, pathology, entomology, biotechnology, many other disciplines that are very much required. So when you talk about the genomics and breeding innovations, recently we discussed, and nowadays this is very clear, and we know that rice was the first crop where we had the reference genome, but now we got these genome sequences available, reference genome available for a number of crop species, and we believe that a high quality reference genome is prerequisite for when you are talking about accelerating the crop improvement. Second is that we need to see the democratization of the sequencing and genomic sequencing and genotyping technology in the different countries, in the different labs or so. And secondly, so not only the sequencing and genotyping, but also we need to think about this precise phenotyping. And nowadays, this is a possibility to develop the pangenomes, and by combining with the phenotyping data, we can go for genes or alleles associated with the traits of interest, and then we can do either gene editing, what Holger has mentioned, or we can do the genomics assisted breeding, which I'm going to tell in few minutes. Now, what kind of genomics innovation? This group knows very well that how important the genomics technology is, and then how we can catalog all possible genes for a given crop or so. And in this regard, sequencing technology, they have been now, I think, in the business for last more than 40 years. A few months back, these different journals of nature, they had this milestone genome sequencing. I happen to be one of the advisors for this particular thing, where they had the discussion that how sequencing technologies, and this was the 40th anniversary of the Sanger sequencing, that they have been helpful, not only that human genetics, but also in the animal and the plant genetics or so. And based on these things, at ICAR-Central also we had a genomic center, which we established way back in 2007. We are having the state-of-the-art genomics and sequencing and computational genomics infrastructure, not at very high scale, but at, I think I will say, the moderate scale. But we believe very strongly in the partnership. And what we have been doing, that we have been working with large number of partners from India, Asia, Africa, and many other countries in North America also. And together, we have been able to deliver the genome sequence for several crops, including pigeon pea, chickpea, pulse millet, and in the groundnut or peanut, we have the two genomes. So we have sequenced the A genome, B genomes, and recently we also completed 2 subspecies genome, Fastigiata and Hypogaea. Not only that, we also have led several genome sequencing projects or contributed in several others, including sesame, mung bean, azuki bean, jatropha, pea, longan, etc. And we feel very proud that our genomic center has led the genome sequencing or contributed to genomes for more than 11 different crop species. Now, at that time earlier, when we were sequencing the genomes and sequencing technology, they are always evolving. When we started the genome sequences way back in 2010 or so, because our first genome appeared in 2012, at that time point, genome sequencing technology, they were very infancy. But during last few years, we have advances in the sequencing technology, and we also have been using those like new technology, including the 3D genome sequencing. And by using these technology, we have improved the genome assembly. Like pigeon pea used to be that kind of poor genome earlier, but now we have assembled the high quality genome. We have fixed several issues of misjoining or some translocation related issue, etc. And same thing in the case of chickpea, etc. So now we have been able to deliver the chromosome length genome assemblies of different crop species. Now, once you have the genomes, you can understand, you can predict the genes, you can do the gene annotation, you can have the gene prediction, etc. You can do a lot of stuff. But now, if we ask the question whether all genes, they are expressed in all the tissues at all the time, this is not the case. So to understand the spatial and temporal gene expression, we have established the gene expression atlas in the case of chickpea, pigeon pea, and groundnut. By doing the RNA-seq for more than 30 to 40 different tissues representing different parts of the plant life cycle, or they are exposed to a number of biotic and abiotic stresses. And based on these things, now we are moving ahead to identify the genes involved in the different metabolic pathways or in response to the different stresses, etc. For instance, in the case of chickpea, we are working in the drought tolerance. In the case of pigeon pea, we are working on the cytoplasmic male sterility. In the case of groundnut, we are talking about the oil biosynthesis pathways, etc. Now, one other question is that many times we think that if we got the reference genome for one individual or so, we have solved the problem. No, this is not the case. Because the genomes, that if you have sequenced one particular line and this does not have the traits, this does not have the genes for a particular trait in which breeders are interested, you will not find those genes. So with this perspective to sequence more genomes, what we have done that we have sequenced about 300 pigeon pea lines coming from the 23 countries. We did huge amount of phenotyping data and did some GWAS analysis. We also identified the center of origin of pigeon pea. Also, like this was in Madhya Pradesh in India, and many other things we have done in the case of pigeon pea. Same thing in the case of chickpea. Initially, we sequenced 430 chickpea lines, and we have done the GWAS analysis in addition to many other answering many biological questions, but I'm talking more from the breeding perspective. So we have identified some genes associated with the yield, drought, and the heat stresses. Some of you may be aware that recently we have completed the genome sequencing of more than 3,000 chickpea genomes, which appeared in the 10th November in Nature. And this paper was not just research, but I think that this was highlighted with very extensively in popular media, including the New York Times, the Economist, and many other media or so. And this shows the value that how the genome sequencing or these pen genomes can be helpful for the crop improvement. I will not go in the details, but I would like to mention that in this project, we have sequenced not only the cultivated, but also the wild species accession from the 8 different species. As expected, we have identified large number of diversity in the wild species, then in the land races, followed by the cultivated or so. And we have done a lot of analysis. I don't have time, but you can read this paper. The most important thing is that we have assembled the pen genome of Scicer species. And as you can see, that when you go for that basically increasing the individuals of sequences, the pen genome keeps on going higher, but after some time this goes at the plateau level and the core genome keeps on going down. But nevertheless, by having this pen genome, we were able to identify around 1600 genes from the additional genes which were not present there, and 1582, they are probably novel genes. And we have found that they are enriched in the metabolism and biosynthesis of secondary metabolites, which may have some roles related to the adaptation or resistance, etc. So nowadays, this having the pen genome is really very, very important. We knew that chickpea was originated in the Fertile Crescent regions and about that domesticated about 10,000 years back. And our study also confirmed that one. But most importantly, our study also identified the two paths of the diffusion or migration of chickpea to the rest of the world, and how this happened, that we identified that one path of so what happened, that migration happened to the South Asia at the same time in South Africa, like in the case of Ethiopia or so. But in secondary diffusion, you had from the Mediterranean region and then simultaneously to the Black Sea and the Central Asia to Afghanistan or so. So basically we had one time migration in this side, another time we had in the other side. In fact, our study analyzed that when we had this chickpea introduction from Afghanistan, which is the white colored chickpea at that time point, because this was coming from Kabul, in North Indian side, when this chickpea, especially this white chickpea, big chickpea seed came from there, people started to call Kabuli chana. So that's the reason in India we have this Desi chana and Kabuli chana or so. So there are many other analyses. Another interesting thing is that for the first time we were able to identify the species divergence time. For instance, Caesar aritinum is the cultivated, reticulatum its immediate wild progenitor, and our analysis have identified that these species were separated about 12,600 years back, and there is large number of those different estimate of the time. And there are many other things from this project. Another important aspect from this project was that generally as a breeders, we are always interested to identify the good genes. And our analysis indicated that when you have this domestication and the breeding, when you go from the wild species to the land races and then from land races to the cultivated one, you keep on accumulating the good genes, but still in the cultivated varieties we have found, we have the significant proportion of the deleterious alleles, or those we call it genetic burden. And because this is a self-pollinated species, you did not have full purging of all these alleles, and our analysis have identified a significant proportion of those deleterious alleles, which can be potential targets for the genomics assisted breeding or the genome editing. So idea is that you just do not accumulate the good alleles, but also you purge the bad alleles. And I think this is another interesting concept in the crop improvement when we are moving ahead. Now, when you would like to see from the breeding perspective, then for the breeding thing, and I know that when I joined ICAR-Central way back in 2005, many times breeders always used to say, if your genomics technology are expensive, we are not going to use. And Sundaram and we had a lot of discussion when he was scientist. He is now having high position as a director, but I know from him from his scientist time that how we can make those genotyping much more cost effective. And in this regard, at ICAR-Central, we have been establishing a range of the genotyping platform, starting from SSR, DART, CASPR, genotyping by sequencing. And when we are saying that, like when you need to do the marker assisted selection, you need to have just 10 SNP panel, and we have brought this cost so down that you can genotype a breeding line in just $1 to $1.5 per sample. When you are having that would like to do the GWAS analysis, you can go for the 56,000 SNP array. If you would like to go for the genomic prediction, you just need to have the 2,000 SNP array. And here our genotyping cost is just about $5 to $6 per sample. So I think that what we have been doing, that to make the breeding program cost effective, to integrate the genomics technology in breeding program, we have brought the cost of all these different marker genotyping platforms. The next thing is that when we are interested to understand the genetics of trait, phenotyping is very, very important. And nowadays, there is a very sophisticated phenotyping platform. And here you can see that you can have the aerial phenotyping platform, you can have the ground phenotyping platform, you can have these unmanned aerial vehicles, drones, etc. So I think that we need to see from the perspective that how much good correlation we are having in those traits phenotyping from the machines versus when the crop is in the field or so. In this regard, at ICAR-Central also our crop physiology group And together with other groups, we have been developing those different kind of phenotyping platform, including Legiskin, lysimeter, field phenotyping, and we have been very successful to use these different platform for phenotyping our breeding population. So, and very recently, we also have been established some more facilities, and where we are using now, we launched this drone facility together with IIT Hyderabad and many other partners, that how we can use these drones now for evaluating those crop performance in the field. So I think that this is the way to move ahead. And so, yeah. So what I was trying to say, friends, that from the genomics perspective, you are having the high density, low density, mid density genotyping platform. From the phenotyping perspective, you got the good platform, and we got large number of genetic population, either they are the biparental, multi-parental lines, magic, nested association mapping, or from the gene bank, diverse genotype, etc. And by combining all these things data, we try to identify those markers associated with the traits. And we are very happy to mention that during last few years, together with large number of partners from India and Africa and many other countries, we have been able to map 20 to 50 traits in each of these crops, including chickpea, like drought tolerant, heat tolerance, salinity, ascocatablite, helicorpa, same thing in the groundnut, pigeon pea. So we have identified large number of markers associated with the different traits. Now, the next thing is the translational research, which is very key for people like us at ICAR, that how we can translate this thing. And this is very core to my, this is very close to my heart, that I always believe that how we can, and I have been working on this aspect, that how we can integrate those advanced genome discoveries in the crop improvement, how we can help to develop the better varieties. So we just don't want to restrict our research to the research papers, to the research journals, but we would like to take those genes from those genomes to the field. Few years back, we have given this concept that how you can use these different kind of molecular breeding approaches, including MABC, MARS, genomic selection, etc. And several of you may be knowing that together with Andreas Graner from IPK and Mark Soros from Cornell University, way back in 2005, we gave a concept of the genomics assisted breeding. And then we proposed that how you can use the genomics technology and have these approaches like marker-assisted selection, marker-assisted backcrossing, marker-assisted recurrent selection. This year, together with several other partners, and we have given this concept that how this GAB can be transformed in the GAB 2.0, genomics assisted breeding 2.0. Here we have come up with this new concept again, that how we can use the haplotype-based breeding, genomic selection, optimal contribution selection, and also use of the gene editing for both, for promoting the good alleles or removal of the bad alleles through the gene editing. We call them page or raise. And then we believe that speed breeding should be the integral part of all these different technologies, so that we can generate the advances in much more faster manner. And we know that rice community has been very, very advanced here in India. And I know that work of Dr. Sundaram and also from many other colleagues from IRI, Dr. A.K. Singh, and also from the NRRI and so, and many other state agriculture university, TNU or so, and PAU, many other organizations in India, they have been very on the forefront to develop the better lines coming out through these different molecular breeding approaches. And they have been doing their great job together with IRRI and many other partners. So I think that we should congratulate that whole rice research community from India and your partners, that you have doing great job. But now the next thing is that where we need to move further. But before that, where we would like to go, I would also like to highlight some examples in ICAR mandate crops, where we did not have even the genetic map few years back, but now through this advanced discovery of the genomics, we were able to integrate those things and develop several improved varieties. Together with the Directorate of Groundnut Research, we have developed the high oleic lines. So for instance, if you see the normal groundnut lines used to have that high amount of the linoleic acid, which is not good for health. And then you are having that oleic acid, and several US varieties, they are having high oleic things. So now in India also, we have moved this thing further, and we have developed through the molecular breeding, the high oleic lines, which are having more than 80% of the oleic acid content. And India has released two varieties, Grinar 4 and Grinar 5 in 2020. And we were also very happy to see these two varieties were the part of the package of the 17 biofortified crop varieties, when Honorable Prime Minister Modi dedicated these varieties to the nation. And then two of them, they were coming from the groundnut. So this was very, very good movement. This was very pleasing for us. Now in the case of chickpea, and in the case of chickpea also, and many times people develop the varieties which are for the disease resistance, because this is much more easier than when you are addressing that abiotic stresses component. But at ICAR side and together with our partners, we were able to identify a QTL hotspot which contains the QTLs for several drought tolerance related traits. And by introgressing this QTL hotspot, we were able to develop several improved lines, and many of these improved lines, they have been released as a varieties following a rigorous testing, national testing, or these country specific pipelines. For instance, in Ethiopia, we had this drought tolerant high yielding varieties. In Ethiopia in 2019, we had, through the interventions of IRI, my colleague Dr. Bhardwaj and Dr. Shailesh Tripathi, now many colleagues from Indian Institute of Pulses Research or so, they have been working, and the same thing for the fusarium wilt resistance with Dr. Mannoor. So we had several varieties for the fusarium wilt, and this year also, again, from that in collaboration with IIPR and IRI, we had the 2 drought tolerant varieties, fusarium wilt resistant varieties, and this work keeps on moving ahead. And again, this year when Honorable Prime Minister Modi, when he dedicated 35 varieties, 2 of our these chickpea varieties, they were also part of that one. And in the case of pigeon pea also, together with US Raichur, we have been moving ahead in this direction. So there are a lot of things, and we feel very happy that during just last 2-3 years, we have been together with the partners. In fact, partners, they release the varieties. So we have been able to deliver this advanced discoveries to release at least 10 to 11 varieties in these 3 different legume crops. As I said, now either legumes or chickpea or wheat or maize, that how we can move further. And we feel that now I think there is a lot of scope, and there is a scope, and we call this approach fast forward breeding. What is this fast forward breeding? As I told that now this is possible to sequence not 1 or 2 individual, but thousands of the lines. As I showed that example in the case of chickpea, we sequence more than 3,000 lines, and chickpea, the genome size is 2 times than the rice one we have. And now we are having those kind of sequencing data in the case of pulse millet and groundnut, which are also having much more complex genome. But nevertheless, genome sequencing is possible. You can identify those different alleles. You can identify the haplotypes. Now, when you have these haplotypes, you can use this approach, haplotype-based breeding. I will talk in a minute. You can use the genomic prediction approaches so that we can keep on advancing the lines which are having the higher breeding values. And some of those lines, we can continue to use them as a parents in our breeding program. Third is when we are using the gene bank material or land races or so, sometimes breeders are worried about this, that they will be bringing some bad alleles. So you will not have just genetic gain, but you will be bringing a lot of inbreeding or bad alleles also. But now by using this optimal contribution selection, you can select the parents in such a manner that you are having good compromise of the higher genetic diversity and higher the trait value or so. So this is the way that we can also select the lines for the OCS. And I've already mentioned that now we do not need to just identify the good alleles, but we can also identify the bad alleles. And for the crop improvement, we need to use the genome editing approaches. You use any approach, but it will be really important if you can advance several generations in 1 year so that you can generate that, you can have the homozygous line in much more faster manner. And we believe that if you can combine all these approaches together, through that you can deliver, you can develop improved varieties in much more faster manner than what we were doing earlier. And here we have highlighted this concept of this haplotype based breeding. And few years back, from the group of Mike Waven from John Innes Center, they have given this concept of the haplotypes, that how you can identify these number of these variation of in the genes from the sequencing data, and you can identify the haplotype. We went 1 step further and we say, okay, we identify these different haplotypes, like genotype 1 is having H1 haplotype for gene 1, H1 haplotype for gene 2, H2 for gene 3, H1 for gene N or so. And in this way, we will be having these haplotype assembly. The next thing what we wanted to do, we wanted to combine these haplotypes with the phenotypes, and we can do this thing haplopheno analysis. And based on this haplopheno analysis, then we identify that for a given gene 1, which haplotype is a superior haplotype, like in this case H3, in this case H1, in this case H2 or so. So you identify the superior haplotypes. Then we ask a question, after sequencing these elite varieties which are grown in the farmer's field, do we have the superior haplotypes for those target genes? If not, and in this case of chickpea, for instance, I have demonstrated that in the case of gene 1, we are having H2 haplotype. On the other hand, we should have the good haplotype, superior haplotype S3. Here we should have at least that H2 haplotype. So what we are trying to do that we can replace those haplotype, and we call this approach as a haplotype based breeding, and we can do this kind of work. And in the case of chickpea, again, that as I said, so we have generated the 3000 sequencing data, 3000 lines. We went one step further and we have done the phenotyping of all those 3000 lines at 6 different locations in India in 2 different years. And my breeding colleagues, they really worked hard and they really generated high quality of the phenotyping data. And we use these phenotyping data to identify not only the jivas, but also alleles. And then as you can see that we have done the 19.10 million haplopheno combinations. And after that, because we wanted to demonstrate this concept, and then we have identified several superior haplotypes. And in fact, we have reconfirmed our approach, because what we have done that if you see that new varieties, they are having higher frequency of the superior haplotype than the old varieties. And based on these things, we already have identified that there are many superior haplotypes for many genes which are not yet present in the elite varieties. So this is the high time that we need to bring those superior haplotypes in these varieties or so. Now the next thing is for the genomic prediction. And for genomic prediction, we are using a range of the approaches. Sometimes we are having this concept that, well, we have considered the environmental data or not. So we are doing the interaction of marker and environment covariates. We are using the whole GM approach. And also for the breeding value, we are not just selecting based on the SNP. We are going also for the haplotype based breeding values or so. And our prediction simulation studies have demonstrated that if you use these genomic breeding approaches, how much yield gain you can have. And some of these things have shown that we can enhance the 100 seed weight up to 23%, which is an important component of that yield. So I think there are several approaches. And in the case of genomic prediction, our group and together with our partners around the world and in India, IIPR, DGR and IRI or so, we have been using these genomic prediction approaches, and our results are very promising, where we can see that higher prediction efficiency for the better yield or so. So I think that this is a really good approach for that. Now I would like to spend a few minutes very quickly on one important component. Many times we are talking about the genetics and breeding, which is very important, and all of us have been developing these better varieties. In India, things have improved a lot during last 5-10 years, thanks to the ICAR Institute, State Agriculture University, and the support from the central government and the state government or so, that farmers also like the replacement rate of the new varieties, replacement of the old varieties through the new varieties is happening very faster. But if you go in many developing countries, farmers, they still grow 15 to 20-year-old varieties. If you see the case of Australia or United States or Europe, where the farming is happening with the larger scale farmer or so, they do not grow the varieties which are more than 5-year-old. So what we want to say that now when you are having these elite varieties, they're coming from any method, genomic assisted breeding or traditional varieties, but they should reach to the farmers in the real time. And we believe that seed system plays very important, especially in those cell-pollinated crops where we don't have much interest from the private sector. So we need to establish or strengthen the seed system so that farmers can have these improved variety seeds in the real time. Second is that when you have improved the genetics in these seeds or these high yielding varieties, we need to ensure that we need to have really good integration of the better agronomy. And now for doing these things, we can really use the digital agriculture, digital decision support tools to help the farming community when they should do the sowing, when they should do the irrigation, when they should do the harvesting, etc., etc. In many developing countries, we also have the problem of the post-harvest losses. We need to work in this particular direction. And then farmers can have the higher produce. But many times, and in India, we are always talking to enhance the income of the farmers than the produce. So now what we need to do, we need to connect the farmers to the markets where the national legislation or these national policies, government role is very, very critical. And then we need to think from the value addition perspective so that not only that farmers are beneficiary, we can also help consumers to be happy, we can deliver the nutrition in their basket. So what we are trying to say that rapid delivery system is equally important as I was talking about the fast forward breeding. So I think these are things are very, very important. We need to consider in the whole these things together. And I would like to mention that some of these things we have used in the tropical legumes project, which ICAR had led together with CIAT, IIT, and the 15 different national programs, including 13 countries in Africa, India, and Bangladesh. And this project ran for several years, and I had a privilege to be the principal investigator for this project for about 7 to 8 years. And this project, we had really big partners for many, many years. But good thing is that as a result of the long-term investment and having the hard work of so many partners, this project delivered 266 improved varieties, 500,000 tons certified seeds, 6 million ton grains. And all of these things, we have documented these stories in that special issue of plant breeding and many books. Most important aspect from this project was that we have established those seed platforms or seed delivery platform. We have strengthened this thing. We brought informal and formal sectors in the seed delivery platform. And then many economists or the several groups, they also have analyzed the impact of this project. And you can see that in the case of chickpea, for instance, that before the tropical legume project, if you see that then the improved seed production was happening about 1,000 tons per year, and this moved to the 3,000 tons per annum or so. Same thing if you go for that, how many household they were being benefited or so from in Uganda, for instance, in the common bean or groundnut, that these numbers, they are increasing each and every case or so. I think this project really helped several million farmers' livelihood or so, and this data is coming from the economist. And we feel very proud to say that ICAR was awarded the Africa Food Prize for this tropical legume project in 2021, and we feel very happy when our work is recognized on such kind of platforms. So I wanted to mention that we need to think from all these perspectives, not just genomics and breeding, but agronomy and seed system and market access is also very key for all these aspects. So anyway, so in summary, I would like to mention that genomics and breeding innovations, in my opinion, they are key for accelerating the crop improvement. Fast forward breeding expeditiously create and incorporate superior genes or haplotypes in crop improvement program. As I mentioned, rapid delivery system needs to be established, or if they already exist, we need to strengthen them for ensuring delivering improved varieties. We need to consider the better agronomic practices. I did not touch the point of mechanization. This is another important area where agriculture needs to be integrated, especially in smallholder agriculture. So, and then the next thing is the farmers' access to the better markets, value addition, food processing. This is very much required. And then if we do this thing from that perspective, this will generate more income to the farmers and deliver better products to the consumers. I would also like to mention that international agricultural agencies, they need to continue to train and develop the next generation of crop scientists, empower farming communities by implementing farmer-centric agricultural policies. International, national, and local government and agency support is very, very much required. So finally, I would like to thank all of our partners, and from the Genomics Center, what I have been leading for last several years, we had a privilege to work with more than 180 partners from the 35 countries in 6 different continents. And of course, during last 10 years or so, 10, 15 years, not all partners on one project at one time point. But this is, I think we see that this is one of our key for our success stories, that how we were able to make some impact on those legume crops, not only from the genomics and breeding perspective, but also from the seed delivery perspective. With these words, thank you very much. And now back to you, Kuto or Sundaram. And if there is any question, I will be very happy to answer those questions.
Thank you, Dr. Rajiv. It was indeed an outstanding presentation. And we got a really good perspective of what kind of difference genomics can do in crop breeding. We have a few questions. Would you like to take them, Dr. Rajiv? Okay.
Yes.
Yeah. The first question is from somebody named DTL. He says that given we are more aware of our environment footprints in our food, beans and pulses from India can be a good source for alternative proteins. Do we know if there is any essential amino acid lacking in bean and pulse? Perhaps it's a good opportunity to spread the food culture of India to other countries to reduce meat-driven protein consumption, thereby reducing our environmental impact. This may not be a question directly related to your presentation. Still, would you like to answer, Dr. Rajiv?
Yes. No, I think this is very good. And thank you very much, DTL. And just would like to little correction. My name is Rajiv, not Sanjeev, but it seems that Sanjeev should be some good friend of DTL. Anyway, so I think that you are having very good point, and this is one of the area. And when you are talking about these legumes, crop or pulses, you are addressing two important things. And this carbon footprint is very, very important when you are talking from this changing the culture or so that you can replace this animal protein by the plant protein. Second is also that these legume crops, they are grown in the marginal environment. So you are also saving the water footprint. So you are talking two, carbon footprints and water footprints. Now at ICAR, we are working on these aspects. And in fact, some of our preliminary data has shown that generally that protein content in these crops, this is around 20%, but we have a possibility to enhance up to 30%. We had some discussion with some companies, including the Good Food Institute or so, who are the major player in this enhancing of promoting the plant-based protein. And we are working in this thing with them on this side. Second is some legume crops, they have the issue of this having the essential amino acids or so, like in the case of soybean, for instance, or so. But I think we have not gone in the details, but this is very important. And I think that this is the area we really want to promote, and we need to work on this aspect.
Thank you, Dr. Rajiv. There is one more question from Dr. Manoj Kumar. He's asking, is there any source available for fall armyworm tolerance in pearl millet?
Yes.
Menace for many crops, including pearl millet as well.
So thank you, Manoj. This is good point. And I'm having a colleague working at ICAR, Dr. Jagdish Java, and then he has developed really good facilities for screening for the fall armyworm resistance. And he's working now to screen the germplasm of sorghum, pearl millet, and also maize for some other colleagues. And I hope that in coming years or so, we will have some good sources of resistance, because the good thing with ICAR is that we got the large scale germplasm collection. And recently we were having some discussion and we were talking, let's target the germplasm from those countries from where this fall armyworm emerged. So let's try to see that whether we can find some good source of resistance there.
Yeah. This is probably one of the last questions. Of course, people can raise their questions. The question is from Vivek. He's asking, what's your opinion on proposed farmer bills concerning the, and it's a link up with rapid delivery system, which you talked about. There are, well, like say, how could a rapid delivery system suggested in your talk can be linked up with a better accessibility and then better price for farmers?
I am assuming that Dr. Vivek is from India, and to answer those questions, to contribute in this thing, I need to go to the parliament probably.
I think that's an apt answer, Dr. Rajiv. Okay. Dr. Arvind Totre has asked a question. How can we collaborate traditional breeding with, or say, how can we combine traditional breeding with this fast-forward breeding? That's a question.
So this is the thing. And now I think that sometimes we give some new fancy names for this breeding, etc. Why? So that people, so this momentum can continue. If we will keep on talking breeding, people say, oh, this is the old science. So basically, we are always having the new labels. But I really don't want to have the differences between this traditional breeding, molecular breeding, fast-forward breeding. My concept is that we should keep on integrating new approaches in such a manner that product development is faster, cheaper, and precise for the different traits. So I think that this is the time now that we need to have in the different ICAR Institute, state agriculture universities, or so that how we should continue to work together with the plant breeding community, with the different logis disciplines, biotechnology, genomics community together. And if we go in this direction, I think we should be able to convert all these different breeding in the fast forward breeding kind of thing. So I think that this is that, in my opinion, this is the way that we can move it.
Thank you, Dr. Rajiv.
And you know that Sundaram, as I predicted, and DTL has also responded, the Sanjeev is his good friend. So I also already knew that one.
Okay, that's fine.
I can't do the genomic prediction. I can also do some other predictions as well.
So he is actually from Vietnam. So
okay,
yeah.
Good.
Thank you, Dr. Rajiv. Are there any more questions anybody would like to ask related to the presentation? Like, say, we have some questions regarding minimum support price and all, which is not this forum. We cannot answer in this forum. One question, interesting question has come. Dr. Bikasani Maitri has asked a question. Does fast-forward breeding help rapid improvement in minor millets?
Of course. So the thing is that in any crop where you are working, the first thing is, and this is our mantra, and that's what we did in this chickpea, pigeon pea, or groundnut. When I joined, we did not have those resources. Sundram, you remember that? When
Yes. Yeah.
So rice has always been the model, but now many people say that now you can do each and everything, even chickpea, pigeon pea, what you would like to do in rice. So what will happen that in minor millets also, and I gave those 4 approaches, and I don't say that you need to use all the 4 approaches, but then depending on the trade, depending on the possibilities, first is you should have the reference genome for all of them. You need to have some sequencing data on the genetic variation data. You need to have the phenotyping. Based on these things, you can implement these GAV 2.0 approaches, including marker-assisted backcrossing, optimal contribution selection. So yes, we have a possibility. My feeling is, and this is my own experience, when you are working on those minor crop community, if you are not working on rice, because in rice, the whole world is working and you cannot count the number of the researchers, number of the research programs, that how many people are working on rice, right? Even in India, you cannot count. If you will ask me how many people are working on chickpea, I will just take 2 minutes and I can count and then tell that yes, this many. Same issue with these minor millets. What we need to do, we need to have the people, we need to have a community, we need to have some dedicated people who can motivate the community. You can bring that other people, you can do anything in any crop provided you have this community, you have got the support, you are having the financial support, etc. So I think these things are possible. You are having the technology, you can deploy them in any crop.
Dr. Rajiv, just a suggestion, not a comment. One thing, like say, we have a lot of, like say, very small scale centers as part of coordinated research system who are doing very good breeding work, but they don't have access to these tools. So what kind of changes we need in India in terms of providing access to some of these modern tools so that they can also use these tools? Of course, now outsourcing is the mode for going ahead with that. So do you think creating regional genotyping hubs, whether public sector or private sector or somewhere in between, could be the right choice?
So I would like to take you back in 2014. And in one of those meetings in San Diego, so some people from the Gates Foundation and myself and some other colleagues from IRRW, Summit, or all these people, we were having this discussion. And one of the objective was that CG systems, some of the CG institute, they are able to do it, but some national program also, like India has delivered, and you yourself is an example in this direction. Dr. A.K. Singh also, many other colleagues from your institute, NRI, and as I mentioned, there are many. But now the thing is, we would like to see these things as an integral part of the breeding. And if so, now, do we like to have the breeders to waste their time? I'm using the word waste, to run the gel and to have this analysis, etc., and also make those processes laborious and time consuming and expensive, or we can make something cheaper. And then based on these things, we initiated this project, high throughput genotyping project, HTPG project. And I was the PI of that project. Now, through that HTPG project, we created the competition in the genotyping service providing companies. We created the demand. We said, so many million data points we need to generate in this crop, etc. We worked with the CG centers, IRRW, Summit, CIAD, many other centers, different national partners. Now we reached at a stage that you can genotype in just $1.5 per sample, including the DNA extraction. Otherwise, if you go in your lab in the DNA, this costs $3 to $4. Now you need to have those kind of genotyping centers. You need to have some analytical support. You think that, for instance, in the ICR Institute or so, can you have some labs, some hubs that as soon as the data comes, they quickly analyze, tell the breeder which line you need to select, what they need to do, etc. So at the same thing, when you are doing the trait mapping, you got fantastic center for ACREP, and Dr. T.R. Sharma, our DDG Crop Science Research nowadays, he's talking how you can involve these ACREP centers for generating the high quality phenotyping data. Many people got the breeding population, how they can share, how can they collect the phenotyping data from all these different places. So I think if we need to do in this direction that, well, coordinated, centralized, genotyping, phenotyping, analytical centers. Analytical centers, they are very, very key, especially when you are talking about the genomic prediction, optimal contribution selection. In our country, we still have some shortage of those people. We need to train our people in this particular area.
That's a wonderful answer, Dr. Rajiv. I totally agree with you. We have one more question from my colleague, Dr. Sheikh Mira, who is presently under deputation with the FED in Egypt. He's an extension specialist, rather a digital extension specialist. His question is, how responsive the public extension systems were in Africa compared to the fast-forward seed systems or project-based interventions in creating and sustaining the required seed systems? This is the first question.
Yeah. So I have read the entire question of Sheikh Mira. He's also a good friend of mine. So for that, I will send you the links of those 2 books, and they are freely available. You download those books and you will really feel very happy that how the Gates Foundation support and our collaborative institute, including CIAT, IITA, ICAR-Central, and many companies, they played an important role. And the most important part was, and which happens in many times when you are having the projects, you develop those seed delivery platform, but sustainability is an issue. And then we have also developed some of those digital tools also that well, and you can talk to our people, Ram Dhulipala and other people here. So what am I saying, that not only just we have created these things, but the most important thing is that how you can have this business model and then do this thing sustainable. Fortunately, this is happening, at least in some countries or so, but we need to have the national government support also very much required in these things. And I don't know that how many people are here, senior people in this rice community. This Rockefeller Foundation network projects was a key to start the molecular breeding in rice in India. They came, they trained the people, they established the different labs, they left. India continued to have the sustainable program. China, we have seen that one. So I think that once you create those kind of, now HTPG project is over. But now here in this case, instead of government, we have done this thing with Intertech. Now this is sustainable. So SAIC, it's very important to have this sustainable platform, sustainable approaches, whatever you would like to do. So I think this is very, very important from that perspective.
I'll drop the last question related to GM crops. It's more of political and less of scientific. So Dr. Rajiv, it was a really wonderful experience listening to you for all of us. And thank you. I now request Dr. Himanshu Pathak to continue forward and offer a vote of thanks to both the speakers.
Thank you. And before Dr. Pathak comes, I would like to thank all the people who have put very nice words and appreciated. Thanks everybody, and thanks for listening. And thank you ARRW for giving me this opportunity. Sundaram, you are a great friend. Kutub is there. Dr. Himanshu Pathak and many other colleagues were. Dr. Swain, the director of the NRRI. Thank you everyone. And Dr. Beg also, he was the one who was in touch with me. I hope he's here in somewhere in this meeting. Thank you.
Thank you.
Okay, thank you, Dr. Rajiv. That was my job actually. Thank you very much. Thank you very much. Friends, every good thing comes to an end, and that is also for today's presentation. Professor Holger and Dr. Rajiv first name. As you know that we are celebrating the Diamond Jubilee of our association. And let me tell you, while listening to both of your presentations, it simply came in my mind that probably these two lectures, these two evening lectures on the Diamond Jubilee celebration of our association will be remembered for a long time to come. Will be certainly remembered for a long time to come. This was so important, so lucid, and full of enthusiasm from both of you. I was watching both of you, Professor Holger and also Rajiv, so passionate both of you are on the subject, and also what you could achieve and what we are all expecting from the research of both of you. So thank you very much. Thank you very much on behalf of our association, on behalf of the whole rice community. And today they have gathered in large number. It was at one point of time more than 160 or so. So thank you very much. And of course, my special thanks to our co-chairs, Professor Padmini Swai Madam, and of course, our friend, Dr. Sundaram. Thank you very much for very nicely organizing both the presentations. And of course, our Professor Holger, our dinner is waiting actually. But actually, we do not mind to delay it further. because this was a treat. This was a treat, and I think somebody has mentioned it was a music. So maybe whatever you call it, it could be music, it could be treat, but whatever word you use, these were fantastic. These were really, really fantastic in terms of contents, in terms of lucidity, in terms of enthusiasm, and lots of things which already been achieved and what are going to come, going to come in future. So thank you very much. And also my special thanks to Kutub, our youngest friend probably, and also a very passionate molecular biologist, also working on some of these areas, for so nicely moderating the whole session. Friends, tomorrow morning, again, we all will join at 9:30. Professor Holger, thank you very much. Dr. Rajiv Varsney, both of you can join tomorrow. Again, I don't know, probably could be very busy. Tomorrow, again, we are going to have some very brilliant presentations, including another plenary lecture, which will be delivered by Dr. T. Mahapatra, our Honorable Director General and also Secretary there. So if time permits, please join us. It will be really, really good occasion to have you tomorrow again. Once again, I thank each and every one of you for joining us this evening, and of course, continuing your very good research in rice or even pulses, chickpea, and many other crops. Thank you very much. Good night. Shubharatri, Sabba Khair, and please take care of yourself. Thank you very much.
About the dinner for us.
Yes, it is ready actually. We are just, it is online. It is online.
Thank you.
Thank you. Bye.
Thank you very much.
Thank you very much.
Thank you very much.
Thank you very much.
Thank you very much.